what lies beyond the limits of our world. Our journey begins close to home, uncovering the long-hidden secrets of the far side of the Moon, a world that remained invisible to humanity for millennia. But the Moon is only the first step. We then travel across the void to our grand galactic neighbour, the Andromeda Galaxy. What lurks within its core of 1 trillion stars, and what is the inevitable fate awaiting our own Milky Way. Finally, we push past the boundaries of known space, peering 13 billion years into the past to witness the cosmic dawn, the moment the first stars ignited and the very first galaxies were born. Settle in for an epic voyage through scale, time, and the greatest mysteries of the cosmos. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. It's the part we never see from Earth, always turned away, hidden in darkness. For decades we had no idea what was out there. No landings, no close-up images, just mystery. But that changed. NASA sent missions, orbiters, and high-tech instruments to explore it. What they found? Massive craters from ancient impacts, strange minerals that don't match anything nearby, signals so magnetic, powerful, and unexplained, even signs of frozen water, trapped in deep, permanent shadows. It's a place that looks dead, but something about it doesn't add up. So what's really out there on the Moon's far side, and why is NASA still so interested? Before we begin, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, subscribe to our channel, and settle in for a fascinating journey. The Moon, our closest celestial neighbour, presents a familiar face to Earth. For as long as humanity has gazed skyward, we have seen the same patterns of dark volcanic plains and bright cratered highlands. This constancy is not a trick of light or distance, but a fundamental characteristic of the Moon's behaviour, a phenomenon known as tidal locking. Understanding tidal locking is central to grasping why one side of the Moon remained utterly hidden from human eyes for countless millennia, shrouded in an enduring mystery that only modern spaceflight could unravel. Tidal locking occurs when the gravitational pull of a larger body, in this case Earth, shapes the rotation of a smaller orbiting body, the Moon. Over an immensely long span of cosmic time, the Earth's gravity exerted a profound influence on the Moon. The Moon is not a perfect sphere. It possesses slight bulges, both on the side facing Earth and on the opposite side. These bulges are created by the Earth's gravitational pull, which tugs more strongly on the near side of the Moon and slightly less strongly on the far side, stretching the Moon slightly along the line connecting the two celestial bodies. This differential gravitational pull creates a tidal bulge. Imagine, if you will, the early Moon spinning much faster than it does today. As it orbited Earth, the Earth's gravity would constantly try to pull these bulges back into alignment, much like how Earth's gravity pulls on the oceans, creating tides. This constant gravitational tug created a torque, a rotational force, on the Moon. This torque acted like a brake, gradually slowing down the Moon's spin. Over hundreds of millions, possibly billions of years, this braking effect continued. The Moon's rotational energy was slowly dissipated, primarily through internal friction within its rocky interior, which would have generated a minuscule amount of heat. This process was relentless and irreversible until a state of equilibrium was reached. The equilibrium state is achieved when the Moon's period of rotation on its axis precisely matches its period of revolution around the Earth. In simpler terms, the Moon takes the same amount of time to spin around once as it does to complete one orbit around our planet. This synchronized dance means that the same hemisphere is perpetually oriented towards Earth. From our vantage point, it appears as though the Moon is not rotating at all, but it is. Its rotation is just perfectly matched with its orbital speed. This is similar to how a person might walk around a merry-go-round, always facing its center. They are rotating relative to the outside world, but not relative to the merry-go-round's central pole. For the Moon, this stable configuration minimizes the gravitational stresses exerted by Earth, leading to the tidally locked state we observe today. This phenomenon is not unique to the Earth-Moon system. Many moons throughout our solar system are tidally locked to their parent planets. For example, Charon, the largest moon of the dwarf planet Pluto, is tidally locked not only to Pluto, but Pluto is also tidally locked to Charon, meaning they always show the same face to each other. This is a common outcome of powerful gravitational interactions over vast timescales, particularly for satellites orbiting relatively close to massive planets. The physical principles behind it involve the transfer of angular momentum and the search for the most energetically favourable configuration in a gravitational field. While it is true that the same side of the Moon generally faces Earth, we actually get to see slightly more than 50% of its surface over time. This is due to phenomena called librations. Librations are small oscillations or wobbles in the Moon's apparent position as seen from Earth. There are several types of librations. Optical librations are due to changes in our viewing geometry. For instance, the Moon's orbit around Earth is not a perfect circle, but an ellipse. When the Moon is closer to Earth in its orbit, it moves slightly faster, and when it is farther away, it moves slightly slower. However, its spin rate remains nearly constant. This difference in speed allows us to peak slightly around its eastern and western limbs at different points in its orbit, revealing a little more of the surface. Another optical libration is caused by the tilt of the Moon's axis relative to its orbital plane. Just as the Earth's tilt causes seasons, the Moon's tilt allows us to see slightly over its north and south poles at different times of the month. So, while a core 50% of the Moon's surface is always visible, and another 50% is always hidden, there is a 9% sliver of territory along the edge of the Moon that sometimes swings into view and sometimes swings out of view, depending on these librations. This means that, over the course of a full lunar cycle, a total of approximately 59% of the Moon's surface can be seen from Earth. However, the majority of the far side, approximately 41%, remains perpetually out of our direct line of sight. It is this large, truly hidden portion that constituted the enduring mystery. The far side's inherent invisibility from Earth meant that for thousands of years, its terrain, its features, and its very nature remained entirely speculative. Ancient astronomers, keen observers of the night sky, could map the features of the near side with increasing detail, even assigning names to its craters and seas. Yet the other half of our lunar companion was a blank canvas, a realm of scientific and imaginative conjecture. No telescope, no matter how powerful or refined, could bend light around the Moon to reveal its unseen hemisphere. From the earliest rudimentary spyglasses of Galileo Galilei in the 17th century to the massive ground-based observatories of the 20th century, every instrument was fundamentally limited by the Moon's tidally locked orientation. Humanity could only observe what was presented to them, and the far side steadfastly refused to show itself. This lack of direct observation meant that early lunar maps were incomplete by definition. They represented only the visible surface, leaving the reverse side to the realm of artists' imaginings and educated guesses. Without empirical data, scientists could only hypothesize about its appearance. Some might have assumed it was similar to the near side, while others might have speculated it was vastly different. There was no way to confirm or deny these theories from Earth. The advent of photography in the 19th century allowed for more detailed and permanent records of the near side, but it did nothing to pierce the veil of the far side. Even as mapping techniques advanced, creating intricate topographical charts of the visible lunar surface, the far side remained a cartographical void. The true reason for its prolonged mystery was the absence of a crucial technological leap: space travel. Until the mid-20th century, the concept of sending probes beyond Earth's atmosphere was largely confined to the pages of science fiction. The engineering challenges were immense, developing rockets powerful enough to escape Earth's gravity, designing guidance systems capable of precise trajectories over vast distances, and creating communication systems that could transmit data back to Earth from interplanetary space. These were not trivial hurdles. They represented the very cutting edge of scientific and engineering endeavour for their time. The dawn of the space age, sparked by the launch of Sputnik 1 by the Soviet Union in the mid-1950s, fundamentally altered this reality. Suddenly, what was once pure fantasy became a tangible goal. The race to the moon intensified, driven by geopolitical competition and an insatiable scientific curiosity. But even with powerful rockets, directly observing the far side posed an immediate and unique problem: communication. A spacecraft on the far side of the moon would be entirely blocked by the moon itself from sending radio signals directly back to Earth. There would be no line of sight, creating a communication blind spot. Imagine trying to talk to someone on the other side of a very large hill. Your voice simply would not carry. For a spacecraft, this meant that any data it collected, any images it captured, would be trapped on board unless a solution was found. This challenge necessitated the development of advanced relay technologies, such as orbiting satellites that could receive signals from a far-side probe and then retransmit them to Earth. Without such relays, long-duration missions to the far side would be impossible to control or to retrieve data from. The first successful venture to glimpse the far side was undertaken by the Soviet Union. In October of 1959, their Luna 3 probe swung around the moon, becoming the first spacecraft to capture images of this enigmatic territory. The images were crude and blurry by modern standards, distorted by the primitive camera technology and the vast distance, but they were revolutionary. They revealed a surface much more heavily cratered than the near side, notably lacking the large dark volcanic plains, or maria, that define the visible lunar landscape. This initial revelation confirmed that the far side was not simply a mirror image of the near side. It possessed distinct geological characteristics that hinted at a different evolutionary history. The excitement generated by these first distant photographs was immense, confirming the potential for entirely new scientific discoveries. The initial Luna 3 images were a tantalizing first step, but they were far from providing a comprehensive understanding. NASA, then a relatively young space agency, quickly began its own ambitious lunar exploration programs. Its Surveyor series of uncrewed landers and Lunar Orbiter series of photographic missions laid crucial groundwork, mapping the visible side in preparation for human landings. While these early NASA missions primarily focused on the near side for practical reasons related to landing sites and communication, the scientific imperative to explore the entire moon remained strong. Setting the stage for its eventual exploration was a multifaceted endeavour that extended beyond merely developing powerful rockets. It involved decades of meticulous scientific planning, technological innovation, and international collaboration, or competition. The desire to see the unseen was not just an idle curiosity. It was driven by fundamental questions about the moon's origin and evolution. Was the far side older? Had it experienced a different bombardment history? Did it hold unique resources or geological formations that could shed light on the early solar system? These were the kinds of scientific inquiries that fueled the push for its exploration. The technological roadmap was incremental. First, flybys like Luna 3, which offered fleeting glimpses. Next, orbiting missions, which could systematically map the entire surface at higher resolutions over longer periods. Then, the ultimate challenge of soft landings, to analyze the surface material directly. Each step built upon the last, refining techniques for navigation, imaging, and data transmission. The development of miniaturized electronics, powerful antennas, and robust power systems was critical. For the far side, in particular, the concept of a communication relay satellite became paramount. Without a system to bounce signals, missions would essentially be operating incommunicado for critical periods. The importance of relay satellites cannot be overstated for any long-duration presence or detailed exploration of the far side. Future lunar missions, whether robotic or human, that aim to operate extensively on the far side will rely heavily on a dedicated network of communication orbiters. These orbiters would act as intermediaries, receiving data from surface assets and transmitting commands to them, effectively extending Earth's communication reach beyond the moon's limb. This technical solution overcomes the fundamental line-of-sight issue that made the far side so mysterious for so long. The ongoing exploration of the far side represents a triumph of human ingenuity and persistence. From millennia of ignorance about its existence, to blurry first images, to detailed topographical maps and geological surveys, our understanding has advanced exponentially. The hidden side of the moon is no longer a blank page. It is a canvas rich with scientific data, revealing clues about the moon's tumultuous past, its geological distinctions, and its potential as a site for future astronomical observatories, shielded from Earth's radio noise. The journey to unveil the hidden moon was long and arduous, but its secrets are steadily yielding to the relentless pursuit of knowledge, driven by the inherent human desire to explore the unknown. It is a testament to how far we have come from simply gazing at a single, unchanging face in the night sky to actively exploring the entirety of our celestial partner. The scientific community's fascination with the far side stems from the distinct geological differences observed from early on. The near side is characterized by extensive maria, the dark plains formed by ancient volcanic eruptions which are relatively smooth and less cratered. The far side, in stark contrast, is dominated by rugged, heavily cratered highlands with very few maria. This asymmetry has profound implications for understanding the moon's formation and evolution. Theories suggest that the near side's thinner crust allowed volcanic material to reach the surface more easily, forming the maria. The far side, with its thicker crust, may have resisted such eruptions. This fundamental difference in crustal thickness and composition is one of the most significant discoveries made possible by exploring the far side. NASA's subsequent missions have been crucial in refining these theories, transmitting complex images and scientific telemetry. Power systems shifted from short-duration batteries to long-lasting solar panels and radioisotope thermoelectric generators, allowing missions to operate for years. Each of these innovations played a crucial role in enabling NASA and other space agencies to move beyond simple flybys and into detailed long-term mapping and observation of the entire moon, including its hidden side. The scientific instruments also became more precise and varied. From basic cameras, they progressed to spectrometers that could identify minerals, altimeters that could map topography with astonishing accuracy, and gravimeters that could detect subtle variations in the moon's gravitational field. These sophisticated tools, deployed on missions orbiting the moon, meticulously gathered data that slowly but surely peeled back the layers of mystery surrounding the far side. The persistent communication challenge for far-side operations means that any future human outpost or robotic base on that hemisphere would require a dedicated network of relay satellites. These satellites would typically orbit the moon in specific pathways that allow them to maintain a line of sight with both Earth and the far-side base. This network ensures continuous communication, enabling mission control to send commands, receive vital telemetry, and download scientific data without interruption. Without such a relay system, operations would be limited to brief periods when the base might be visible due to librations or require immense power for signals to diffract around the moon, which is not practical. The development and deployment of these relay satellites are as critical as the surface landers themselves, forming an essential bridge in our sustained exploration of the hidden hemisphere. The scientific questions addressed by exploring the far side extend beyond geology. The far side, being shielded from Earth's radio noise, offers a unique environment for radio astronomy. Future observatories placed there could listen to the universe without interference, potentially detecting signals from the very early universe that are currently masked by our own planet's radio emissions. This potential makes the far side a highly desirable location for certain types of scientific research, adding another layer to its importance. The long-term vision of lunar exploration includes not just scientific outposts but also human habitats, and understanding the far side's environment, its radiation levels, temperature extremes and regolith properties, is vital for ensuring the safety and sustainability of such endeavours. Every piece of data collected by NASA missions, whether from orbit or hypothetical future landers, contributes to this grander vision, transforming the once-hidden moon into a frontier for humanity's expansion. The systematic exploration has illuminated not just the moon, but our place in the cosmos, revealing the intricate dance of gravitational forces and the relentless march of geological time. The hidden moon is a testament to the power of scientific inquiry and technological advancement, continually revealing new wonders. The human fascination with the moon, and indeed with the heavens beyond, stretches back to the earliest moments of our existence. Before the scientific method, before telescopes, and before the very concept of space travel, the moon was a mystical object, a luminous orb in the night sky that inspired awe, wonder, and countless myths. Ancient civilizations across the globe wove elaborate tales around this celestial body, often associating it with deities, fertility, the passage of time, and the mysteries of the night. It was seen as a silver chariot driven across the heavens, a watchful eye, or a powerful entity influencing tides and harvests. These early thoughts were not about physical travel, but about understanding the moon's nature and its spiritual significance. Philosophers like Anaxagoras, an ancient Greek thinker of the 5th century before the Common Era, boldly suggested that the moon was a rocky body similar to Earth, illuminated by the sun, rather than a divine light source. This was a radical idea for his time, challenging prevailing mystical beliefs and laying a foundational, albeit rudimentary, stone for later scientific inquiry. Aristotle, another towering figure in ancient Greek philosophy, built upon these observations, integrating them into his geocentric model of the universe, where the Earth was at the centre and celestial bodies moved in perfect circles around it. While his model was ultimately incorrect, his systematic approach to observing and theorizing about the cosmos influenced thinkers for over 1,000 years. The idea of the moon as a world, a place of substance rather than just a light, began to take tenuous root in these early philosophical inquiries. The dream of flying, of transcending earthly bounds, also permeated ancient thought. The myth of Icarus, attempting to fly to the sun with wax wings, serves as a powerful allegory for humanity's enduring aspiration to conquer the skies. While these were not direct dreams of space travel, they represented a fundamental yearning to escape the confines of the Earth's surface, a precursor to the grander ambition of reaching other celestial bodies. For many centuries, the lack of fundamental scientific understanding about physics, gravity, and atmospheric conditions meant that the concept of travelling to the moon remained firmly in the realm of fantasy and allegory. It was a subject for poets and storytellers, not engineers or scientists. The 17th century marked a pivotal shift, as the scientific revolution began to transform humanity's understanding of the universe. The invention of the telescope by Hans Lippershey and its subsequent astronomical application by Galileo Galilei in the early 1600s revolutionized lunar observation. Galileo's telescopic observations revealed that the moon was not a perfect smooth sphere, as previously thought, but a rugged world with mountains, valleys, and craters resembling landscapes on Earth. He even estimated the heights of lunar mountains by observing the shadows they cast. This empirical evidence, derived from direct observation, solidified the idea of the moon as a physical body, a world in its own right, rather than a luminous projection or a divine entity. This new understanding spurred imaginative leaps from the realm of pure myth to a more grounded, albeit still fictional, exploration of lunar travel. Inspired by these new scientific insights, writers began to pen early works of science fiction that explored the idea of travelling to the moon. In the mid-1600s, Cyrano de Bergerac, a French playwright and duelist, wrote The Other World, Comical History of the States and Empires of the Moon. His fantastical methods of reaching the moon included using dew-filled bottles that would evaporate and lift him, or rockets powered by firecrackers. While wildly unscientific, his work was significant for its portrayal of lunar inhabitants and a society on the moon. Around the same time, Francis Godwin, an English bishop, published The Man in the Moon, where his protagonist travels to the moon in a device pulled by trained geese. These narratives, though fantastical, represented a nascent human desire to imagine the mechanics of such a journey, even if those mechanics were entirely speculative. They explored the challenges of space, albeit imaginatively, such as the problem of gravity and the need for a breathable atmosphere. The 18th and 19th centuries saw a further flourishing of speculative fiction that increasingly intertwined scientific concepts with imaginative storytelling. Jules Verne, a French novelist, became a titan of this genre in the 19th century. His 1965 novel, From the Earth to the Moon, is perhaps the most famous and influential work of early space travel fiction. Verne's concept for lunar travel was a giant cannon, firing a projectile containing passengers towards the moon. While a cannon launch would be lethally impractical in reality due to the immense g-forces, Verne meticulously calculated the trajectory, the required muzzle velocity, and even the dimensions of his fictional space gun. He described the challenges of living in a projectile during flight and the experience of weightlessness, demonstrating a remarkable effort to ground his fiction in the scientific knowledge of his time. His work captivated public imagination and subtly introduced the scientific principles of ballistics and trajectory to a wide audience. Another prominent 19th century author, H.G. Wells, an English writer, contributed significantly to the genre with his 1901 novel, The First Men in the Moon. Wells conceived of a more scientifically imaginative method of propulsion, a substance called cavaret, which could nullify gravity. While entirely fictional, this concept allowed Wells to explore the idea of controlled flight to the moon and the challenges of returning. He also created a vivid portrayal of an alien civilization inhabiting the moon, adding a layer of sociological and philosophical inquiry to the space travel narrative. These literary works were crucial in cultivating a widespread public fascination with space travel, transforming it from an obscure scientific concept into an exciting and plausible future endeavour. They bridged the gap between pure fantasy and the burgeoning fields of physics and engineering, inspiring generations of future scientists and engineers. The true intellectual groundwork for space travel began to be laid by a remarkable group of visionaries in the late 19th and early 20th centuries, often working independently and against considerable skepticism. Konstantin Tsiolkovsky, a Russian schoolteacher and self-taught scientist, stands out as one of the most significant theoretical pioneers of astronautics. Working in relative isolation in the late 1800s and early 1900s, Tsiolkovsky developed the fundamental principles of rocketry. He famously formulated the rocket equation, a mathematical formula that describes the velocity change a rocket can achieve based on the exhaust velocity of its propellant and the mass ratio of the rocket, the ratio of its initial mass to its final mass after expelling propellant. This equation demonstrated that high exhaust velocities and efficient fuel usage were paramount for achieving spaceflight. Tsiolkovsky was also a strong proponent of liquid-fueled rockets, recognizing their superior thrust and controllability compared to solid-fueled alternatives. He conceptualized multi-stage rockets, understanding that shedding spent fuel tanks and engines during flight would dramatically increase efficiency and enable higher velocities. He even theorized about the use of liquid oxygen and liquid hydrogen as propellants that are still used in modern spaceflight due to their exceptional energy density. Beyond the technical specifics, Tsiolkovsky was a deep philosophical thinker who believed that humanity's destiny lay in space. He envisioned space stations, lunar bases, and the colonization of the solar system, articulating a grand vision for human expansion beyond Earth. His work, though largely unknown outside of Russia during his lifetime, provided the theoretical blueprint for subsequent practical developments in rocketry. Across the Atlantic, in the United States, Robert Goddard, an American physicist, was independently pursuing his own pioneering work in rocketry. Often ridiculed by the press and misunderstood by the public for his seemingly outlandish ideas, Goddard was a tireless experimenter. In 1926, he achieved a monumental feat, the launch of the world's first liquid-fueled rocket. This small rocket, named Nell, flew only a short distance and for a few seconds, but it was a transformative moment. It proved, in tangible terms, the viability of liquid propellant rocket technology. Goddard continued to develop and test more powerful rockets throughout his career, often facing funding challenges and working with limited resources. He patented numerous inventions critical to rocket design, including multi-stage rockets, fuel pumps, and guidance systems. His meticulous hands-on approach and persistent experimentation laid the practical foundation for rocketry in the United States. He solved many engineering problems that Tsiolkovsky had only theorized about, bridging the gap between abstract mathematical principles and functional hardware. In Germany, Hermann Oberth, a physicist and engineer, was another key figure in the theoretical development of spaceflight during the early 20th century. His 1923 book, The Rocket into Interplanetary Space, rigorously explored the mathematics and physics of rocket propulsion. Oberth also contributed significantly to the concept of space stations and the use of rockets for scientific research. He influenced a generation of German rocket scientists, including Wernher von Braun, who would later play a crucial role in both military rocketry and the American space program. Together, Tsiolkovsky, Goddard and Oberth are often referred to as the fathers of rocketry, their independent yet converging work forming the bedrock of modern astronautics. Their theoretical calculations showed that escape velocity, the minimum speed an object needs to break free from a planet's gravitational pull, was achievable with rockets, moving the idea of space travel from the realm of the impossible to the realm of the challenging but attainable. The grim reality of World War II inadvertently accelerated rocket development. The German V-2 rocket, developed under the leadership of Wernher von Braun, was a military weapon, but it was also the world's first large-scale liquid-fueled ballistic missile capable of reaching the edge of space. The V-2 demonstrated the immense power and potential of rocket technology. After the war, both the United States and the Soviet Union acquired German rocket scientists and V-2 technology, which provided a significant leap forward in their respective missile and nascent space programs. This wartime development, while destructive in its original intent, provided invaluable knowledge and hardware that directly contributed to the post-war space race. The dawn of the Cold War in the mid-20th century provided a powerful geopolitical impetus for space exploration. The space race between the United States and the Soviet Union became a proxy battle for ideological supremacy, technological superiority, and national prestige. The launch of Sputnik 1 by the Soviet Union in October of 1957, the first artificial satellite to orbit Earth, sent shockwaves through the United States. It demonstrated Soviet technological prowess and ignited a fierce determination in the US to catch up and surpass. This event directly led to the formation of the National Aeronautics and Space Administration, or NASA, in 1958, consolidating various American civilian space efforts under one agency. The initial focus was on catching up to the Soviets and then aiming for the ultimate prize, putting a human on the moon. Before NASA, various organizations had contributed to aerospace research, but Sputnik underscored the need for a unified national effort. The public's imagination, already primed by decades of science fiction, was now fully captivated by the prospect of space travel. The idea of reaching the moon, once a fantastic dream, now became a concrete national goal, backed by massive government funding and political will. The space race transformed the early scientific ideas about space travel from theoretical discussions among a few visionaries into a monumental national endeavour involving hundreds of thousands of engineers, scientists and technicians. It created an urgency and a scale of investment that was unprecedented. The transition from early space dreams to actual space missions was a complex interplay of scientific curiosity, technological breakthroughs, and intense geopolitical competition, all converging to launch humanity beyond its home planet. The foundations laid by the independent thinkers of the previous centuries were now being built upon by entire nations, striving to turn the once impossible dream into a reality. The very idea of an astronaut or cosmonaut emerged from this intense period of rapid development and audacious ambition, forever altering humanity's perspective on its place in the universe. For untold millennia, the far side of the moon remained an impenetrable mystery to humanity. From Earth, only one face of our celestial neighbour was ever visible, a consequence of what scientists call tidal locking. This meant that any knowledge of the moon's other hemisphere would require a monumental leap in technology, the ability to send spacecraft beyond our planet's gravitational pull and to navigate them around the moon itself. The mid-20th century witnessed the beginning of this transformative era, as the burgeoning space race between two global superpowers, the Soviet Union and the United States, propelled humanity toward its first direct observations of this enigmatic lunar territory. It was the Soviet Union, with its early lead in rocket technology, that achieved this pioneering feat, offering the first blurry but profoundly significant glimpses of the moon's unseen side. The mission responsible for this groundbreaking achievement was Luna 3, a robotic probe launched by the Soviet Union. The launch occurred in the month of October in the year 1959. This timing placed it just over 2 years after the momentous launch of Sputnik 1, the Earth's first artificial satellite, which had stunned the world and ignited the intense space race. The Luna 3 mission was ambitious for its time, designed not just to orbit Earth, but to journey towards the moon, swing around it, and then transmit images back across the vast distance of space. Its primary objective was singular and revolutionary: to photograph the side of the moon that had never before been seen by human eyes, or indeed by any terrestrial instrument. The design of the Luna 3 spacecraft was a testament to the engineering capabilities of the late 1950s, constrained by the then available technology. It was a cylindrical craft tapering at one end, equipped with solar panels to generate electrical power and antennas for communication. Crucially, it carried an imaging system that was primitive by today's standards, but revolutionary for its era. This system consisted of a pair of cameras with different focal lengths, allowing for both wider views and slightly more zoomed-in shots. What made the system particularly ingenious, and indeed challenging, was its onboard film processing capability. Traditional film, similar to that used in ground-based cameras, was employed. Once images were captured, the film would be automatically developed, fixed and dried within the spacecraft itself, all while travelling through the harsh vacuum of space. Following the onboard development, the images on the film had to be converted into an electronic signal for transmission back to Earth. This was achieved by a process similar to early television broadcasting. A tiny light spot would scan the developed film, line by line, detecting variations in light and shadow. These variations were then translated into an electrical signal, which was then radioed back to receiving stations on Earth. This method was inherently prone to noise and distortion, contributing significantly to the low quality of the resulting images, but it represented the cutting edge of remote imaging and data transmission for its time. The communication link across hundreds of thousands of miles was tenuous, and the signal received on Earth was incredibly weak, requiring powerful antennas and sophisticated signal processing to extract any meaningful data. The trajectory of Luna 3 was also a masterpiece of early space navigation. Unlike later missions that aim for precise lunar orbits or landings, Luna 3 was designed for a circumlunar flyby. It launched from Earth, travelled directly towards the Moon, and then used the Moon's gravity to alter its course, swinging around the far side before heading back towards Earth. This manoeuvre, known as a gravity assist, was a clever way to achieve the desired path without requiring excessive amounts of propellant. The timing of the photography was critical. The spacecraft had to be positioned correctly, relative to the Moon's rotation and the Sun's illumination to capture the far side in sunlight. On the 7th day of October, in the year 1959, as Luna 3 arced around the Moon, its cameras snapped pictures of the previously unseen hemisphere. The images, once transmitted back to Earth, were indeed blurry. They were characterized by low resolution, making it difficult to discern fine details. Streaks and static often marred the frames, artifacts of the primitive transmission technology and the vast distance the signals had to traverse. Yet, despite their imperfections, these images were nothing short of breathtaking. They provided the very first empirical evidence of what lay on the other side of our Moon. The most immediate and striking revelation from these initial blurry photographs was the stark difference between the far side and the familiar near side of the Moon. The near side is easily recognizable by its extensive, dark, relatively smooth plains, known as maria, or seas, which are actually vast basins formed by ancient volcanic eruptions that subsequently filled with solidified lava. These maria cover a significant portion of the near side, giving it its distinctive face-like appearance. The Luna 3 images, however, showed a strikingly different landscape for the far side. It was predominantly covered in rugged, heavily cratered terrain, with a notable absence of the large, dark maria that characterized the visible side. Only a few smaller, irregular dark patches, vaguely resembling maria, were discernible, such as what would later be named Mare Moscoviense, or Moscow Sea, and an even smaller one called Mare Smithii, though Mare Smithii extends onto the edge of the near side. This immediate observation of a heavily cratered landscape dominating the far side had profound implications for lunar geology. Scientists quickly deduced that the far side had likely experienced a different geological history compared to the near side. The greater abundance of craters suggested an older, less geologically active surface, one that had not been resurfaced by extensive lava flows in the same way the near side had been. This asymmetry pointed to fundamental differences in the Moon's crustal thickness and internal structure between its two hemispheres. It challenged previous assumptions that the Moon might be uniform in its composition and geological evolution across its entire surface. The initial scientific interpretations stemming from these first images were revolutionary. The lack of maria on the far side suggested that the lunar crust there might be significantly thicker than on the near side. A thicker crust would make it more difficult for magma from the Moon's interior to breach the surface and create large volcanic plains. This hypothesis, though initially speculative, would later be supported by data from subsequent missions. The images also provided further evidence for the intense bombardment phase that the early solar system experienced, with the far side serving as a more preserved record of these impacts due to less subsequent volcanic activity. The naming of newly discovered features on the far side also began with these early images. The most prominent feature identified, a vast impact basin, was named Tsiolkovsky, in honor of Konstantin Tsiolkovsky, a pioneering Russian rocket scientist whose theoretical work had paved the way for space travel. Other features were given names reflecting the Soviet contributions to space exploration. These names began the process of mapping and characterizing a landscape that had previously been entirely unknown to humanity. The impact of Luna 3's achievement reverberated far beyond the scientific community. It was a massive propaganda victory for the Soviet Union in the height of the space race, demonstrating their continuing technological lead. For the broader public, it was an awe-inspiring moment, suddenly making the Moon feel less mysterious and more like a real, albeit alien world. The photographs sparked immense public interest and fueled further scientific curiosity about the Moon. They confirmed that humanity had the capability to venture beyond Earth's immediate vicinity and to reveal the secrets of other celestial bodies. The mission provided crucial data that influenced future mission planning for both Soviet and American space programs. For the Americans, who were then in the early stages of establishing NASA and planning their own lunar missions, Luna 3's findings provided invaluable intelligence about the lunar environment. It underscored the need for detailed mapping and reconnaissance of the Moon's entire surface, not just the familiar near side. The experience gained in orbital maneuvers, remote imaging, and long-distance communication from Luna 3, though Soviet, offered lessons that could be studied and adapted by other spacefaring nations. Furthermore, Luna 3's imagery provided crucial insights into the phenomenon of tidal locking itself. By confirming the dramatic differences between the two lunar hemispheres, it underscored how Earth's gravitational pull had not only locked the Moon's rotation, but also influenced its geological development in an asymmetrical way. This reinforced the understanding that celestial mechanics could profoundly shape the very geology of orbiting bodies. The far side was not simply the other side. It was a distinct geological entity, shaped by billions of years of cosmic forces, and its secrets were only just beginning to be revealed by these first pioneering glimpses. The blurry images were not just photographs, they were windows into a previously unimaginable world, opening new avenues for scientific inquiry and setting the stage for more detailed explorations that would follow. They marked a profound shift from speculation to empirical observation in our understanding of our nearest celestial neighbour. The significance of these initial images cannot be overstated. Before Luna 3, the far side of the Moon was a realm of conjecture. Some theories, based on limited data from near-side observations, suggested a fairly uniform lunar surface. Others allowed for the possibility of differences, but without any photographic evidence, these remained hypotheses. Luna 3 provided the first concrete proof that the Moon was indeed asymmetrical. This asymmetry sparked intense scientific debate and research, leading to new models for the Moon's formation and evolution. For instance, the theory that the far side has a significantly thicker crust, which prevented widespread volcanic eruptions and maria formation, gained considerable traction after Luna 3's findings. This crustal thickness difference might be linked to the Moon's formation from the debris of a giant impact, where material might have coalesced unevenly around a central core. The heavily cratered nature of the far side also reinforced the idea of an early, intense period of bombardment in the solar system, providing a relatively pristine record of these ancient impacts compared to the more resurfaced near side. The technological challenges overcome by Luna 3 also paved the way for future space missions. Developing film in a vacuum, scanning it, and transmitting the analog signal across hundreds of thousands of miles was a remarkable engineering feat for the 1950s. The lessons learned from the reliability of its components, the performance of its propulsion system, and the accuracy of its trajectory were invaluable. These early experiences in deep space communication, even with their limitations, formed the foundation upon which more sophisticated systems for later probes and human missions would be built. The success of Luna 3 not only delivered the first images, but also demonstrated the feasibility of complex robotic missions to other celestial bodies, inspiring confidence in the pursuit of even more ambitious ventures. It was a small step for a spacecraft, but a giant leap for humanity's understanding of its lunar companion. The hidden moon was hidden no more, at least in a general sense, and the blurry outlines of its true face began to emerge from the cosmic dark. The middle of the 20th century was a period of intense global rivalry, characterized by the Cold War between the United States and the Soviet Union. This competition extended beyond terrestrial boundaries, reaching into the vast expanse of outer space. The catalyst for America's full-fledged commitment to space exploration, and specifically for the creation of its civilian space agency, came on a crisp October day in 1957. On that day, the Soviet Union successfully launched Sputnik 1, the Earth's first artificial satellite, into orbit. The small, beeping satellite circling our planet every 96 minutes sent shockwaves across the United States. It was not just a technological achievement, it was a powerful symbol of Soviet scientific and military prowess. The event, widely dubbed the Sputnik Crisis, ignited a profound sense of alarm and urgency within the American government and its populace. Prior to Sputnik, space-related research in the United States was fragmented. Various military branches, including the Army, Navy, and Air Force, were independently pursuing rocket development, primarily for ballistic missiles. Civilian scientific efforts were also underway, often under the purview of organizations like the National Advisory Committee for Aeronautics, or NACA, which had been established in the early 1900s to conduct aeronautical research. However, there was no single, unified civilian agency dedicated to exploring space for peaceful, scientific purposes. The Sputnik launch made it abundantly clear that a more cohesive and centralized approach was desperately needed if the United States was to compete effectively in this new frontier. The fragmented nature of American efforts meant that resources were sometimes duplicated, and coordination was often lacking, leaving the nation seemingly behind in the initial stages of the space race. Recognizing the strategic and scientific imperative, President Dwight D. Eisenhower took decisive action. He understood that the American response needed to be robust, comprehensive, and clearly focused on peaceful exploration rather than purely military applications. On the 29th day of July, in the year 1958, President Eisenhower signed the National Aeronautics and Space Act into law. This landmark legislation officially created the National Aeronautics and Space Administration, or NASA. The new agency was designed to consolidate and lead all civilian space activities in the United States. Its mandate was clear: to organize and conduct aeronautical and space activities for peaceful purposes, benefiting all of humankind. This was a crucial distinction from the Soviet Union's more militarized space program, though both nations' space efforts had roots in missile technology. NASA was effectively built upon the foundation of NACA, which ceased to exist as a separate entity. NACA's highly skilled engineers and scientists, along with its extensive research facilities, were absorbed into the new agency, providing an immediate and substantial technical workforce. Additionally, various other military and civilian research groups and projects were transferred to NASA, including the Jet Propulsion Laboratory, or JPL, and elements of the Army Ballistic Missile Agency. This consolidation brought together disparate talents and resources under one roof, providing the necessary infrastructure and expertise to embark on ambitious space endeavors. NASA's initial structure was designed to be agile and responsive, capable of managing large, complex projects that would push the boundaries of technology and human endurance. Its goals were not modest. They quickly expanded from simply launching satellites to putting humans into orbit and eventually to sending them to the moon. NASA's early goals for lunar exploration were ambitious and systematically planned, evolving from simpler human spaceflight missions to the ultimate lunar landing. Project Mercury was the first step in this grand human spaceflight endeavour. Its primary objective was to determine if humans could survive and function in the harsh environment of space. Launched in the early 1960s, Mercury missions involved single astronauts in small capsules, orbited Earth for short durations. These flights were crucial for understanding the effects of weightlessness on the human body, testing life support systems, and developing the critical procedures for launch, orbital flight, and safe re-entry. The success of Project Mercury, including Alan Shepard's suborbital flight and John Glenn's orbital flight, proved that humans could indeed operate effectively in space, laying the psychological and practical groundwork for more complex missions. Building upon the experience gained from Mercury, NASA launched Project Gemini. This program, conducted in the mid-1960s, involved two-person spacecraft and was designed to develop the advanced capabilities necessary for a moon landing. Gemini missions focused on mastering critical techniques such as orbital rendezvous and docking, which would be essential for connecting the lunar module to the command module in lunar orbit during an Apollo mission. Astronauts also performed spacewalks, or extravehicular activities, testing their ability to work outside the spacecraft in the vacuum of space. Gemini missions lasted for longer durations than Mercury, providing more data on long-term human endurance in space. These 12 Gemini flights were vital proving grounds, systematically perfecting the maneuvers and procedures that would be absolutely necessary for the complex journey to the Moon. The ultimate objective of these preparatory programs was Project Apollo, a monumental undertaking aimed at landing humans on the Moon and returning them safely to Earth. President John F. Kennedy's bold challenge in 1961 to land a man on the Moon before the end of the decade galvanized the nation and set a clear, ambitious target for NASA. However, before humans could land, a vast amount of basic information about the lunar surface was required. This is where NASA's initial uncrewed missions, particularly the Ranger and Surveyor programs, played an absolutely critical role. They were the robotic scouts, sent ahead to gather vital intelligence about the Moon's environment and geology, de-risking the future human missions. The Ranger program was NASA's first series of uncrewed attempts to obtain close-up images of the Moon's surface. Launched in the early to mid-1960s, these missions had a straightforward objective: to fly directly towards the Moon and transmit high-resolution television images back to Earth just before intentionally crashing onto the lunar surface. The early Ranger missions faced numerous challenges and experienced several failures, which were a painful but necessary part of the learning curve in the nascent days of deep space exploration. Technical glitches, ranging from power system failures to instrument malfunctions, plagued the initial attempts. However, each failure provided valuable lessons, allowing engineers to refine designs and procedures. The perseverance paid off with Ranger 7. Launched in July of 1964, Ranger 7 was a resounding success. As it plummeted towards the Moon, it transmitted over 4,300 close-up images, revealing details far smaller than what could be seen with Earth-based telescopes. These images showed craters as small as 1 foot across, providing unprecedented detail of the lunar terrain. Ranger 7's success was followed by Ranger 8 in February of 1965 and Ranger 9 in March of 1965, both of which also successfully delivered thousands of high-resolution images. These Ranger images were instrumental in settling a key debate among lunar scientists at the time, whether the Moon's surface was covered in a deep layer of soft dust into which a lander might sink, or if it was firm enough to support a spacecraft. The Ranger images clearly showed a relatively solid rocky surface, densely covered with craters, but firm enough to support a lander. This information was absolutely vital for the design of the Apollo lunar module's landing gear and for selecting safe landing sites. The clarity of these images also helped scientists understand the lunar regolith, the layer of loose, fragmented material covering the Moon's surface, and the effects of micrometeorite impacts. Following the success of the Ranger impact probes, NASA embarked on the Surveyor program, which represented a monumental leap in lunar exploration capability. The objective of the Surveyor missions was to achieve a soft landing on the Moon and to analyze the lunar surface directly. This was a far more complex undertaking than a simple impact. Each Surveyor spacecraft was equipped with a retro-rocket system that would fire to slow its descent, allowing for a gentle touchdown on the lunar surface. The Surveyor design was also much more sophisticated, featuring multiple television cameras to provide panoramic and close-up views of the landing site, as well as instruments to analyze the soil. Surveyor 1 achieved the first successful American soft landing on the Moon in June of 1966. This was a tremendous triumph for NASA, proving the agency's capability to safely land a spacecraft on another celestial body. Surveyor 1 transmitted over 11,000 images of its landing site, showing the landscape in incredible detail. Subsequent Surveyor missions, a total of 7 spacecraft were launched with 5 successful landings, provided even more critical data. For example, Surveyor 5 carried an alpha scattering instrument, which analysed the chemical composition of the lunar soil, confirming that it was basaltic, similar to volcanic rocks on Earth. Other surveyors were equipped with scoops that could dig trenches in the lunar regolith, providing direct information on its bearing strength and consistency. This confirmed that the lunar surface was firm enough to support the weight of the Apollo lunar module, and that astronauts could walk on it without sinking. The detailed images from Surveyor missions also helped engineers understand the nature of the rocks, boulders, and terrain that future astronauts would encounter, allowing for crucial refinements in mission planning and astronaut training. The Surveyor program essentially served as the ultimate test and validation for the Apollo landing concept. Beyond Ranger and Surveyor, NASA also initiated the Lunar Orbiter program in the mid-1960s. While some of its detailed far-side mapping would fall under a later chapter, it is important to note its role as an early American mission gathering basic information. These robotic orbiters were designed to systematically map the entire lunar surface, including both the near and far sides at high resolution. Their primary goal was to scout and photograph potential landing sites for the Apollo missions, ensuring that the chosen locations were flat, free of large boulders, and safe for a human landing. The Lunar Orbiter missions produced a comprehensive photographic atlas of the Moon, revealing details of craters, rills, and mountains across the entire globe. This data, combined with that from Ranger and Surveyor, provided an unparalleled understanding of the lunar environment, which was absolutely indispensable for the ambitious Apollo program. The Moon, our nearest celestial neighbour, presented a familiar face to Earth for countless generations. Due to the phenomenon of tidal locking, only one side of the Moon is ever visible from our planet. This means that for all of human history, until the advent of space travel, the far side of the Moon remained utterly hidden, a mysterious hemisphere known only through scientific conjecture and imaginative tales. However, with the commencement of the Apollo program by the National Aeronautics and Space Administration, or NASA, humanity gained the ability not only to orbit the Moon but eventually to land upon its near side. During these historic journeys, the Apollo astronauts, while circling the lunar body, received the unprecedented opportunity to directly observe the far side, offering the very first human accounts of its appearance and contributing a unique layer of understanding to the robotic data collected by previous probes. The pioneering mission that first carried human beings around the Moon was Apollo 8. Launched in December of 1968, Apollo 8 was a daring and accelerated mission, originally intended as an Earth orbital test flight for the Apollo Command and Service modules. However, in a strategic shift, NASA decided to send the crew of Frank Borman, James Lovell and William Anders directly to the Moon. Their mission was to orbit the Moon 10 times before returning to Earth. This decision meant that for the first time, human eyes would behold the far side of the Moon directly. As their spacecraft rounded the lunar limb, the Earth dropped out of view and the unknown hemisphere emerged into their sight. The experience was profoundly impactful for the astronauts, and their live television broadcasts back to Earth allowed millions to share in their awe, even if the images were grainy and the descriptions limited by the transmission technology of the time. As Apollo 8 completed its first orbital pass around the Moon, the crew described a landscape that was starkly different from the familiar near side. They immediately noticed the absence of the vast dark volcanic plains, or maria, that characterized the side of the Moon facing Earth. Instead, the far side appeared as an endless expanse of rugged, heavily cratered terrain. Astronaut William Anders famously described it as an immense, forbidding, lonely expanse. The visual impression was one of desolate grey, a surface churned and pockmarked by billions of years of cosmic impacts. This direct human observation corroborated the earlier blurry images captured by the Soviet Union's Luna 3 robotic probe in 1959. The human eye, however, could perceive depth and nuance in a way that early automated cameras could not, allowing the astronauts to convey the sheer scale and overwhelming desolation of the far side. They described seeing craters superimposed upon craters, a testament to an ancient and relentless bombardment. The experience of passing over the far side also brought a period of communication blackout. As the Apollo spacecraft moved behind the Moon, the direct line of sight with Earth was severed. For approximately 15 to 20 minutes during each orbit, the crew of Apollo 8 and all subsequent Apollo missions were completely cut off from mission control in Houston. This enforced silence was a stark reminder of their immense distance from home and the absolute isolation of their journey. Frank Borman, the commander of Apollo 8, described the feeling as being truly alone in the universe during these blackouts. During these periods, the spacecraft relied entirely on its onboard systems and the crew's diligence. All communications, telemetry and navigation updates ceased until the spacecraft re-emerged from behind the lunar disk. The precision of the orbital mechanics meant that mission control could predict the exact moment of blackout and signal reacquisition. But for the crew, it was a profound experience of self-reliance and detachment. The Apollo 8 mission was followed by Apollo 10 in May of 1969. This mission was a dress rehearsal for the lunar landing, carrying a full Apollo stack including a lunar module that separated and descended to within 50,000 feet of the lunar surface before rejoining the command module. The crew, Thomas Stafford, John Young and Eugene Cernan, also orbited the Moon extensively, providing further human observations of the far side. Their detailed reconnaissance, while primarily focused on mapping potential landing sites on the near side, inherently involved multiple passes over the far side. Their reports echoed the earlier descriptions, a uniform, heavily cratered, ancient surface. They often described the vastness of the craters, some appearing to be hundreds of miles across, and the stark contrast between the bright, sunlit crater rims and the deep, dark shadows within the craters. The lighting conditions varied with each orbit, offering different perspectives on the intricate topography of the far side. Apollo 11, the historic mission that first landed humans on the Moon in July of 1969, also provided significant human observations of the far side, particularly from the perspective of Michael Collins. As Neil Armstrong and Buzz Aldrin descended to the lunar surface in the Lunar Module Eagle, Collins remained in orbit in the Command Module Columbia. For nearly 28 hours, Collins orbited the Moon alone, completing 30 orbits. During each of these orbits, he passed over the far side. His solo journey offered a unique perspective on the isolation and scale of the lunar environment. Collins described the far side as being uniformly pockmarked and conveying a sense of profound loneliness. He noted the constant communication blackout, emphasizing the absolute isolation during those periods. His observations confirmed the uniformity and ancient nature of the far side, reinforcing the robotic findings and adding the invaluable human touch to the scientific record. Collins' detailed recollections of seeing the familiar Earth disappear and the unknown lunar terrain emerge were poignant and reflective, underscoring the deep psychological impact of such a journey. Subsequent Apollo missions, including Apollo 12, 14, 15, 16 and 17, continued to provide extensive human observations of the far side during their orbital phases. While the primary objectives of these missions shifted towards more detailed scientific exploration of specific near-side landing sites, the necessity of orbiting the Moon meant that every crew had multiple opportunities to view and describe the far side. Astronauts often had mapping cameras and other scientific instruments in the service module's Scientific Instrument Module, or SIM, bay on later flights, which collected systematic data as they flew over the far side. However, their direct visual impressions remained a crucial complement to the instrument data. The descriptions from these later Apollo crews consistently emphasized the ruggedness and ancient appearance of the far side. Astronauts like David Scott of Apollo 15, John Young of Apollo 16, and Gene Cernan of Apollo 17, all of whom flew on multiple Apollo missions and had extensive orbital experience, often noted the stark, raw nature of the far side compared to the relative geological diversity of the near side. They could visually discern areas of higher elevation and deeper depressions, providing qualitative topographic data. The sun angle played a critical role in their observations. When the sun was low on the horizon, the shadows cast by craters and mountains were long and dramatic, highlighting the topography. When the sun was high, the surface appeared flatter, but the differences in reflectivity of the lunar regolith became more apparent. The communication blackout periods during far-side passes were a recurring feature of all Apollo lunar missions. This required precise planning and adherence to strict protocols. Before entering the blackout zone, Mission Control would transmit final instructions and updates to the crew. The astronauts would then monitor their spacecraft systems independently, relying on onboard computers and their training. This period was often used for quiet reflection or for specific tasks that did not require real-time communication. The reacquisition of signal after emerging from behind the moon was always a moment of relief and a confirmation that the mission was proceeding as planned. This enforced isolation during each far-side pass became a defining characteristic of lunar orbital flight, reminding the crews of the vast distances involved and the delicate balance of technology that kept them connected to Earth. The experiences during these blackouts underscored the dependence on the Command Service module as a self-contained life support system. The astronauts' training for lunar missions included extensive simulations and geological briefings. While much of this preparation focused on the near-side landing sites, they were also educated on the then limited understanding of the far side based on early robotic probes. This knowledge allowed them to make informed observations during their orbits. They were trained to look for specific geological features, even if they were seeing them for the first time with their own eyes. Their direct reports, often given live or recorded for later debriefings, provided valuable human validation of the robotic mapping data. For example, observations on the relative density of craters or the presence or absence of certain types of terrain contributed to the overall geological picture. The human eye and brain, capable of synthesizing complex visual information in real time, provided a level of qualitative assessment that even advanced photographic equipment struggled to replicate in the early space age. The perspective of the command module pilot, the astronaut who remained in orbit while two crewmates descended to the surface, was particularly unique regarding the far side. Michael Collins on Apollo 11, Richard Gordon on Apollo 12, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ron Evans on Apollo 17 all spent considerable time alone in lunar orbit, circling the moon multiple times, often for days, observing the far side repeatedly. Their solitude enhanced the experience, making their observations even more introspective and profound. They became, for significant periods, the only humans to witness the full sweep of the far side directly. Their detailed descriptions, often published in their post-mission books and interviews, provided rich, personal insights into this alien landscape. They spoke of the eerie silence, the absence of any discernible features that suggested life or recent geological activity, and the overwhelming sense of geological time encapsulated in the ancient battered surface. Even Apollo 13, a mission that faced a catastrophic in-flight emergency, provided an inadvertent and dramatic human encounter with the far side. After an explosion in the service module crippled their spacecraft, the crew had to use the moon's gravity to swing around and return to Earth. This free return trajectory meant passing behind the moon, over the far side. For the distressed crew, James Lovell, Jack Swigert and Fred Hayes, this was a moment of immense tension. During the crucial far side pass, they were entirely cut off from mission control, unable to receive critical updates or send emergency telemetry. This blackout period, normally a routine occurrence, became a period of heightened anxiety as they silently rounded the moon, uncertain if their crippled spacecraft would survive the journey back. Their experience, though not focused on scientific observation of the far side, dramatically underscored the isolating nature of this hidden hemisphere and the critical importance of reliable communication. The cumulative human observations from all the Apollo missions greatly enhanced humanity's understanding of the far side. They provided a visual and experiential context to the robotic mapping data. While instruments could measure topography and composition with precision, the astronauts provided the qualitative feel, the human impression of what it was like to gaze upon this ancient, forbidding landscape. Their accounts consistently reinforced the scientific understanding that the far side was fundamentally different from the near side in its geological history, appearing more ancient, more heavily cratered, and lacking the extensive volcanic resurfacing seen on the Earth-facing side. These human observations confirmed the Moon's asymmetry and contributed to the scientific theories explaining this dichotomy, such as differences in crustal thickness and the impact history. The far side, once entirely unknown, slowly yielded its visual secrets to the persistent gaze of human explorers in lunar orbit, adding an invaluable dimension to our knowledge of Earth's closest celestial companion. The legacy of their direct observations continues to inform our understanding of this once mysterious lunar hemisphere. The Moon's surface is scarred by countless impact craters, a testament to its long and tumultuous history in the early solar system. These craters range in size from tiny pockmarks to enormous basins hundreds of miles across. Among these monumental features, one stands out as truly exceptional in its scale and significance: the South Pole Aitken Basin, often abbreviated as SPA. This colossal impact structure, located on the Moon's far side, is not only the largest and deepest confirmed impact basin on the Moon, but it is also one of the largest and oldest known impact features in the entire solar system. Its immense size and unique location have made it a prime target for scientific investigation by NASA and other space agencies, as it holds invaluable clues about the Moon's formation, its internal structure, and the history of early solar system bombardment. The South Pole Aitken Basin was not discovered in a single moment, but gradually revealed its immense presence through successive robotic missions. The first hints of its existence came from the blurry images transmitted by the Soviet Union's Luna 3 probe in October of 1959, which provided the initial glimpse of the Moon's far side. While these early images were of low resolution, they showed a heavily cratered terrain distinct from the near side. As NASA launched its own series of lunar orbiters in the mid-1960s, particularly the Lunar Orbiter program, more detailed photographic coverage of the far side became available. These high-resolution images allowed scientists to begin mapping and identifying the vast, subtle depression that characterized the basin. Later, images from Apollo mapping cameras during the human missions provided even better views, further confirming the basin's colossal scale. However, due to its sheer size and the low angle of the Sun at the lunar poles, its full extent and depth were not immediately obvious from photographic data alone. The basin is appropriately named for its location. It encircles the Moon's south pole and extends northward towards the relatively prominent Aitken crater, which serves as a visible landmark near its northern edge. Its shape is roughly circular or somewhat elliptical, reflecting the angle of the impactor that created it. The sheer dimensions of the South Pole Aitken Basin are staggering. It spans approximately 2,500 kilometers, or about 1,550 miles in diameter. To put this in perspective, that is roughly the distance from New York City to Dallas. Its depth is also remarkable, reaching approximately 8 to 13 kilometers, or 5 to 8 miles, from its highest rim to its deepest floor. This makes it significantly deeper than the Grand Canyon on Earth, and represents a massive excavation of the lunar crust. The age of the South Pole Aitken Basin is another critical aspect of its scientific importance. Scientists estimate that this immense impact occurred very early in the Moon's history, likely between 4.3 and 4.2 billion years ago. This places its formation within the period known as the Late Heavy Bombardment, a hypothesized era in the early solar system when a disproportionately large number of asteroids and comets collided with the inner planets and their moons. As one of the oldest and largest features on the Moon, SPA serves as a fundamental geological marker, providing a chronological anchor for understanding lunar history and the wider bombardment history of the solar system. By studying SPEM, scientists can gain insights into the conditions and events that shaped the planets and moons during their infancy. NASA's sustained exploration efforts have been paramount in unraveling the secrets of the South Pole Aitken Basin. Early missions provided photographic evidence, but more sophisticated instruments were needed for detailed characterization. In the early 1990s, the Galileo spacecraft on its way to Jupiter conducted a flyby of the Moon and provided multispectral imaging data, offering new insights into the basin's composition. Shortly thereafter, the Clementine mission, launched in 1994, provided a wealth of data, including high-resolution photographic and topographic maps of the lunar surface, and also collected multispectral information that helped define the basin's unique mineralogy. A pivotal mission for understanding SPA was NASA's Lunar Prospector, launched in 1998. Lunar Prospector carried a gamma-ray spectrometer that was crucial for mapping the elemental composition of the lunar surface. For the South Pole Aitken Basin, this instrument revealed anomalous concentrations of certain elements, particularly iron and titanium, on the basin floor. These higher concentrations were interpreted as evidence of deeper crustal or even mantle material having been excavated by the immense impact and brought closer to the surface. Lunar Prospector also provided critical gravitational field data, confirming that the basin had a distinct gravity signature, further reinforcing its massive scale and unique subsurface structure. However, the most comprehensive data on the South Pole Aitken Basin has come from NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009 and still operating. LRO has transformed our understanding of the Moon, including SPA, with its suite of advanced instruments. Its Lunar Orbiter Laser Altimeter, or LOLA, mapped the basin's topography with unprecedented precision. By bouncing laser pulses off the lunar surface and measuring the time it took for the light to return, LOLA created a highly accurate three-dimensional model of SPA, precisely defining its depth, rim structure, and the subtle contours of its floor. This allowed scientists to calculate the exact volume of material excavated by the impact, providing crucial data for models of basin formation. LRO's Diviner Lunar Radiometer experiment, another key instrument, measured temperatures across the lunar surface, providing insights into thermal properties and helping to identify the distribution of various minerals based on how they radiate heat. Combined with data from spectrometers on other missions, compositional maps of SPA became increasingly refined. These maps consistently show that the floor of SPA contains material that is rich in iron and magnesium, elements typically found in the Moon's mantle, the layer beneath the crust. This finding strongly supports the hypothesis that the SPA impact was so powerful and deep that it effectively punched through the lunar crust, excavating and exposing material from the Moon's deeper interior. This is of immense scientific interest because it offers a rare opportunity to study the Moon's mantle without having to drill kilometers into its surface. The scientific theories surrounding the formation of the South Pole Aitken Basin are fascinating. The prevailing theory suggests that the basin was formed by the impact of an enormous asteroid or comet, possibly hundreds of kilometers in diameter, traveling at incredibly high velocities. Such an impact would have unleashed an unimaginable amount of energy, far exceeding any event witnessed on Earth in recorded history. The sheer force of this collision would have instantaneously vaporized vast quantities of rock, melted more, and ejected colossal amounts of material across the lunar surface and into space. The resulting crater would have been so large that its rim would have immediately begun to collapse inwards, creating the complex multi-ring structure characteristic of such immense basins, though much of this structure has since been eroded by subsequent impacts. One of the key implications of the SPA impact is the resulting thinning of the lunar crust beneath the basin floor. Models suggest that the impact effectively removed significant portions of the original crust, leaving a thinner, warmer crustal layer at the bottom of the basin. Paradoxically, despite this crustal thinning, the South Pole Aitken Basin does not contain the extensive mare basalts, volcanic plains, that are prevalent on the Moon's near side. While some smaller, irregular mare patches exist within SPA, they are not as widespread or voluminous as those found in basins like Mare Imbrium or Mare Serenitatis. This observation has led to complex scientific debate. One theory suggests that while the crust was thinned, the timing of the impact relative to the Moon's internal thermal evolution meant that widespread volcanism did not occur in SPA. Another possibility is that the deep excavation exposed mantle material that was not conducive to forming extensive lava flows, or that the material erupted was too viscous to spread widely. The mantle excavation hypothesis is a cornerstone of SPA's scientific significance. If the impact did indeed bring mantle material to the surface, it provides a unique natural laboratory for studying the Moon's deep interior. scientists are keenly interested in confirming the presence of pristine mantle rocks, as this would provide direct insights into the Moon's composition beyond its crust. Minerals like olivine and pyroxene, which are common in Earth's mantle, would be strong indicators of exposed lunar mantle material. Remote sensing data from LRO and other orbiters has strongly suggested the presence of these materials, but direct sample analysis would be the definitive proof. Understanding the Moon's mantle is crucial for understanding its overall thermal evolution, its magnetic history, and its differentiation into distinct layers. Furthermore, the SPAE impact is thought to have played a significant role in the overall asymmetry observed between the Moon's near and far sides. The immense amount of energy released and the massive redistribution of mass caused by the impact would have profoundly influenced the Moon's gravitational field and its internal stress distribution. Some scientific models suggest that the SPAE impact could have shifted the Moon's centre of mass or altered its internal heat flow patterns, which in turn might have contributed to the differences in crustal thickness and the uneven distribution of volcanism between the two hemispheres. The thermal effects of such a colossal impact would have been immense, potentially influencing the Moon's internal temperature for millions of years, which could have affected volcanic activity and the evolution of its core. The scientific significance of the South Pole Aitken Basin is multifaceted. Firstly, it serves as an invaluable window into the early solar system. Its pristine age and immense size make it a key target for understanding the nature and intensity of the late heavy bombardment. By studying the cratering record within SPA and on its rim, scientists can refine models of early solar system dynamics and the populations of impactors that shape the inner planets. Secondly, as previously discussed, it offers unique access to the Moon's deep interior. Direct analysis of samples from SPA would be a scientific goldmine, allowing scientists to test theories about mantle composition and the Moon's differentiation. Thirdly, the basin encompasses part of the lunar South Polar region, an area of particular interest due to the confirmed presence of water ice in permanently shadowed craters. While the water ice itself is not a direct result of the SPA impact, the basin's geography means that many of these cold traps lie within its vast confines. NASA's LRO mission, with instruments like Lola, has meticulously mapped these permanently shadowed regions, confirming the existence of significant quantities of water ice. This discovery has profound implications for future human exploration, as water ice could potentially be processed into drinking water, breathable oxygen, and rocket propellant, making a sustained human presence on the Moon more feasible. Thus, the SPA basin, with its potential resources, becomes a strategic location for future lunar missions. Exploring the South Pole Aitken Basin presents significant challenges. Its location on the far side of the Moon means that any lander or rover operating within it would face constant communication challenges, requiring relay satellites in lunar orbit to transmit data back to Earth. The rugged topography, with its immense craters, steep slopes, and deep shadowed regions, makes landing and traversing difficult for robotic missions. Furthermore, the permanently shadowed regions within the basin are among the coldest places in the solar system, with temperatures plummeting to hundreds of degrees below 0 Fahrenheit. Operating robotic equipment in such extreme cold requires specialized technology and robust power systems. Despite these challenges, the scientific allure of the South Pole Aitken Basin remains incredibly strong. International efforts are increasingly focused on this region. For example, the Chinese Chang'e 4 mission successfully landed its rover, Yutu-2, within the von Karman crater, which is situated inside the Spear Basin, in January of 2019. This was the first ever soft landing on the lunar far side. While not a NASA mission, its success demonstrated the feasibility of operating within SPA and underscored the global scientific interest in this unique geological feature. Future NASA missions, both robotic and potentially human, are eyeing the South Pole Aitken Basin as a prime target for further investigation, including potential sample return missions that would bring actual pieces of SP material back to Earth for detailed laboratory analysis. Such samples would provide unprecedented insights into the Moon's formation and the early history of the solar system, further solidifying the basin's status as a scientific treasure trove. The Great Basin continues to yield its ancient secrets to the relentless pursuit of scientific knowledge. For most of human history, the Andromeda Galaxy was seen as nothing more than a faint blurry smudge in the night sky. Some people thought it was just a nebula, a small cloud of gas floating within our own Milky Way. But others imagined something much bigger, wondering if it could be an entire galaxy all on its own. When we finally learned the truth, it completely changed the way we understood the universe. Andromeda is not just another starry object in the sky. It is the largest galaxy in our local group, containing around 1 trillion stars and countless mysteries yet to be uncovered. Over billions of years, our Milky Way and Andromeda are on a slow collision course, destined to merge into a single, entirely new galaxy. What secrets does this enormous neighbour hold? Could it host planets we have not yet discovered? Could humanity ever travel into space to reach it? Before we start, drop a comment below and tell us where in the world you're watching from and what time it is there now. Now, settle in as we take you on a journey to the centre of the Andromeda Galaxy. At the dawn of the 20th century, a profound mystery lingered in the minds of astronomers, a puzzle so deep that solving it would forever change humanity's understanding of the cosmos. Among the countless stars that twinkled in the night sky, a faint blurry patch of light caught the attention of scientists. This object was known as the Andromeda Nebula. At the time, it was just one among many such smudges in the heavens, often called nebulo, a term that suggested clouds of gas floating within our own Milky Way. The central question, however, was nothing less than revolutionary. Was Andromeda merely a cloud of interstellar gas within our galaxy? Or was it something far more astonishing, an entirely separate galaxy, a distant island universe in its own right? The prevailing view in the early 1900s was that the universe was far smaller than we now understand it to be. The Milky Way, the sprawling band of stars that stretched across the sky, was thought to contain all that existed. Every star, every planet, every speck of dust and gas. In this picture, the Milky Way was everything. Any faint glow beyond it was generally assumed to be nothing more than a local cloud of gas, slowly coalescing into new stars. Andromeda, with its soft, diffuse light and elegant spiral shape, was catalogued as one of these nebulae. Its beauty and structure, however, sparked curiosity and debate. By the early 1900s, astronomers began to question the very nature of Andromeda. Some bold scientists suggested that this faint light might not be part of the Milky Way at all. Perhaps they proposed it was a vast collection of stars, a separate galaxy like our own, drifting silently through the darkness of space. This idea was nothing short of revolutionary. If true, it implied that the universe was immensely larger than anyone had dared to imagine. The Milky Way, enormous though it was, would no longer be the sole star system in existence. Instead, it would be just one among countless galaxies scattered throughout the cosmos, each containing billions of stars, possibly with their own planets and their own mysteries. One of the main arguments against the idea of Andromeda as a separate galaxy came from the esteemed astronomer Harlow Shapley. In 1917, Shapley undertook a detailed study of the Milky Way and estimated its size to be roughly 300,000 light-years across. This was an extraordinary figure by the standards of the time, almost beyond comprehension. Shapley and others who agreed with him believed that the Milky Way was so vast that there could be no need for other galaxies. All the so-called nebulae, they argued, were likely part of our own galaxy, merely clouds of gas or clusters of stars forming within it. The idea that Andromeda could lie outside the Milky Way, separated by millions of light-years, seemed impossible, almost absurd. The sheer scale required to accommodate another galaxy was difficult for anyone to imagine. Yet, not everyone agreed with Shapley. A passionate astronomer named Heber Curtis offered a strikingly different perspective. Curtis looked at the evidence in a new light and proposed that Andromeda, and several other spiral nebulae, might indeed exist far beyond the boundaries of the Milky Way. He pointed to a particularly intriguing clue, the observation of novas, or exploding stars in Andromeda. Novas briefly flare up, becoming extremely bright before fading back into obscurity. Curtis noticed that these novae appeared much dimmer than those observed within our galaxy. If these were similar events, their faintness could only be explained if Andromeda was situated at a tremendous distance, far beyond the limits of the Milky Way. Curtis also studied the structure of Andromeda itself. Unlike a simple gas cloud, Andromeda displayed a striking spiral shape, a graceful swirl of light that resembled the structure of our own Milky Way. While some nebulae within the Milky Way seemed irregular or diffuse, these spiral forms had an unmistakable organized pattern. If they were merely gas clouds, it was difficult to understand why they would take on such ordered shapes. But if they were separate galaxies, vast collections of stars each bound by gravity, then their spiral forms made perfect sense. Here was a tantalizing possibility. The night sky might be dotted with countless galaxies, each a sprawling island of stars like Andromeda itself. This debate between Shapley and Curtis reached its dramatic climax in 1920 during what would come to be known as the Great Debate, held at the Smithsonian Institution in Washington, D.C. It was a historic event, bringing two of the era's greatest minds face to face to argue in public about the very structure of the universe. Shapley, representing the one galaxy view, argued forcefully that the Milky Way's enormous size rendered the concept of other galaxies unnecessary. Curtis, on the other hand, defended the idea of a universe teeming with galaxies, asserting that Andromeda and other spiral nebulae were independent star systems, separate from our own. The debate was lively, spirited, and filled with complex arguments about observations, distances, and the limits of contemporary knowledge. Yet, in the end, no definitive winner emerged. Both men presented compelling points, and the evidence available at the time could not resolve the question. The true nature of Andromeda remained one of astronomy's greatest mysteries. Despite the lack of a clear resolution at the Great Debate, the search for answers pressed on. Astronomers continued to study Andromeda, looking for a method to measure its distance accurately. It was in 1924 that a breakthrough occurred, thanks to the tireless efforts of Edwin Hubble at the Mount Wilson Observatory in California. Using the powerful 100-inch telescope, a marvel of engineering at the time, Hubble embarked on a careful study of Andromeda, seeking definitive proof of its status. His work would forever transform the field of astronomy. Hubble's key tool was a special type of star known as a Cepheid variable. These stars are remarkable because they pulsate with a regular rhythm, growing brighter and dimmer over a predictable cycle. Earlier in the century, the astronomer Henrietta Swan Leavitt had conducted detailed studies of Cepheid variables in the Small Magellanic Cloud, a nearby galaxy. She discovered a vital relationship. The longer a Cepheid's pulsation period, the more luminous it truly is. This meant that by observing how fast a Cepheid varied in brightness, astronomers could determine its actual luminosity. Comparing this intrinsic brightness with how bright the star appeared from Earth allowed them to calculate its distance. It was a method both elegant and precise, offering a direct means of measuring the vast expanses of space. Hubble applied this technique to Andromeda and identified several Cepheid variables within the nebula. Calculating their distances, he arrived at a staggering result. Andromeda lay more than 2 million light-years from Earth. This measurement was beyond all reasonable doubt and placed Andromeda far outside the Milky Way. For the first time, astronomers had concrete proof that Andromeda was not a gas cloud within our galaxy, but a separate galaxy altogether, an island universe in its own right. Hubble's discovery shattered the long-held notion of a single galaxy universe. Suddenly, the cosmos expanded in the minds of humanity. The Milky Way, previously imagined as the entire universe, was now revealed to be just one galaxy among countless others, each containing billions of stars, possibly with their own planets, dust clouds, and cosmic phenomena. The implications of Hubble's work were profound and immediate. The concept of an island universe was no longer a speculative theory. It was a verified fact. The universe was unimaginably vast, filled with galaxies spread across distances that stretched the limits of human comprehension. As telescopes grew ever more powerful, astronomers began discovering more and more galaxies, some dwarfing the Milky Way in size, others smaller and more distant, scattered across the void in astonishing numbers. The simple night sky that had once seemed familiar and finite now appeared as a vast ocean of galaxies, each a cosmic city of stars swirling and shining across unimaginable distances. Hubble's discovery also laid the groundwork for a new era of cosmology, the scientific study of the universe as a whole. No longer could astronomers limit their investigations to the Milky Way alone. The universe itself became the laboratory, and questions about its size, structure, and origin came to the forefront. The idea of a static, limited universe gave way to the understanding that the cosmos is vast, dynamic, and filled with mysteries waiting to be explored. Observations of galaxies led to further discoveries, including the realization that the universe is expanding, a concept first hinted at by Hubble's later work in the 1920s and 1930s. The transformation of astronomical knowledge in the early 20th century serves as a powerful reminder of how humanity's understanding of the cosmos can evolve. What was once assumed to be the totality of existence, the Milky Way, was revealed to be only one part of a far larger and more intricate reality. Andromeda, once merely a faint, mysterious patch of light, became a symbol of curiosity, persistence, and the human desire to explore the unknown. The debate between Shapley and Curtis, the careful measurements of Hubble, and the insights of Henrietta Swan-Leavitt collectively illustrate the collaborative and cumulative nature of scientific discovery. Each astronomer, with careful observation and daring ideas, contributed to an understanding that reshaped our perception of the universe forever. In retrospect, the story of Andromeda reflects the broader journey of science itself. Initial observations lead to hypotheses, which then encounter debate and scrutiny. Only through rigorous measurement, careful reasoning, and innovative techniques does certainty emerge. Andromeda's revelation as a galaxy beyond the Milky Way was not merely about a single object. It was a gateway to a new cosmic perspective, a transformation in how we perceive our place in the universe. The night sky, once thought to be limited and comprehensible, became a vast and boundless frontier, each new discovery inviting deeper questions about the origins, evolution, and ultimate destiny of the cosmos. By the mid-20th century, astronomers had catalogued thousands of galaxies, each unique in shape, size, and structure. Some were grand spirals swirling like Andromeda itself. Others were elliptical, massive and rounded, while still others were irregular, lacking any clear form. The diversity of galaxies further emphasized the richness and complexity of the universe. Human beings, for the first time, could appreciate not only the vastness of space, but also the incredible variety of the objects within it. The notion that our galaxy was everything had been replaced by the understanding that it was only one of an enormous multitude, each a realm of stars and potential worlds. This expanded view of the cosmos also inspired philosophical and cultural reflection. If the Milky Way was not alone, then humanity's place in the universe might be more humble than previously believed. Yet, at the same time, the discovery of countless galaxies hinted at possibilities beyond imagination, worlds and civilizations that might exist elsewhere, separated by millions or billions of light years. The night sky became not just a backdrop for human observation, but a vast tapestry of cosmic architecture, each galaxy a thread in a universe that was far larger, older, and more complex than anyone had ever dared to dream. Even after the groundbreaking discoveries of Edwin Hubble in the early 1920s had transformed the field of astronomy, many doubts and unanswered questions continued to linger among scientists. Hubble's work had dramatically changed the way humans understood the universe, revealing that the faint, smudgy object in the night sky known as the Andromeda Nebula was not a mere cloud of gas within the Milky Way, but a separate, enormous galaxy in its own right, located far beyond the limits of our own stellar system. This revelation alone was enough to shake the foundations of astronomical thought at the time. Yet, as is often the case in science, progress did not follow a straight or simple path. Confirming that Andromeda was indeed a galaxy did not suddenly resolve all uncertainties about the universe. Instead, it opened the door to an entirely new set of mysteries and challenges, many of which puzzled astronomers for decades. One of the first and most pressing questions concerned the brightness of galaxies. If these vast assemblies of stars were actually millions of light-years away from Earth, as Hubble's measurements indicated, then their intrinsic luminosity, the amount of light they produced, must be far greater than anyone had previously imagined. For many scientists, this was a difficult concept to accept. The idea that a single galaxy, composed of billions of stars, could emit such enormous quantities of light across such mind-boggling distances seemed almost impossible. It was not merely a matter of scale, but also a matter of understanding the processes that powered stars themselves. At that time, astronomers had only a rudimentary grasp of the inner workings of stars, and the leading theories of stellar energy were still the subject of lively debate. In the early decades of the 20th century, the dominant explanation for how stars generated energy involved gravitational contraction. According to this theory, stars shone because their immense mass slowly compressed under its own weight, generating heat and light in the process. This concept could explain why stars emitted energy for a time, but it had a serious flaw. It could not account for the incredibly long lifespans of stars. If stars were powered solely by gravitational contraction, they would burn out in tens of millions of years, far shorter than the billions of years implied by observations of the universe. This problem became especially acute when applied to galaxies. Hubble's work suggested that galaxies contained billions of stars, each shining brightly. If this was true, then the known mechanisms of stellar energy production could not possibly account for the observed brightness of galaxies as a whole. Scientists needed a new understanding of the processes occurring within stars to reconcile these observations. It was not until the mid-20th century that this problem was resolved, when researchers finally confirmed that stars derived their energy from nuclear fusion. In this process, hydrogen atoms deep within a star's core fuse together to form helium, releasing vast amounts of energy in the form of light and heat. This mechanism explained both the enormous luminosity of individual stars and their ability to shine consistently for billions of years. With nuclear fusion as the energy engine of stars, astronomers could finally begin to understand how entire galaxies, composed of countless stars, could produce the staggering amounts of light that Hubble had measured. Yet, brightness was only one of many questions that remained. Another perplexing issue involved the distribution of galaxies across the universe. If the cosmos was indeed filled with countless galaxies, why did they appear to be unevenly spread across the sky? Early surveys of the heavens revealed that galaxies were not randomly scattered. Instead, they seemed to cluster in certain regions, leaving other areas relatively empty. Some astronomers wondered if this clustering was simply an illusion, caused by the limitations of the telescopes available at the time. Others suspected that these patterns were real and that galaxies were inherently arranged in groups and clusters. If this was the case, a new question arose. What force was responsible for creating these structures? Gravity seemed like the obvious answer, but astronomers in the early 20th century lacked the tools and precise measurements needed to fully study the motions of galaxies on such a grand scale. The dynamics of these cosmic assemblies remained largely mysterious. Complicating matters further were early attempts to measure the motions of galaxies. Hubble had demonstrated that in general, galaxies appeared to be moving away from Earth, a discovery that became the foundation for the idea of an expanding universe. However, exceptions to this pattern puzzled astronomers. Some galaxies showed very little redshift, suggesting that they were not receding as quickly as others. Even more strangely, Andromeda itself seemed to be approaching the Milky Way, rather than moving away. How could this be reconciled with the expanding universe model? It would later be understood that the overall expansion of space did not prevent galaxies from moving independently under the influence of their mutual gravitational pulls. In the case of Andromeda and the Milky Way, their proximity was close enough that the gravitational attraction between them overcame the general expansion of the cosmos, setting them on a slow-motion collision course that would continue for billions of years. While Hubble had confirmed the immense distance of Andromeda, the status of the many other spiral-shaped objects catalogued in the night sky remained uncertain. Were they all equally distant galaxies, or were some much closer, perhaps even part of our own Milky Way? Determining the true nature of these objects required painstaking observation and analysis. In some cases, objects that appeared to be spiral nebulae were later found to be entirely different phenomena, such as planetary nebulae or the remnants of supernovae within our galaxy. The line between galaxies and other celestial structures was often difficult to discern, highlighting the challenges astronomers faced as they sought to classify the vast and varied contents of the universe. The discovery that galaxies were enormous collections of stars also raised fundamental questions about star formation itself. How did stars form within these galaxies, and did all galaxies produce stars at the same rate? Early observations suggested that some galaxies were far more active than others. Certain galaxies contained regions that glowed brightly, indicating vigorous star formation, while others appeared more quiescent, with less noticeable stellar activity. The reasons behind these differences were not immediately clear, and astronomers needed more data to understand the processes driving star formation across different galactic environments. Beyond the mechanics of star formation, scientists also grappled with questions about the evolution of galaxies over time. Had galaxies always existed in their current forms, or did they change and develop over billions of years? The challenge in answering this question lay in the nature of light itself. Light from distant galaxies takes millions, sometimes billions of years to reach Earth, meaning that observing faraway galaxies allowed astronomers to see them as they were long ago, rather than as they exist in the present. However, the telescopes of the early 20th century were not yet powerful enough to observe the most distant galaxies, preventing scientists from studying the earlier stages of galactic formation. As a result, astronomers could only examine the galaxies that were accessible to their instruments and make informed hypotheses about the past. Even with these uncertainties, the idea that Andromeda was a galaxy gradually became widely accepted within the scientific community. The evidence in favour of this conclusion was simply too compelling to ignore. The detailed measurements of distance, the observed structure of the nebula, and the comparison with the known properties of star systems all pointed to the same conclusion. Andromeda was not a minor feature within the Milky Way, but a vast independent galaxy, comparable in size and complexity to our own. Yet, as is often the case in science, each new answer seemed to raise more questions than it resolved. The confirmation of Andromeda's galactic status marked the beginning, rather than the end, of the study of galaxies. As astronomers continued their work, the mysteries of the universe expanded even further. How exactly were galaxies distributed on the larger scales? What determined the shape and structure of a galaxy? Why did some galaxies appear to form stars at a rapid pace, while others seemed nearly dormant? And what would the study of ever more distant galaxies reveal about the history and evolution of the cosmos itself? Each of these questions required not only careful observation, but also a deep theoretical understanding, and scientists were only beginning to develop the tools necessary to explore them. The introduction of more advanced telescopes, the development of spectroscopy, and the refinement of mathematical models of gravity and motion would gradually provide the answers, but the path forward was far from straightforward. In addition, the study of galaxies forced astronomers to reconsider their understanding of time and scale. The universe was far larger than previously imagined, filled with countless stellar systems, each containing billions of stars, many with their own planets, and potentially other structures. Human concepts of space, distance, and time had to expand to accommodate this immense cosmic arena. Distances that had once seemed incomprehensible now became measurable in terms of millions or billions of light years, and the very concept of the size of the universe had to be reconsidered. The faint glimmers of distant galaxies were not just points of light in the sky. They were windows into the past, glimpses of objects as they existed millions or billions of years ago, long before the Earth itself had formed. Even today, the questions that began with Hubble's discoveries continue to inspire astronomers. Modern research into galaxy formation, dark matter, dark energy, and the large-scale structure of the universe builds directly on the foundations laid by Hubble's observations. While the tools and techniques available to astronomers have advanced tremendously since the early 20th century, the spirit of curiosity, the drive to question assumptions, and the willingness to confront uncertainty remain at the heart of the field. Hubble's confirmation of Andromeda as a galaxy was not the conclusion of a story, but the opening chapter of an ongoing exploration that continues to unfold, revealing a universe more vast, complex, and wondrous than anyone could have imagined a century ago. In the end, the study of galaxies exemplifies the true nature of scientific inquiry. Answers lead to new questions. Each discovery illuminates certain aspects of the cosmos while casting others into shadow, prompting further investigation and deeper contemplation. The realization that Andromeda was a galaxy did not close the book on astronomy. It opened an entirely new volume, one filled with mysteries that challenged human understanding and stretched the imagination. The journey from seeing Andromeda as a faint smudge in the night sky, to recognizing it as a sprawling galaxy millions of light years away, was not just a triumph of observation, but a testament to the persistence, ingenuity, and courage of scientists willing to rethink the universe and their place within it. Through the decades that followed Hubble's pioneering work, astronomers gradually began to unravel the complexities of galaxies. They learned to measure distances with increasing precision, chart the motions of stars within galaxies, and understand the processes that govern the birth and death of stars. They discovered that galaxies could collide, merge, and evolve over billions of years, forming structures of incredible variety and beauty. They realized that galaxies were not isolated entities, but were part of a vast cosmic web, influenced by gravity, dark matter, and the mysterious expansion of space itself. And yet, despite all of these advances, the universe retained its capacity to surprise, to challenge assumptions, and to inspire wonder. For countless centuries, the faint patch of light that we now know as the Andromeda Galaxy puzzled stargazers. To the naked eye, it looked no more than a small smudge against the black canvas of the night sky. Some thought it was simply a hazy cloud of gas inside our own Milky Way. Others dared to imagine that it might be something much larger, perhaps a great island of stars far beyond our cosmic neighbourhood. With the progress of telescopes and the determination of astronomers, the truth was finally revealed. That hazy blur was not a nearby cloud, but an entire galaxy of its own, a colossal star system stretching for hundreds of thousands of light-years. Today, this galaxy is known by several names: the Andromeda Galaxy, Messier 31, or simply M31. Whatever name is used, it has become one of the most studied and celebrated galaxies in the entire universe. Once astronomers moved past the great debate of whether Andromeda was a galaxy at all, their attention turned to its inner workings. They wanted to know what it was made of, how it was structured, and what secrets were hidden in its immense expanse. What they uncovered was not a simple system of stars, but a grand cosmic city teeming with billions upon billions of suns, drifting rivers of gas, mysterious halos of unseen matter, and scars left behind by violent mergers with other galaxies. The deeper they looked, the more they realized that Andromeda was not a static object, but a living, evolving system shaped by cosmic forces across billions of years. Much like our own Milky Way, Andromeda is home to stars of every age and kind. Some are fiery blue giants that live short, brilliant lives before exploding into supernovae. Others are tiny red dwarfs, dim and enduring, which have burned quietly for more than 10 billion years. This mix of the young and the ancient gives the galaxy a character that is at once dynamic and seasoned by time. In its brilliant central bulge, the crowded heart of the galaxy, ancient red stars dominate. Their warm glow is the light of suns that formed in the early days of Andromeda's life, when gas was plentiful and star formation was furious. These stars long ago used up much of the surrounding fuel, leaving behind a population that is older, steadier, and redder in colour. Yet beyond this ancient core, the story changes. Stretching outward in sweeping spiral arms are great clouds of gas and dust, thick enough to block starlight and dense enough to collapse under their own weight. In these arms, young stars are still being born. Some regions sparkle with the blue shine of massive, newly formed suns, each of them so hot and luminous that their light outshines entire clusters of older stars. To astronomers, these glowing blue regions are evidence of ongoing creation. They show that Andromeda is not a galaxy that has finished its story, but one that continues to write new chapters in the language of stars. A galaxy made only of old stars would be a silent museum of cosmic history, no longer creating new suns. A galaxy filled only with young stars would be something just beginning its journey, still in the early days of growth. But Andromeda is neither of these extremes. Instead, it is a mixture of the ancient and the newborn, a cosmic balance that reveals its long and varied past. Over billions of years, it has passed through cycles, sometimes bursting with star formation when gas is stirred or compressed, other times falling into quieter periods when little new light is born. These cycles depend on the movement of gas, the essential ingredient of stars, which drifts and flows across the galaxy like a restless ocean. The supply of this gas is the key to Andromeda's ongoing evolution. Most of it is hydrogen, the simplest and most common element in the universe. Vast clouds of hydrogen float in the spaces between the stars, sometimes thin and ghostly, sometimes gathering into thick knots of matter. When gravity pulls enough gas into one place, the pressure and temperature rise to astonishing levels. At a certain point, nuclear fusion begins and a new star is born. This process is nature's greatest alchemy, the transformation of simple hydrogen gas into blazing starlight. Often, not just one star, but entire clusters ignite from a single massive gas cloud, lighting up the spiral arms like fireworks across the dark sky. Not all of the gas within Andromeda behaves in neat harmony. Some streams of gas do not match the galaxy's overall rotation. These odd motions suggest that Andromeda has not always lived alone. Over its long history, it has swallowed smaller galaxies, pulling them apart with its powerful gravity. When a tiny companion galaxy drifts too close, Andromeda seizes it, stripping away its stars and gas and adding them to its own structure. These cosmic feasts leave behind traces, faint rivers of stars stretched across the sky, twisted trails of gas, and disrupted patterns in the spiral arms. By studying these remnants, astronomers can reconstruct Andromeda's violent past, a history of collisions and mergers that shaped it into what we see today. Yet Andromeda holds more than stars and gas. Surrounding the entire galaxy is something invisible but massive, an enormous halo of dark matter. This strange substance does not shine, reflect, or block light. No telescope can capture an image of it, yet its presence is undeniable. It reveals itself through gravity. In the early 20th century, astronomers studying galaxies noticed something puzzling. By all normal reasoning, stars at the far edges of a galaxy should move more slowly than those near the centre, much as in our solar system, where distant planets like Neptune drift slowly, while the inner worlds race quickly around the Sun. But in Andromeda, and in many other galaxies, the stars at the edges were moving just as swiftly as those close to the core. There was only one explanation. Some hidden mass must be providing the extra pull of gravity, holding the outer stars in place. The visible stars and gas were simply not enough to account for this effect, and so astronomers proposed the existence of dark matter, an invisible skeleton of mass surrounding galaxies. By carefully measuring the motion of stars and gas in Andromeda, scientists concluded that the majority of its mass is not in the shining stars or glowing gas, but in this unseen component. The familiar matter, the kind that makes up suns, planets, and people, forms only a small fraction of Andromeda's total. The rest is locked in dark matter, stretching outward in a colossal halo that extends far beyond the galaxy's visible disk. Dark matter remains one of the most profound mysteries of modern science. Decades of research have not revealed its true identity. Is it made of some unknown particle, heavier than anything we can detect in our laboratories? Is it a sign of hidden laws of gravity that we do not yet understand? Whatever the answer, it is clear that dark matter plays a vital role in shaping galaxies. Without its invisible gravity, the stars of Andromeda would drift apart like sparks in the wind. With it, they are bound together, forming a magnificent spiral that has endured for billions of years. Andromeda is not just a collection of stars and gas. It is a cosmic city with a complicated structure and a long, dramatic history. When astronomers look at it, they do not see a single simple shape, but instead a layered and living system that stretches across unimaginable distances and holds countless secrets about how galaxies are born, grow, and change with time. At the very heart of Andromeda lies a bright central bulge. This bulge is like the downtown area of a city, filled with stars packed together far more tightly than in the quieter suburbs of the galaxy. Most of these central stars are old, survivors from the early days of Andromeda, when the galaxy was still young and restless. Their light blends together into a brilliant glow, which can be seen even from Earth through a telescope. Hidden within this bulge is the most powerful object of all, Andromeda's central black hole. This is no ordinary black hole. It is what astronomers call a supermassive black hole, a monster weighing millions of times more than our own Sun. Its gravity is so strong that nothing, not even light, can escape once it falls too close. Yet Andromeda's black hole is a strangely quiet giant. Unlike the central black holes of some other galaxies, which feast on huge amounts of gas and dust and blast out fierce jets of energy, Andromeda's central black hole consumes only small amounts of matter. Because of this, it does not shine with powerful radiation or produce violent outbursts of energy. Instead, it sits in relative calm, its great power mostly hidden, though its influence over nearby stars is enormous. Moving outward from this dense core, the galaxy spreads into a thick disk filled with stars. This disk is not smooth or uniform, but is shaped into sweeping spiral arms that twist gracefully outward. To the human eye, these arms would look like bright, glowing rivers of light curving through the galaxy. But these arms are not solid bridges made of stars. Instead, they are more like travelling waves, patterns of density that move through the disk. As these waves pass through regions of gas and dust, they squeeze the material together, triggering new bursts of star formation. This is why the spiral arms often sparkle with the bluish light of young, hot stars freshly born from the clouds of gas compressed by the passing waves. These spiral arms are not fixed in place. Over time, they shift and change, pulled by the complex gravitational forces at play within Andromeda. One important influence comes from the smaller galaxies that orbit Andromeda. These tiny companions tug at the spiral arms, stretch them, and sometimes even warp them, much like the way the moon pulls on the oceans of Earth and causes tides. The result is that Andromeda's spiral arms are constantly reshaped, giving the galaxy a dynamic and living character. Andromeda is not alone in space. It is surrounded by dozens of smaller galaxies, which circle around it the way moons circle around planets. Among the most famous of these companions are two dwarf galaxies named Messier 32 and Messier 110. These smaller systems are not safe in their orbits. They are being slowly torn apart by Andromeda's immense gravity. Piece by piece, their stars and gas are pulled away, adding to Andromeda's own vast structure. Over long spans of cosmic time, some of these dwarfs will likely merge completely with Andromeda, becoming part of its ever-growing body. This process of swallowing smaller neighbours is one of the main ways galaxies increase in size. Orbiting around the central regions of Andromeda are also hundreds of globular clusters. These are tightly packed groups of stars, often containing tens of thousands or even hundreds of thousands of stars all bound together by gravity. The stars within globular clusters are usually very old, among the oldest in the entire galaxy. They are like ancient fossils, preserving the memory of Andromeda's earliest years. By studying the stars in these clusters, astronomers can piece together clues about the conditions that existed when Andromeda first began to take shape billions of years ago. In a sense, globular clusters serve as historical records written not on paper, but in starlight. Even with all of these known features, Andromeda still has surprises to offer. In recent years, astronomers have discovered something completely unexpected. A vast, thin plane of dwarf galaxies orbiting around Andromeda in a coordinated fashion. Instead of being scattered randomly in space, as current theories suggest they should be, many of Andromeda's satellite galaxies lie within a flat sheet-like structure. This discovery has puzzled scientists since computer simulations of galaxy formation predict that such satellites should be spread in all directions. Why these small galaxies move in such an organized way remains a mystery, hinting that our understanding of galaxy evolution may be missing an important piece. Another startling revelation about Andromeda's past is that it has not always grown gently by swallowing small companions. Evidence now shows that Andromeda experienced at least one enormous collision with another large galaxy in the distant past. This ancient merger shook Andromeda's structure to its core. Stars and clouds of gas were flung across vast regions of space, reshaping the galaxy's halo, the extended faint outer region that surrounds the main disk. Even today, the motions of stars in Andromeda's halo carry the signature of this long-ago impact. Remnants of the galaxy that collided with Andromeda still drift in its outer reaches, like ghosts of a cosmic battle that ended billions of years earlier. Understanding Andromeda is not just about knowing a distant galaxy. Because Andromeda is the closest large galaxy to our own Milky Way, it serves as a natural laboratory for astronomers. By studying it in detail, scientists can test their theories about how galaxies live, change, and interact with their surroundings. Andromeda provides a nearby example of many of the processes that shape galaxies throughout the universe, from the quiet hunger of supermassive black holes to the grand choreography of spiral arms and the violent drama of galactic mergers. Astronomers continue to investigate many open questions. How exactly does Andromeda's central black hole influence the stars and gas around it? What is the ultimate fate of its many satellite galaxies? How often has it collided with other large systems? Each new observation brings fresh pieces of information, yet the picture is far from complete. In the near future, new telescopes and instruments will offer even deeper views of Andromeda. Powerful observatories, both on Earth and in space, will allow astronomers to map the galaxy with greater detail than ever before. They will be able to trace the motions of individual stars, study the birthplaces of new stars hidden within clouds of dust, and perhaps even watch as Andromeda's smaller companions are slowly pulled apart. The story of Andromeda is, in truth, a story about the universe itself. It shows us that galaxies are not simple pinwheels of stars frozen in time, but rather they are vast, changing ecosystems where gravity, gas and starlight dance together over billions of years. By looking at Andromeda, humanity looks into a mirror that reflects our own Milky Way's past and hints at its future. One day, billions of years from now, Andromeda and the Milky Way will themselves merge in a titanic union, creating an even larger galaxy. Until that day arrives, Andromeda will continue to shine in the night sky, a beacon of beauty and mystery, drawing the eyes of dreamers and scientists alike. Just as a detective carefully examines every tiny piece of evidence at a crime scene, looking for fingerprints, fibers, or traces of dust to reconstruct a story, astronomers act in a similar way when they study distant galaxies. Instead of fingerprints or footprints, however, their clues come in the form of light. When astronomers look at the Andromeda galaxy, they break apart its light into different colours, much like how a prism splits sunlight into a rainbow. By studying this spread of light, they can detect the presence of different elements. Each element, whether it is hydrogen, oxygen, carbon, or iron, leaves behind a very specific pattern in the light. This pattern is like a chemical fingerprint, and it reveals what Andromeda's stars, gas clouds, and dust are made of. The chemical story written into Andromeda's light is not simple or uniform. It is a record shaped over billions of years, years filled with star births, stellar deaths, violent explosions, and the endless recycling of cosmic material. Every star that has ever lived in Andromeda has left behind traces of its life, much like generations of people leave behind architecture, tools, or writings that archaeologists study on Earth. Andromeda's chemical composition, therefore, is a living archive of its past. The first thing that astronomers notice is that the most common element in Andromeda is hydrogen. This is not surprising because hydrogen is also the most abundant element in the entire universe. It is the simplest of all elements, made from just one proton and one electron. Hydrogen was created in massive amounts in the very earliest moments after the birth of the universe, during the great event that scientists call the Big Bang, which happened about 13.5 billion years ago. Hydrogen is the raw fuel that allows stars to ignite. Whenever a star forms, it begins its life by burning hydrogen in its core, turning it into helium through a process known as nuclear fusion. Alongside hydrogen, helium is also found in large amounts in Andromeda. Like hydrogen, helium was produced in those first few minutes after the Big Bang. Together, hydrogen and helium formed the basic building blocks from which the very first stars were born. In many ways, hydrogen and helium can be thought of as the cosmic foundation stones. Without them, there would have been no stars, no galaxies, and ultimately no planets or life. But while hydrogen and helium dominate in quantity, they are not what make Andromeda chemically special. What sets this galaxy apart is the wide range of heavier elements that have gradually been created inside its stars over countless ages. Stars are the true factories of the universe. Deep within their fiery cores, nuclear fusion squeezes lighter elements together to make heavier ones. Smaller stars, like our own Sun, can forge lighter elements such as carbon, nitrogen, and oxygen. These are elements essential for life as we know it. Carbon forms the backbone of molecules in living cells, nitrogen is vital in DNA and proteins, and oxygen allows creatures like us to breathe and burn energy. More massive stars, however, are capable of going even further. In their short but dramatic lives, they fuse elements into heavier forms such as magnesium, silicon, iron, nickel, and even rarer substances like gold or uranium. When these colossal stars reach the ends of their lives, they explode as supernovae. In the fury of these explosions, even heavier elements are forged in mere seconds, then thrown out into the galaxy like glitter scattered into the wind. All these newly formed elements, whether from smaller stars gently shedding their outer layers, or massive stars exploding violently, do not remain locked inside the stars forever. They are released into the surrounding space, mixing with clouds of gas and dust. From this enriched material, new stars are born, and with them, new planets can form. Each new generation of stars therefore contains slightly more heavy elements than the one before it. Over billions of years, this cycle of birth, death, and rebirth has built up the chemical richness that we see in Andromeda today. But the distribution of these elements is not the same everywhere in the galaxy. Astronomers have discovered that the oldest stars in Andromeda's outer halo, those that formed more than 10 billion years ago, contain very few heavy elements. These ancient stars were born before many of the heavier elements even existed, back in the early days when hydrogen and helium still dominated. In contrast, the younger stars found in Andromeda's spiral arms, where new stars are still forming, are much richer in heavy elements. These regions shine with the presence of metals, which is the term astronomers use to describe all elements heavier than helium. In everyday life, we think of metals as things like iron, gold, or silver, but in astronomy the definition is broader. For scientists studying galaxies, oxygen, carbon, nitrogen, and all the rest are grouped together as metals because they are products of stellar enrichment. One of the most fascinating features of Andromeda's chemistry lies in the unusual ratios of isotopes found there. Isotopes are different versions of the same element. For example, carbon can appear as carbon-12 or carbon-13, depending on how many neutrons are in its nucleus. These subtle differences are like faint signatures left behind by particular processes. Some isotopes are created in the extreme heat and pressure of giant stars, while others are formed more slowly in small stars. By measuring the relative amounts of different isotopes of elements like oxygen or carbon, astronomers can uncover clues about what kinds of stars contributed most to Andromeda's makeup. Interestingly, the isotopic ratios in Andromeda do not always match those found in our own Milky Way. This suggests that Andromeda and the Milky Way, despite being cosmic neighbours and similar in size, have experienced different evolutionary histories. Perhaps Andromeda had a faster or slower rate of star formation at certain times. Perhaps it experienced a greater number of massive star explosions compared to the Milky Way. These differences remind us that even galaxies, like people, each have their own individual life stories, shaped by unique experiences. Another layer of complexity comes from galactic mergers. Galaxies are not isolated islands. They frequently collide and merge with one another. When this happens, a galaxy not only gains new stars, but also inherits the chemical fingerprints of the incoming system. In Andromeda's outer regions, scientists have found patches of stars and gas whose chemical makeup does not match the rest of the galaxy. These areas could be the remains of smaller galaxies that Andromeda swallowed long ago. Although the galaxies themselves have been lost, their chemical signatures live on, like ghostly memories imprinted in Andromeda's outer halo. The central region of Andromeda, its bright glowing core, tells yet another story. Measurements show that the core contains a higher concentration of iron and other heavy elements than the areas farther out. This hints that Andromeda's core went through particularly intense bursts of star formation in the past. During these times, large numbers of massive stars would have lived and died in rapid succession, exploding as supernovae and enriching the core with heavy elements. The echoes of that activity remain today, locked into the stars and gas at the heart of the galaxy. Yet even with all this richness, Andromeda still shows a few puzzling features. For example, studies suggest that it has slightly less magnesium than astronomers would expect for a galaxy of its size and age. Magnesium is typically produced in massive stars, so its lower abundance may mean that Andromeda's history of star formation was influenced by unusual conditions. Perhaps its early environment, or its past interactions with other galaxies, altered the balance of elements created within its stars. Such mysteries keep astronomers searching, piecing together the grand puzzle of Andromeda's chemical evolution. Dust, too, plays an important role in this story. Scattered throughout Andromeda are countless dust grains, each no larger than a speck of smoke. These grains are made of solid particles of carbon, silicon, oxygen, and other elements. Though tiny, dust grains are essential in the formation of stars and planets. They help cool clouds of gas, allowing gravity to pull the material together to form new stars. They also provide the raw ingredients from which planets are built. Without cosmic dust, worlds like Earth would never have come into being. What is particularly interesting is that the dust composition in Andromeda is not uniform. Some regions contain more carbon-rich grains, while others are dominated by silicate particles similar to the rocky minerals found on Earth. This variation reflects the different processes and environments across the galaxy. In regions where massive stars have lived and died, silicates may dominate, while in quieter areas, carbon grains may accumulate. Thus, even the dust tells a story about Andromeda's past. Taken together, the chemical portrait of Andromeda is like a grand tapestry woven over billions of years. Every atom of carbon, every grain of dust, every trace of gold or iron is evidence of past events. Some were formed in the quiet glow of long-lived stars. Others were born in cataclysmic explosions that shook the galaxy. Some were inherited from long-lost galaxies that Andromeda devoured. And all of it, combined, makes Andromeda not just another spiral of stars in the night sky, but a vast and dynamic system with a chemical identity as unique as a fingerprint. One of the most powerful tools that astronomers use to uncover the hidden secrets of Andromeda's chemical makeup is called spectroscopy. This technique is like giving the galaxy a detailed chemical scan, allowing scientists to read its light as if it were a story, written in the language of atoms and molecules. Every element in Andromeda, from the simplest hydrogen to heavier elements like carbon, oxygen and iron, leaves a unique imprint in the light it emits or absorbs. By carefully studying these patterns, astronomers can tell exactly which elements are present, almost like identifying the ingredients in a cosmic recipe. Using spectroscopy, scientists have discovered fascinating molecules within Andromeda, including carbon monoxide, which is commonly found in dense, cold clouds where new stars are born. These molecular clouds act like stellar nurseries, incubating the next generation of shining stars. Each time astronomers detect these molecules, they are essentially catching Andromeda in the act of creating new life in the form of stars. The presence of these clouds tells a story of ongoing transformation, showing that the galaxy is far from static. It is alive, evolving, and continually shaping its own future. As Andromeda keeps forming new stars, the composition of its gas and dust slowly changes. In particular, the galaxy's metallicity, which is the term astronomers use to describe the abundance of elements heavier than helium, gradually rises. With each generation of stars, heavier elements are produced in their cores and released into space when those stars die, enriching the galaxy for the next cycle of star formation. But this cosmic cycle cannot last forever. As Andromeda slowly consumes its supply of raw gas, the rate at which new stars are born will gradually decline. Over billions of years, the galaxy will transition into a quieter stage of life, dominated by older, long-lived stars, with fewer and fewer new stars emerging. Looking even farther into the future, astronomers predict that Andromeda will eventually collide and merge with our own Milky Way galaxy in approximately 4 billion years. When this grand cosmic encounter occurs, the two galaxies will combine their stars, gas, dust, and importantly, their chemical histories. The resulting galaxy will carry the unique chemical fingerprints of both Andromeda and the Milky Way, blending their pasts into a new, unified identity, a single galactic system that tells the story of billions of years of cosmic evolution. In this way, the chemical traces that astronomers observe today not only reveal Andromeda's present state, but also offer a glimpse into the grand, unfolding future of our local universe. The Andromeda Galaxy is a vast, luminous realm teeming with a spectacular variety of stars. From the most ordinary to the most extraordinary, Andromeda's stellar population mirrors, in many ways, what we observe in other galaxies scattered across the universe. Stars follow life cycles that have been extensively studied and mapped, and in that sense, Andromeda offers a familiar cosmic landscape. Yet, beyond the commonality of its billions of suns lies a hidden treasure trove of rare, unusual, and sometimes almost inexplicably strange stars, each with stories that stretch our understanding of the cosmos and challenge the models astronomers have painstakingly developed over centuries. Among the galaxy's most captivating and enigmatic stars are the so-called luminous blue variables, or LBVs. These celestial giants are massive stars, often tens or even hundreds of times the mass of our Sun, yet they live life on the edge of stability. Unlike the calmer stars that slowly burn through their hydrogen fuel over millions or billions of years, luminous blue variables exist in a delicate tug-of-war between gravity, which tries to pull their massive bodies inward, and the immense pressure from their radiation, which constantly pushes outward. This balance is precarious, and the result is a dramatic, unpredictable life. LBVs can swell to enormous sizes and then, without warning, shed vast amounts of their outer layers in violent stellar winds that ripple through space. Their brightness fluctuates in ways that can puzzle observers for decades, sometimes dimming and at other times shining with the intensity of hundreds of thousands of suns. One of the best-known examples in Andromeda is AE Andromedae, a star that has been carefully monitored over time as it pulsates, brightens and fades in its brief yet spectacular life. These stars occupy a fleeting chapter in the evolution of massive stars, a stage that lasts only a fraction of a star's total lifespan, but it is a stage that sets the stage for some of the most dramatic events in the universe: supernova explosions. By studying LBVs like AE Andromedae, astronomers can peer into the final unstable moments before a massive star ends its life in a cataclysmic outburst, offering insights into processes that shape the chemical makeup of galaxies and even the origin of the elements themselves. Scattered across Andromeda's elegant spiral arms is another remarkable class of stars known as Wolf-Rayet stars, named after the astronomers Charles Wolf and Georges Rayet, who first described them in the mid-19th century. These stars are exceedingly rare, and their appearance signals extreme and transformative phases of stellar life. By the time a star becomes a Wolf-Rayet, it has already shed much of its outer hydrogen layers, revealing the hotter, more energetic cores where heavier elements like helium, carbon, nitrogen, and oxygen are actively forged. The result is a star of extraordinary luminosity, radiating powerful blue-white light that can outshine entire star clusters. Yet, with brilliance comes instability. These stars are characterized by fierce, relentless stellar winds that can strip away significant portions of their mass over their brief lifetimes, which typically span only a few million years, a mere heartbeat on cosmic timescales. The presence of Wolf-Rayet stars is a cosmic marker, indicating regions where intense star formation has occurred recently, and where the cycle of stellar birth, evolution, and death continues at a breathtaking pace. Each of these stars is a herald of a future supernova destined to enrich the interstellar medium with heavy elements that will become the building blocks for new stars, planets, and potentially life itself. Among the galaxy's many peculiarities are hypervelocity stars, a phenomenon that stretches the imagination and tests our understanding of gravity. These stars move with such extraordinary speed that their trajectories defy expectations based on ordinary galactic dynamics. Some hypervelocity stars may have been part of binary systems where one star exploded in a supernova, violently propelling its companion outward at mind-boggling speeds. Others may have experienced a near miss with Andromeda's supermassive central black hole, being flung outward like cosmic cannonballs by the black hole's immense gravitational pull. These stellar sprinters are not merely curiosities, they are messengers carrying information about the forces at work deep within the galaxy. Travelling at velocities that could allow them to escape Andromeda entirely, they offer astronomers a unique way to probe the strength of gravitational interactions and to trace the hidden structure of the galaxy's dark matter halo, which exerts a subtle yet pervasive influence on the motion of stars throughout Andromeda. Venturing farther from the bustling arms of Andromeda, into the quieter outer reaches of the galaxy, astronomers encounter an entirely different type of rare star: carbon stars. These stars possess an unusually high concentration of carbon in their atmospheres, which gives them a striking reddish hue that sets them apart from the surrounding stellar population. The red glow is the result of processes deep within the star, where convection currents dredge up carbon from the interior and release it into the outer layers. This enrichment alters the star's light output, giving it a distinctive colour and making it easily identifiable to astronomers with the right instruments. Beyond their aesthetic appeal, carbon stars play a vital role in the cosmic cycle of matter. By shedding carbon-rich material into space, they enrich the interstellar medium with the raw ingredients necessary for forming new stars, planets, and even the complex molecules that are precursors to life. In this way, Carbon stars act as both custodians and distributors of the galaxy's chemical wealth, linking the death of one star to the birth of countless others. The heart of Andromeda, its bright central bulge, holds yet another treasure trove of rare stars, extremely metal-poor stars. These ancient suns formed in the galaxy's earliest epochs, when the cosmos itself was young and heavier elements were scarce. Unlike stars like our Sun, which contain a rich blend of elements forged in countless generations of previous stars, metal-poor stars are relics from a time when the universe had barely begun its chemical enrichment. Their compositions are dominated by hydrogen and helium, with only trace amounts of heavier elements. As a result, these stars offer astronomers a direct glimpse into the conditions of the early universe, serving as living fossils that reveal what Andromeda, and indeed galaxies across the cosmos, might have looked like billions of years ago. Many of these metal-poor stars are among the oldest objects in Andromeda, potentially dating back to when the galaxy itself was first taking shape, and their study helps scientists reconstruct the timeline of star formation and galactic evolution over cosmic history. In contrast to these ancient relics are stars caught in brief, transitional stages of their evolution, such as yellow supergiants. These stars occupy a rare and fleeting phase, straddling the divide between red supergiants and blue supergiants. The transition is so brief that, in astronomical terms, it is almost instantaneous, a mere few thousand years out of a life that can span millions or even tens of millions of years. This brevity makes yellow supergiants exceptionally difficult to observe, yet each discovery provides crucial insight into the life cycles of massive stars. By studying these ephemeral stars in Andromeda, astronomers can refine their models of stellar evolution, understanding more precisely how stars change in colour, size and luminosity as they move through different stages of life. The presence of yellow supergiants in Andromeda's stellar population adds another layer of richness to the galaxy's tapestry, reminding us that every star, no matter how fleeting its appearance, contributes to the ongoing story of the cosmos. Among the most mysterious and extreme objects in Andromeda are magnetars, a rare class of neutron stars with magnetic fields so powerful that they are almost beyond human comprehension. Formed from the collapsed cores of massive stars that exploded as supernovae, magnetars are incredibly dense, packing the mass of the Sun into a sphere barely 20 kilometers across. Their magnetic fields can be trillions of times stronger than Earth's, capable of distorting space around them and generating bursts of high-energy radiation that ripple across the galaxy. The detection of magnetars in Andromeda indicates that the galaxy has undergone numerous supernova events, each leaving behind remnants with extraordinary physical properties. By studying these objects, scientists can explore physics at extremes impossible to replicate in laboratories on Earth, offering a window into the behaviour of matter and energy under conditions that push the very limits of our understanding. Adding yet more complexity to Andromeda's stellar menagerie are variable white dwarfs. These small, dense remnants of dead stars often display surprising variations in brightness. Some of these fluctuations are caused by pulsations within the star itself, while others arise from interactions with surrounding material, especially if the white dwarf is part of a binary system. In such cases, the white dwarf may slowly accrete matter from its companion, leading to dramatic outbursts known as novae. During a nova, the white dwarf can brighten by thousands of times for a short period, only to gradually fade back into relative obscurity. Each of these events provides astronomers with valuable data about stellar life cycles, binary star dynamics, and the processes that govern nuclear fusion in extreme conditions. Taken together, all these rare and unusual stars paint a picture of Andromeda that is far richer and more complex than what meets the eye from Earth. They are not merely anomalies or curiosities, they are essential clues to the galaxy's history and its ongoing evolution. By observing luminous blue variables, Wolf-Rayet stars, hypervelocity stars, carbon stars, metal-poor ancient stars, yellow supergiants, magnetars, and variable white dwarfs, astronomers can piece together the processes that govern star formation, stellar death, chemical enrichment, and the dynamics of galactic structure. Each star acts as both witness and participant in the grand cosmic drama, tracing pathways that connect the galaxy's earliest moments to its potential future. Even within a galaxy as well studied as Andromeda, new discoveries continue to surprise and challenge astronomers. Instruments on the ground and in space are revealing faint stars previously hidden by dust or outshone by their neighbours. Sophisticated spectroscopic techniques allow scientists to measure the chemical fingerprints of stars, identifying subtle differences in composition that hint at unusual evolutionary histories. Observations across the electromagnetic spectrum, from radio waves to gamma rays, are uncovering violent stellar winds, explosive events, and high-energy phenomena that were once thought impossible. And with every new observation, theories are refined, models adjusted, and our understanding of the galaxy's intricate workings becomes just a little deeper. The study of Andromeda's rare stars is not merely an academic pursuit. These celestial objects play crucial roles in the galaxy's life story, driving chemical evolution, shaping interstellar environments, and influencing the formation of future generations of stars and planetary systems. Luminous blue variables shed their outer layers to enrich their surroundings with heavy elements. Wolf-Rayet stars broadcast intense radiation, and winds that sculpt the nearby interstellar medium. Hypervelocity stars trace the influence of extreme gravitational forces and reveal the hidden architecture of the galaxy. Carbon stars act as chemical gardeners, seeding space with the ingredients needed for new stars and planets. Magnetars and variable white dwarfs provide natural laboratories for extreme physics, illuminating processes that no human experiment can replicate. Even the ancient metal-poor stars tell stories of a universe in its infancy, giving astronomers direct insight into conditions billions of years ago. In many ways, these hidden luminaries are the unsung heroes of Andromeda, often overlooked in broad surveys or casual discussions of galaxies, which tend to focus on bright star clusters or the sprawling spiral arms. Yet without these unusual and rare stars, the picture of Andromeda would be incomplete. They reveal the violent, the transient, the extreme, and the ancient, all aspects of a galaxy that is alive with activity and brimming with history. Their presence reminds us that even a galaxy as close and familiar as Andromeda still holds secrets waiting to be uncovered, mysteries that stretch the imagination and challenge our understanding of the cosmos. Andromeda's rare stars, scattered across its core, spiral arms, and outer fringes, are more than scientific curiosities. They are chapters in a story that spans billions of years, a narrative of birth, transformation, and eventual death that is mirrored in galaxies across the universe. Each type of star, from the volatile luminous blue variables to the fleeting yellow supergiants, from the blazing Wolf-Rayet stars to the ancient metal-poor relics, contributes a unique verse to this cosmic epic. By studying them, astronomers not only learn about Andromeda's past and present, but also gain a window into the forces that shape all galaxies, including our own Milky Way. These stars are teachers, guides, and witnesses, showing us how matter is forged, how energy flows, and how gravity orchestrates the dance of the cosmos. As telescopes grow more powerful, as instruments more sensitive, and as computational models more sophisticated, the galaxy continues to reveal its hidden wonders. Stars once invisible become detectable. Processes once mysterious become understood. Andromeda, though studied for centuries, still harbours surprises. Each observation of a hypervelocity star, a carbon star, a magnetar, or a variable white dwarf adds a piece to the cosmic puzzle, revealing not just how stars live and die, but also how galaxies evolve, interact, and influence the broader universe. In this sense, the study of Andromeda's rare and unusual stars is a journey into the heart of cosmic understanding, a journey that stretches across space and time, inviting humanity to explore, to question, and to marvel at the extraordinary variety of life in the universe, even when that life is composed of blazing balls of gas, dense remnants of dead stars, and the most extreme manifestations of physics itself. Andromeda is not merely a collection of stars scattered aimlessly across space. It is a magnificent, sprawling cosmic city where stars do not live in isolation, but congregate in bustling communities, forming intricate networks that evolve together over millions and even billions of years. Imagine looking up at a vast landscape filled not just with single points of light, but with neighborhoods of stars, each with its own story, history, and unique dynamics. These neighborhoods, or star clusters as astronomers call them, come in many varieties, each providing a window into different stages of stellar life, galactic evolution, and the cosmic forces that shape entire galaxies. Among the most fascinating gatherings of stars within Andromeda are the globular clusters. These dense, nearly spherical assemblies of stars are among the most ancient structures to be found in any galaxy, often containing stars that were born during the universe's early epochs, mere hundreds of millions of years after the Big Bang. While the stars within our own Milky Way also form such clusters, Andromeda surpasses the Milky Way by a wide margin in this regard. Astronomers estimate that there are more than 500 globular clusters orbiting Andromeda, creating a stellar halo that encircles the galaxy like a vast, glittering necklace. Each of these clusters is a time capsule, preserving the conditions of a universe that existed billions of years ago. However, not all globular clusters in Andromeda fit neatly into expectations. While many are composed of the very oldest stars, astronomers have discovered some clusters that seem surprisingly youthful. These younger stars challenge conventional models of cluster formation, suggesting that star birth can sometimes occur in ways previously thought impossible for such tightly bound systems. Even more intriguing, certain clusters display unusual motions, moving along trajectories that hint they might not have originally belonged to Andromeda at all. The evidence suggests that these clusters were likely captured from smaller galaxies that collided with Andromeda in the distant past, adding their own stars to the galaxy's expanding population. In this way, Andromeda's globular clusters are not just relics of ancient times, but also records of cosmic mergers and encounters, tracing the galaxy's tumultuous history through their very orbits and compositions. Beyond the classical globular clusters, Andromeda hosts an extraordinary variety of extended clusters. Unlike their densely packed cousins, these clusters are looser, with stars spread more thinly across space, yet still gravitationally bound into coherent structures. Extended clusters occupy a curious middle ground between traditional star clusters and diminutive galaxies. Their lower densities and less compact forms suggest that they could represent transitional stages in galactic evolution, possibly providing clues about how small galaxies are gradually absorbed and reshaped within larger ones. These clusters demonstrate the fluidity of cosmic structures, blurring the line between what astronomers define as a star cluster and what is considered a small galaxy. Adding to the mystery, Andromeda is home to faint, fuzzy clusters, a particularly enigmatic type of star group. These were first discovered in the galaxy's more distant outer regions, and they defy simple classification. While they share some characteristics with globular clusters such as containing old stars, they are far more diffuse and loosely organized. This loose structure makes them fragile in the face of Andromeda's gravitational forces, raising questions about how they have survived for billions of years without being torn apart. Some scientists speculate that these faint fuzzy clusters may be the lingering remnants of smaller galaxies that merged with Andromeda in the distant past, gradually dispersing into their current delicate forms. These clusters act as ghostly witnesses to ancient galactic collisions, silently preserving evidence of Andromeda's dynamic history. Yet the story of Andromeda's star clusters does not end with the old and mysterious. The galaxy also contains surprisingly young and massive clusters, brimming with bright hot stars that have formed only a few million years ago, a blink of an eye in cosmic terms. What makes these young clusters especially intriguing is their location. Many are found in regions where astronomers had assumed star formation had long since ceased, far from Andromeda's primary stellar nurseries. Their presence suggests that new stars can still emerge under unusual conditions, perhaps triggered by tidal forces from neighbouring satellite galaxies or past galactic collisions. These young clusters offer a living laboratory for understanding how star formation can continue even in the more quiet and settled regions of a galaxy, defying previous assumptions about where new stars are likely to be born. The chemical composition of Andromeda's star clusters adds yet another layer of intrigue. Not all clusters share the same chemical signature as the galaxy's broader population. Some contain stars with peculiar ratios of metals, astronomical metals referring to elements heavier than hydrogen and helium. A few clusters even display compositions that resemble those found in smaller dwarf galaxies rather than a grand spiral galaxy like Andromeda. These chemical anomalies are like fingerprints, revealing past events in which Andromeda absorbed smaller galaxies, incorporating their stars and clusters into its own growing structure. By studying the chemical makeup of these clusters, astronomers can reconstruct a timeline of mergers and acquisitions, tracing back billions of years to uncover the processes that have shaped the galaxy we see today. The spatial distribution of Andromeda's star clusters provides further clues about the galaxy's past. Some clusters are located in places where gravitational forces should have disrupted them long ago, yet they persist, hinting at unusual formation histories or dynamic interactions that allowed them to survive. Other clusters are found arranged in streams or arcs, suggestive of remnants from previous galactic mergers. These structures imply that Andromeda's halo, the vast spherical region surrounding the galaxy, is still being sculpted by the gravitational influence of smaller galaxies and the relics of past collisions. Patterns in the positions of clusters are therefore not random, but hold a record of Andromeda's interactions and ongoing evolution, painting a picture of a galaxy that is constantly growing, reshaping, and recycling its stellar populations. Even within this already diverse population, some of Andromeda's star clusters remain difficult to classify. Certain clusters contain extraordinarily massive stars that should not have survived for billions of years, or mixtures of stars that seem to contradict expected ages and evolutionary paths. These anomalies have led some astronomers to propose that such clusters may be temporary, held together only loosely by gravity, and destined to eventually dissolve into the general stellar background of Andromeda. These transient clusters offer a glimpse into the delicate balance of forces that govern star cluster survival and the intricate dance of stars within a galaxy. Technological advancements in telescope design have further expanded our view of Andromeda's star clusters, revealing populations previously hidden from view. Dense regions near the galaxy's core, once obscured by dust and the overwhelming glare of nearby stars, now reveal clusters that may hold crucial information about the galaxy's central supermassive black hole. Interactions between these clusters and the black hole's intense gravitational field could influence both the structure of the clusters and the dynamics of stars in the galaxy's heart. Similarly, discoveries of clusters at extreme distances from the galaxy's main body challenge astronomers to reconsider the full extent of Andromeda's gravitational influence. These far-flung clusters are tantalizing clues about how galaxies interact with their surrounding intergalactic environment and the invisible forces that bind vast cosmic structures together. The incredible diversity of star clusters in Andromeda highlights the galaxy's complex and dynamic nature. Each cluster, from the densely packed ancient globular clusters to the loose and enigmatic faint fuzzy clusters, tells a story of formation, survival, and sometimes even cosmic upheaval. The clusters act as living records, preserving the history of Andromeda's interactions with neighbouring galaxies, the births and deaths of stars, and the ongoing gravitational forces that shape its structure. By studying these stellar communities, astronomers gain insight not only into the life cycle of stars, but also into the processes that govern galaxy formation and evolution on a cosmic scale. Moreover, the star clusters of Andromeda reveal the interplay between time and gravity. Globular clusters demonstrate how stars born billions of years ago can remain bound together despite the galaxy's powerful gravitational forces. Extended clusters and faint fuzzy clusters reveal the delicate balance required for stars to maintain coherence over long periods, showing how minor perturbations from neighbouring galaxies or internal gravitational shifts can gradually reshape or even dissolve these formations. Young massive clusters, on the other hand, illustrate the ongoing dynamism of the galaxy, highlighting regions where the cosmic environment still encourages star formation, even in seemingly quiescent areas. Some clusters also act as markers of past cataclysmic events. Streams of stars stretching across the galaxy, faint arcs, and unusual chemical signatures all point to mergers that have left lasting imprints on Andromeda's structure. These observations suggest that Andromeda's halo is far from static. It is a living, evolving region where the remnants of smaller galaxies continue to mix and interact with the larger system. The very motions and arrangements of star clusters carry encoded information about the gravitational encounters, collisions and absorptions that have shaped the galaxy over billions of years. Even the outliers, the clusters that defy easy classification or appear to contain unexpected stellar compositions, offer critical clues about galactic evolution. Some may represent fleeting structures, temporary gatherings of stars that eventually disperse. Others may have formed under unusual circumstances, influenced by tidal forces or past collisions that created pockets of intense star formation far from the galaxy's core. Each anomaly challenges astronomers to refine their understanding of how stars and galaxies evolve, demonstrating that the universe is far more complex and varied than any simple model can fully capture. The study of Andromeda's star clusters is not merely an exercise in cataloguing cosmic curiosities. Each discovery adds to a broader understanding of how galaxies form, evolve, and interact with their environments. Clusters provide insight into processes that occur on timescales spanning billions of years, revealing both the stability and fragility of stellar communities. They illustrate the interplay between formation, gravitational dynamics, chemical evolution, and galactic mergers. By carefully examining these structures, astronomers can reconstruct Andromeda's history, piece by piece, unraveling a narrative that spans much of the universe's lifetime. In the grand tapestry of the cosmos, Andromeda stands as both a laboratory and a historical archive. Its star clusters are chapters in an ever-unfolding story, recording the births, lives, and deaths of stars, the accretion of smaller galaxies, and the ongoing reshaping of cosmic structures. From the oldest, densest globular clusters to the youngest, brightest massive clusters, Andromeda showcases the astonishing variety and complexity of stellar assemblies. Each cluster offers a different perspective, a unique lens through which to understand the forces that govern galaxies and the universe as a whole. At the very heart of the Andromeda Galaxy, hidden deep within its brilliant core, lies one of the most mysterious and powerful objects in the cosmos, a supermassive black hole. This extraordinary entity is not just another feature of the galaxy. It is a force that shapes the very nature of everything around it, influencing the motion of countless stars, bending the paths of light itself, and consuming any matter that ventures too close to its overwhelming gravity. For decades, scientists have suspected that most large galaxies, especially those as majestic and sprawling as Andromeda, contain such colossal black holes at their centres, but studying them in detail remains a challenge. Yet, observations of Andromeda have revealed the immense scale of its central black hole, named M31 star, which is estimated to weigh approximately 140 million times the mass of our Sun. To put this into perspective, this makes it far more massive than the supermassive black hole at the centre of our own Milky Way galaxy, known as Sagittarius A star, which, while enormous, is dwarfed in comparison by M31 star. The presence of such a staggering object at Andromeda's core raises profound questions for astronomers. How did a single black hole grow to such immense proportions? How did it come to dominate the gravitational landscape of one of our closest galactic neighbours? Some of the most widely considered theories suggest that Andromeda did not grow in isolation. Over the course of billions of years, it likely absorbed smaller galaxies, each bringing with it its own black hole. Through a series of cosmic mergers, these smaller black holes may have combined, eventually forming the supermassive black hole we observe today. Each merger would have released vast amounts of energy, stirring the galactic environment and altering the orbits of stars and gas clouds within the galaxy. Surrounding M31 star is another striking feature, a dense, compact cluster of stars. Unlike the relatively diffuse arrangements of stars in some galactic cores, this cluster is tightly packed and moves in ways that are extraordinary even by galactic standards. The stars within this cluster orbit at tremendous speeds, whipped around by the black hole's immense gravitational pull. By carefully observing the paths and velocities of these stars, astronomers were able to confirm the existence of M31 star itself. No other object or combination of objects could explain the extreme movements observed in this central cluster. In this way, the stars serve as tracers, revealing the hidden presence of an object that cannot be seen directly because it swallows light along with matter. Despite its enormous mass, Andromeda's central black hole does not currently appear to be in a phase of consuming large amounts of matter. In many galaxies, supermassive black holes are surrounded by what astronomers call an active galactic nucleus, or AGN, in which gas, dust, and sometimes entire clouds of matter spiral inward, heating up as they fall and emitting powerful radiation that can be detected across vast distances. But M31 star is relatively quiet. It emits only small amounts of X-rays and radio waves, and no significant outbursts of energy have been observed. Scientists believe that this calm state may only be temporary. In the past, the black hole may have been far more active, feeding on surrounding gas and dust, releasing energy that could have influenced the evolution of Andromeda's core. Likewise, future encounters with clouds of gas, clusters of stars, or even entire smaller galaxies could awaken M31 star once more, transforming it into a more active, luminous, and energetic presence that could profoundly reshape the galaxy's central region. Yet, the supermassive black hole at the core is not the only kind of black hole that may inhabit Andromeda. Astronomers suspect that smaller intermediate mass black holes are scattered throughout the galaxy, hidden within its spiral arms and clusters of stars. These intermediate black holes, with masses ranging from a few hundred to several thousand times the mass of the Sun, likely formed in one of two ways, either from the collapse of particularly massive stars at the ends of their lives, or through the gradual merging of smaller black holes over cosmic time. While supermassive black holes dominate the centers of galaxies, these intermediate mass black holes are far more elusive, and their detection requires highly sensitive instruments and careful observation. They may lurk at the hearts of dense star clusters or orbit within the broader galactic disk, silently influencing the stars around them with their gravity. There is growing evidence that some of Andromeda's globular clusters, spherical groupings of stars bound tightly together, may harbour black holes at their cores. In these environments, a single black hole, or even multiple black holes, could subtly shape the motions of surrounding stars. If confirmed, these intermediate black holes could serve as vital clues to understanding the growth of supermassive black holes. Repeated mergers of smaller black holes over millions or billions of years might gradually produce larger black holes, ultimately contributing to the formation of objects as immense as M31 star. In this way, the galaxy may be home to a dynamic ecosystem of black holes, from the relatively small to the unimaginably vast, all interacting in complex gravitational dances. Some black holes are not tied to a fixed location, but instead wander throughout the galaxy. These rogue black holes could be remnants of smaller galaxies that Andromeda absorbed in the distant past, flung from their original positions by gravitational forces during violent collisions. Others may have been ejected from dense clusters following encounters with other massive objects. Despite being invisible in the traditional sense, they emit no light of their own. These wandering black holes still exert influence on the galaxy around them. Their gravity can disrupt the orbits of nearby stars, interfere with the formation of planetary systems, and even perturb the paths of entire star clusters. In this sense, Andromeda may be a living laboratory of hidden, invisible forces, with countless black holes shaping its structure from the shadows. Detecting these black holes is challenging. They only reveal themselves indirectly, through their gravitational effects. Sometimes, a black hole passing in front of a distant star will bend and magnify the light of that star, an effect known as gravitational lensing. Observing such events allows astronomers to infer the presence and mass of these unseen objects, providing rare glimpses of their otherwise invisible existence. Advances in technology, particularly in gravitational wave detection, offer new opportunities to uncover these hidden black holes. When black holes merge, they send ripples through the very fabric of space and time, gravitational waves that can be measured by highly sensitive instruments on Earth. By capturing these signals, scientists hope to map Andromeda's population of hidden black holes, uncovering their locations, masses, and interactions. The role of black holes in Andromeda's evolution is far from trivial. Even though they cannot be seen directly, their presence has shaped the galaxy over billions of years. The supermassive black hole at the center dictates the motion of stars in the inner core, while intermediate and wandering black holes subtly influence the orbits of stars and clusters farther out. In some cases, black holes may trigger the formation of new stars by compressing gas clouds with their gravitational pull, while in others, they may prevent star formation by scattering gas away. This dual influence highlights the complex role black holes play in shaping the life cycle of galaxies. Studying Andromeda's black holes also provides a mirror for understanding our own galaxy. Sagittarius A star, the Milky Way's central black hole, shares many similarities with M31 star, but is less massive and relatively quieter. Comparing the two allows astronomers to explore why some black holes grow to such immense sizes, while others remain more modest, and why certain black holes enter periods of activity while others stay dormant. By examining these cosmic cousins, scientists can begin to unravel the broader story of galaxy formation and evolution across the universe. The central black hole, M31 star, also reveals the violent history of Andromeda itself. Theories suggest that billions of years ago Andromeda collided with and absorbed smaller galaxies, each interaction stirring the stars, gas and dust within the galaxy and contributing to the growth of the supermassive black hole. The compact cluster of stars surrounding the black hole may contain remnants of these ancient mergers, stellar populations that were dragged toward the centre by the black hole's gravity. Every orbit of a star within this cluster, every bend in the light passing near the black hole, tells a story of cosmic upheaval, revealing how Andromeda came to be the majestic spiral galaxy we see today. Even today, the story of Andromeda's black holes is far from complete. Future collisions with other galaxies, interactions with dense clouds of gas, and the potential discovery of additional intermediate and wandering black holes may transform the galaxy once more. Astronomers continue to watch, study, and simulate the motions of stars and gas, gradually uncovering the hidden forces that shape one of the universe's closest neighbours. In doing so, they are not only learning about Andromeda itself, but also gaining deeper insight into the nature of black holes, the growth of galaxies, and the cosmic interplay of matter and gravity over billions of years. Andromeda, therefore, is not simply a collection of stars arranged in a spiral pattern. It is a living, dynamic system with supermassive, intermediate, and wandering black holes serving as invisible architects, guiding the formation and evolution of stars and clusters, shaping the flow of gas and dust, and influencing the galaxy's future. As our technology improves and new telescopes and detectors come online, astronomers are poised to uncover even more about these enigmatic objects. Every observation adds a piece to the puzzle, helping us understand how black holes grow, how they interact, and how they exert their silent but powerful influence on the grand cosmic structures we observe today. Without dark matter, the Andromeda Galaxy, along with our own Milky Way and countless other galaxies scattered across the cosmos, would not exist in the forms we observe today. The universe as we know it would look radically different. Stars would not have gathered into the vast spiral arms that decorate galaxies, planets would be far less likely to orbit in stable paths, and the intricate cosmic dance that structures galaxies would be disrupted. Dark matter, though invisible and mysterious, serves as the hidden scaffolding that allows galaxies to take shape, grow, and survive across billions of years. It is the unseen glue, the silent architect, whose gravitational influence holds the luminous matter, the stars, planets, gas clouds, and dust together. One of the earliest hints that Andromeda, also known as Messier 31, is dominated by dark matter came from careful observations of how the galaxy rotates. When astronomers measured the speeds of stars and gas in Andromeda, they found something unexpected. According to classical physics, if Andromeda consisted only of the stars, gas and dust that we can see, the outer regions of the galaxy should rotate much more slowly than the inner parts. Imagine a merry-go-round where the horses near the centre spin rapidly, while those on the edge barely move. That is what scientists would expect if only visible matter were present. Yet, in Andromeda, stars at the far edges were moving astonishingly fast, as if being tugged by a gravitational force far stronger than could be accounted for by the stars and gas alone. The most straightforward explanation for this unusual rotation is that Andromeda is enveloped by an enormous halo of invisible material. This halo stretches far beyond the glowing spiral arms, visible in telescopes, and contains far more mass than all the stars, planets, and clouds of gas combined. The gravitational pull of this unseen substance is so strong that it keeps the galaxy intact, preventing it from flying apart despite the rapid motion of its outer stars. Scientists have estimated that the total mass of dark matter in Andromeda likely surpasses the mass of all the luminous matter by several times. Without it, the galaxy's stars and gas clouds would not have enough combined gravity to remain bound together, and Andromeda as we know it simply would not exist. Dark matter in Andromeda is not spread evenly like a smooth fog. Instead, its distribution appears to be uneven, forming regions of varying density throughout the halo. Some parts of the halo contain denser concentrations, while other regions are more diffuse. Astronomers have begun to map this elusive material through a process called gravitational lensing. This method relies on observing the way light bends as it travels through the gravitational field created by massive objects. When light from distant stars or galaxies passes through Andromeda's halo, it curves ever so slightly, as though the invisible mass is tugging on it. By carefully measuring these distortions, scientists can reconstruct a map of dark matter within Andromeda, revealing its clumpy and irregular structure. The clumps of dark matter in Andromeda may have been shaped by numerous factors, some likely formed through interactions with smaller satellite galaxies orbiting Andromeda. As these dwarf galaxies move through the halo, their gravitational influence could have pulled and distorted patches of dark matter, creating a pattern of denser and lighter regions. Additionally, the internal forces within Andromeda itself, the tug of its stars, the pull of gas clouds, and the motions of spiral arms, may have moulded the dark matter over billions of years. The result is a halo that is far from uniform, a dynamic and evolving structure invisible to the human eye yet profoundly shaping the galaxy. Dark matter does more than shape Andromeda internally. It also affects the galaxy's relationship with its cosmic neighbours. Andromeda is a major member of the Local Group, a collection of galaxies that includes the Milky Way, the Triangulum Galaxy, and dozens of smaller satellite galaxies. The gravitational influence of dark matter extends far beyond Andromeda's luminous boundary, reaching into intergalactic space and subtly pulling on nearby galaxies. Some dwarf galaxies, orbiting quietly around Andromeda, are held in place by the gravity of this dark halo, preventing them from drifting away into the vast emptiness of space. Others are slowly being drawn in, gradually spiralling toward the larger galaxy, inexorably attracted by the hidden mass that dominates the halo. One of the greatest mysteries surrounding dark matter in Andromeda lies in the distant future, when Andromeda and the Milky Way are expected to collide in roughly 4 billion years. The collision of two such massive galaxies promises to be a cosmic spectacle. The visible stars and clouds of gas in both galaxies will interact violently, producing shock waves, triggering the formation of new stars and reconfiguring the shapes of the galaxies. Yet the dark matter will behave differently. Unlike the luminous material, which can collide, compress, and spark new processes, dark matter does not interact electromagnetically. It passes through itself and ordinary matter almost entirely unhindered. During the galactic collision, the dark matter halos of Andromeda and the Milky Way will interpenetrate, their massive gravitational fields tugging on the stars and gas and helping to shape the final structure of the merged galaxy. The behaviour of dark matter during such a collision holds vital clues about its fundamental nature. Many scientific theories propose that dark matter is composed of weakly interacting particles. If this is the case, its post-collision distribution could reveal the particle properties of dark matter, such as mass, velocity, or how these particles respond to gravity. On the other hand, if dark matter does interact even slightly with itself, astronomers may observe unexpected patterns in how the merged halos settle after the collision. Studying these outcomes could help distinguish between competing models and bring humanity closer to understanding one of the universe's deepest mysteries. Another profound question about dark matter concerns its origin. Did it form alongside the first stars and galaxies, or did it predate them, seeding the universe with invisible scaffolding upon which luminous matter later gathered? Many researchers believe that dark matter was created in the earliest moments of the universe, shortly after the Big Bang, roughly 13,800,000,000 years ago. In these earliest epochs, dark matter particles may have spread throughout space, establishing the gravitational wells into which ordinary matter would eventually fall. These invisible wells would act as the foundations for the first galaxies, including Andromeda, long before any stars had ignited their nuclear furnaces. Alternative theories suggest that dark matter could be linked to forces or particles that remain entirely unknown. While the standard model of particle physics accounts for ordinary matter, it cannot explain dark matter. Its existence points to phenomena beyond our current understanding, possibly indicating a hidden sector of physics with its own particles and interactions. As a result, mapping the dark matter in Andromeda is more than a study of one galaxy. It is an exploration into the very laws that govern the cosmos. By observing how stars, gas, and smaller galaxies respond to the gravitational pull of dark matter, astronomers hope to infer its properties and, perhaps, uncover the underlying particles responsible for its existence. In addition to its gravitational role, dark matter indirectly shapes the life cycle of stars and the evolution of galaxies. By providing the majority of the galaxy's mass, it stabilizes the galaxy's rotation, maintaining the delicate balance that allows spiral arms to persist over billions of years. Without this stability, spiral arms could unravel, star formation could slow or become chaotic, and the galaxy might take on a more amorphous, irregular shape. The clumpy nature of dark matter could also influence star formation locally. Denser regions of dark matter may slightly enhance the density of gas clouds, encouraging the collapse of these clouds and the birth of new stars. While invisible, dark matter's presence permeates every facet of galactic evolution, subtly guiding processes that might otherwise seem random. The ongoing study of Andromeda's dark matter is aided by several sophisticated techniques. Gravitational lensing remains one of the most powerful tools, allowing astronomers to detect the bending of light caused by invisible mass. Additionally, scientists track the velocities of stars and satellite galaxies, using their motions to infer the distribution and total mass of the halo. Computer simulations play an essential role as well. By modelling Andromeda with different dark matter scenarios, researchers can test how various distributions, particle properties, and interactions affect the galaxy's structure and evolution. Comparing these models to actual observations helps scientists narrow down the possibilities and refine their understanding of dark matter's role. Dark matter's influence extends even further, shaping interactions within the local group. The gravitational pull of Andromeda's halo affects not only its immediate satellite galaxies, but also the larger dynamics of the group. For example, the Milky Way is gradually moving toward Andromeda, and the two galaxies will eventually merge. The unseen mass of both galaxies affects their trajectories, velocities, and the timing of the collision. Similarly, smaller galaxies within the local group are constantly influenced by the gravitational interplay of dark matter, sometimes being captured into orbit around larger galaxies or deflected on new paths through intergalactic space. Despite decades of study, dark matter remains one of the most tantalizing mysteries in astrophysics. Its presence is inferred through its gravitational effects, yet it eludes direct detection. Experiments on Earth have yet to identify dark matter particles, and even their fundamental properties, mass, composition, and interaction type, remain largely unknown. Yet its influence is undeniable. In Andromeda, dark matter is the invisible architect of the galaxy's shape, the hidden hand governing its rotation, and the unseen force orchestrating its interactions with neighbouring galaxies. Without it, Andromeda would be a mere scattering of stars, unable to form the vast, spiralling masterpiece we observe across the cosmic void. Ultimately, the study of dark matter in Andromeda is more than an exploration of a single galaxy. It is a journey into the hidden structure of the universe itself. By observing how this invisible substance shapes stars, gas, and satellite galaxies, scientists hope to piece together a more complete picture of cosmic evolution. Future missions and observations may reveal whether dark matter formed in the universe's earliest moments, or whether it is connected to forces and particles yet undiscovered. Perhaps, through detailed mapping of Andromeda's halo and careful study of its interactions, humanity will one day lift the veil on this mysterious component of the cosmos. Dark matter, though unseen, is essential to the existence of Andromeda and every galaxy like it. It binds stars and gas together, guides galactic rotation, influences interactions with neighbouring galaxies, and plays a crucial role in shaping the universe over billions of years. The quest to understand dark matter in Andromeda is not merely about mapping an invisible halo. It is about uncovering the hidden forces that structure reality, probing the deep origins of galaxies, and seeking answers to questions that stretch back to the dawn of time itself. In Andromeda's graceful spiral arms and mysterious halo, we glimpse a universe shaped as much by what we cannot see as by what we can. Mapping the galaxy of Andromeda is no simple task. Even though it is the closest large galaxy to our own Milky Way, it presents astronomers with a challenge of immense proportions because of its enormous size. Andromeda, often called M31 in the catalogue of galaxies, stretches across a vast expanse of space, spanning roughly 220,000 light-years in diameter. To put this into perspective, the Milky Way itself is about 150,000 light-years across, meaning that Andromeda is noticeably larger. Observing such a massive structure in its entirety is not as straightforward as pointing a telescope and capturing a single photograph. The galaxy simply does not fit neatly within the field of view of most telescopes. Even the most powerful instruments, whether on Earth or orbiting high above it, can only capture small sections of the galaxy at a time. As a result, astronomers must take hundreds, sometimes thousands, of individual images and carefully stitch them together to form a complete picture. This meticulous process is not instantaneous. It requires years of careful observation, data processing, and precision alignment, as each piece of the puzzle must match perfectly with its neighbours. One of the most remarkable achievements in this endeavour came from the Hubble Space Telescope, which has provided some of the most detailed views of Andromeda ever recorded. Hubble is capable of capturing incredibly sharp images, far clearer than what is possible with ground-based telescopes due to the absence of Earth's atmosphere. To map Andromeda, scientists programmed Hubble to take thousands of separate exposures, each covering a small portion of the galaxy. These exposures were then combined into an enormous mosaic, revealing millions upon millions of individual stars scattered across Andromeda's spiraling arms and central bulge. The resulting image is not just beautiful, it is a treasure trove of scientific information. Every point of light in the mosaic represents a star, a stellar cluster, or in some cases a distant background galaxy. The level of detail allows astronomers to study the properties of individual stars, investigate their life cycles, and observe how they are distributed across the galaxy. However, mapping Andromeda involves far more than simply taking pictures. Photographs alone cannot reveal the full story of this complex galaxy. To truly understand Andromeda, astronomers must also measure distances, analyze motions, and determine the chemical makeup of its stars, gas, and dust. One of the most powerful tools for this type of study is spectroscopy. Spectroscopy involves splitting the light from a star or gas cloud into its component colours, or wavelengths, much like a prism creates a rainbow from sunlight. By examining the resulting spectrum, scientists can identify the presence of specific chemical elements, estimate the temperature of stars, and even determine how fast gas and stars are moving toward or away from Earth. In other words, spectroscopy allows astronomers to read the fingerprints of celestial objects. It reveals the composition of Andromeda's regions, showing where the galaxy contains clouds rich in hydrogen, carbon, oxygen, or more exotic elements forged in the hearts of previous generations of stars. These chemical clues also tell a story about the galaxy's history, where stars have formed, where they have died, and how material has been recycled to give birth to new generations of stars. Motion mapping is another crucial component of understanding Andromeda. The galaxy is not static. It is a dynamic, living system, constantly rotating and shifting under the influence of its own gravity, as well as that of neighbouring galaxies. The stars in Andromeda's spiral arms revolve around its central bulge at varying speeds. Some regions, particularly near the core, spin faster, while outer regions move more slowly. To track these motions, astronomers rely on a phenomenon known as the Doppler effect. This effect, familiar to anyone who has noticed the changing pitch of a passing siren, occurs when the wavelength of a light shifts depending on whether an object is moving toward or away from the observer. Light from stars moving toward Earth is slightly compressed, appearing bluer, while light from stars moving away stretches out, appearing redder. By measuring these subtle shifts across countless stars and gas clouds, scientists can create a detailed rotational map of Andromeda. Such maps not only show how the galaxy spins, but they also reveal gravitational influences, interactions with satellite galaxies, and evidence of past galactic collisions. While motion and composition provide critical information, the visibility of Andromeda is further complicated by interstellar dust. Dust particles are tiny, but they scatter and absorb light, hiding significant portions of the galaxy when observed in visible wavelengths. Some of Andromeda's densest regions are almost entirely obscured to ordinary optical telescopes, leaving gaps in our understanding. To peer through these cosmic veils, astronomers use infrared telescopes, which detect longer wavelengths of light that can pass through dust clouds. The Spitzer Space Telescope, for instance, mapped Andromeda in infrared light, revealing dust-rich regions previously hidden from view. These observations illuminate where new stars are forming, as dust clouds often harbour the raw material for stellar birth. In these dense cocoons, gas collapses under gravity to ignite nuclear fusion, creating newborn stars that may eventually light up the galaxy. Andromeda's composition extends beyond stars and dust to vast reservoirs of hydrogen gas. Hydrogen is the most abundant element in the universe, and it emits a specific wavelength of radio waves that can be detected with radio telescopes. This emission allows astronomers to map the distribution of gas even in regions where visible light is completely blocked. By charting the hydrogen clouds, scientists gain insight into the galaxy's future potential for star formation. Dense concentrations of gas indicate where new stars are likely to emerge, while more diffuse areas suggest regions that may soon be depleted of material. These gas maps also reveal the galaxy's structure on a grand scale, tracing spiral arms and the extended outer disk with remarkable precision. Advances in computational modelling have revolutionised the way Andromeda is studied. Observations alone, while invaluable, cannot always capture the full complexity of a galaxy with hundreds of billions of stars. Astronomers now use computer simulations to recreate Andromeda in virtual space, incorporating known properties such as the distribution of stars, the influence of dark matter, and the gravitational interactions with other galaxies. These simulations allow scientists to test different scenarios for how Andromeda formed and evolved. By comparing the simulated galaxy with real observations, astronomers refine their models, gaining deeper insight into the processes shaping Andromeda. For instance, simulations can reveal how spiral arms maintain their shape, how star formation is regulated, and how past mergers with smaller galaxies have left subtle imprints in the stellar distribution. Speaking of mergers, Andromeda's satellite galaxies are an essential part of the mapping process. The galaxy is surrounded by a family of smaller companions, some of which are easily visible like M32 and M110, while others are faint and difficult to detect. Large-scale surveys of the sky have uncovered an entire system of dwarf galaxies orbiting Andromeda. Tracking these satellites is crucial for understanding the galaxy's gravitational influence and its evolutionary history. Dwarf galaxies often fall prey to their larger host, gradually being absorbed over billions of years. By studying these interactions, astronomers learn how large galaxies grow, how stellar populations mix, and how dark matter shapes galactic halos. Among the most ambitious mapping projects is the effort to understand Andromeda's future collision with the Milky Way. Current measurements of its motion show that Andromeda is approaching our galaxy at roughly 120 kilometers per second. In about 4.5 billion years, the two galaxies are expected to begin merging in a dramatic cosmic event. Scientists use detailed observations of stars, gas clouds, and satellite galaxies to create computer models predicting how this merger will unfold. The simulations suggest that over billions of years, the spiral structures of both galaxies will be disrupted, stars will be scattered into new orbits, and a new, larger galaxy, sometimes called Milkomeda in popular literature, will emerge. This projected future highlights the importance of understanding Andromeda not just as it appears today, but as a dynamic entity with a story still unfolding. Despite decades of observation and modelling, many mysteries remain. Certain regions of Andromeda are still poorly understood, whether because they are obscured by dust, too faint to detect, or influenced by unseen forces such as dark matter. New technologies will be essential to uncover these hidden secrets. Future space telescopes, including the upcoming Nancy Grace Roman Space Telescope, are expected to push the boundaries of our understanding. With more powerful instruments capable of capturing unprecedented detail, astronomers will be able to study individual stars, identify previously hidden structures, and refine models of Andromeda's formation and evolution. These advancements will not only enhance our understanding of Andromeda, but also provide broader insights into the behaviour of galaxies across the universe. The task of mapping Andromeda exemplifies the scale, patience, and ingenuity required for modern astronomy. It is a project that combines cutting-edge technology, careful observation, theoretical modelling, and years of meticulous analysis. Each image, spectrum, and simulation contributes to a richer picture of a galaxy that is both familiar and enigmatic. As astronomers continue to chart Andromeda's stars, dust, gas, and satellites, they piece together not only the story of a single galaxy, but also the broader narrative of cosmic evolution. From the glow of newborn stars in dust-shrouded nurseries to the sweeping spiral arms stretching tens of thousands of light-years across, Andromeda offers a window into the workings of the universe on its largest scales. In mapping Andromeda, scientists are not just capturing images, they are tracing the invisible threads of gravity, composition and motion that bind the galaxy together. They measure the faint whispers of light that have travelled millions of years to reach Earth, decode the chemical fingerprints of stars formed billions of years ago, and simulate the dance of galaxies that will unfold billions of years from now. Each discovery raises new questions, revealing the galaxy's layers of complexity and hinting at phenomena that may challenge our current understanding of physics and cosmology. Andromeda's story is also a story of connection. Its interactions with satellite galaxies, the anticipated merger with the Milky Way, and the flows of gas and dust all demonstrate that galaxies are not isolated islands, but part of a vast interconnected cosmic web. Mapping these interactions requires collaboration across continents and the use of multiple observatories, from ground-based radio telescopes to space-based infrared and optical instruments. The effort is a testament to human curiosity and ingenuity, showing how persistent observation, careful measurement and creative modelling can reveal the secrets of a galaxy millions of light-years away. In the coming decades, as new telescopes are launched and computing power increases, our maps of Andromeda will grow ever more detailed. Astronomers will be able to zoom in on individual stars, uncover the faintest dwarf galaxies, and perhaps even observe the earliest moments of star formation within its distant spiral arms. These advances will not only deepen our understanding of Andromeda itself, but also provide crucial benchmarks for understanding galaxies throughout the cosmos, offering clues to the origins, evolution, and ultimate fate of galaxies like our own Milky Way. Encircling the majestic spiral of the Andromeda Galaxy, a host of smaller galaxies quietly orbit, weaving an intricate ballet that unfolds over millions, even billions, of years. These satellite galaxies, varying dramatically in size, shape and history, are not mere spectators. They are participants in a slow, mesmerizing dance of gravity, motion and cosmic evolution. The surroundings of Andromeda are anything but simple. They are a bustling neighbourhood, a miniature universe of their own, where interactions and transformations continually reshape the landscape. The sizes and forms of these companion galaxies are astonishingly diverse. Some are compact, smooth, and almost featureless, like the tightly packed elliptical dwarfs. These galaxies, with their dense cores of ancient stars, seem to carry the wisdom of the cosmos in their quiet light. Others are more chaotic, irregularly shaped, and often appear as if caught in a violent struggle, their forms twisted and distorted as tidal forces slowly tear them apart. These irregular satellites, often rich in gas and star-forming regions, show the universe's ongoing act of creation and destruction. They are living laboratories where stars continue to ignite, where stellar nurseries shimmer like jewels amidst clouds of cosmic dust, revealing that even in a galaxy's periphery, life, stellar life, can thrive. Among this celestial entourage, two galaxies stand out prominently, M32 and M110. These two companions hover relatively close to Andromeda's bright, bustling central region, their proximity making them more noticeable even to modest telescopes operated by amateur astronomers. M32 is a compact elliptical galaxy, almost perfectly round, with stars packed densely into a remarkably small volume. It is a concentrated jewel of light, where the starlight is thick and intense, creating a sense of stellar intimacy. M110, by contrast, is larger and more diffuse. Its stars spread across a wider expanse, giving it a softer, more ethereal appearance. Yet despite its gentler visage, it bears the scars of past encounters with its massive host. Astronomers studying M110 have uncovered evidence of historical interactions with Andromeda. Subtle ripples in its star distribution, hints of stripped gas, and the faint trails of stars pulled outward by gravitational tides. These two galaxies are more than companions. They are living records of Andromeda's long and complex history. Both M32 and M110 are thought to be the remnants of once larger galaxies, stripped bare of their outer layers and gas by Andromeda's immense gravitational influence many billions of years ago, leaving only dense cores to endure the eons. Beyond these luminous neighbours lies a multitude of fainter, more elusive dwarf galaxies. They orbit Andromeda at much greater distances, like tiny celestial lanterns scattered across the dark waters of intergalactic space. Some of these dwarfs, such as NGC 147 and NGC 185, display structures reminiscent of miniature elliptical galaxies. Their stellar populations are old, calm, and mostly inactive. Very little new star formation occurs within their boundaries. They are serene and timeless, like small cosmic libraries preserving the secrets of the early universe. Others, like IC10, are still vigorously forming stars brimming with youthful energy. Despite Andromeda's imposing gravitational pull, IC10 has managed to retain much of its gas, allowing new stars to ignite and shine, demonstrating that even the smallest galaxies can resist the tidal dominance of a giant spiral and preserve pockets of ongoing creation. For many years, astronomers assumed that these satellite galaxies were scattered randomly around Andromeda, moving in various directions with little apparent order, each one following its own path dictated by chance encounters and gravitational quirks. Yet, recent observations have revealed something far more surprising and deeply intriguing. Many of Andromeda's satellite galaxies are not scattered haphazardly. Instead, they appear to be arranged in an enormous thin plane, as if strung along an invisible cosmic thread. This alignment is startling because it defies the expectations of classical galaxy formation models. It hints at a shared origin. Perhaps these satellites were born together in a single, coherent event, rather than being individually captured over billions of years. If true, this would mean that Andromeda's satellite system is not merely a chaotic assemblage of galaxies, but a structured, organized formation, revealing a new layer of cosmic architecture that challenges long-standing assumptions about how galaxies grow and evolve. Some scientists speculate that this planar arrangement may be part of an even larger cosmic pattern. Perhaps the satellites of Andromeda are linked to the Milky Way's own dwarf galaxy system, forming threads along immense cosmic filaments, long invisible strands of dark matter and gas that weave between galaxy clusters. These filaments act as bridges, guiding galaxies along their paths and orchestrating interactions across vast stretches of space. In this framework, the satellite galaxies are not isolated wanderers, but participants in an interconnected cosmic network, tied to each other and to their host galaxies by the invisible hand of dark matter. Yet, the relationship between Andromeda and its companions is not one-sided. While Andromeda's gravity dominates, it is not entirely immune to the influence of its satellites. The combined pull of these smaller galaxies subtly tugs at Andromeda's outer regions, causing its vast disk to warp and bend over time. Though the effect is gentle and occurs over millions of years, it contributes to the ongoing evolution of Andromeda's structure, hinting that even small companions can leave an indelible mark on their massive host. In some cases, the interactions are violent and transformative. Some of these satellites are slowly being consumed, their stars and gas stretched into elongated streams as they spiral toward Andromeda's core. Observations of Andromeda have revealed enormous arcs of stars and gas extending far into intergalactic space, remnants of galaxies that have already fallen victim to tidal forces. These streams are not mere cosmic debris. They are living evidence of the galaxy's growth through mergers, a process that continues to this day. One of the most dramatic illustrations of Andromeda's cannibalistic tendencies is the giant stellar stream, an immense ribbon of stars stretching more than 100,000 light-years across space. This stellar stream is believed to be the remains of a dwarf galaxy that ventured too close to Andromeda's gravitational grasp and was gradually torn apart. Its stars, once belonging to an independent system, now mingle with Andromeda's halo, merging seamlessly into the larger galaxy's population. The stellar stream provides a breathtaking glimpse of cosmic evolution in action, a galaxy devouring its smaller neighbours, absorbing not just their stars but also their histories, and weaving them into its own complex narrative. Such mergers are not isolated events. They are part of a continuous cycle of cosmic recycling, a testament to the restless and dynamic nature of galaxies in the universe. Even as these smaller galaxies are being drawn in, others retain surprising autonomy. Some are composed almost entirely of dark matter, invisible to traditional telescopes yet detectable through their gravitational influence. These so-called dark galaxies contain very few stars and almost no gas, making them nearly invisible against the dark canvas of space. Despite their faintness, they possess significant mass, enough to shape the motion of nearby objects and reveal the underlying architecture of Andromeda's dark matter halo. The existence of these nearly invisible satellites raises profound questions about galaxy formation and the nature of dark matter itself. How many such hidden galaxies lurk unseen throughout the universe? And what role do they play in shaping the evolution of the luminous galaxies we can observe? As time marches forward, the fates of Andromeda's satellites will continue to diverge. Some will inevitably merge with their dominant host, their stars becoming part of Andromeda's vast stellar population. Others may be flung into the depths of intergalactic space, cast out by complex gravitational interactions or cataclysmic encounters. Meanwhile, Andromeda itself is slowly moving closer to the Milky Way, on a collision course that will unfold in the distant future, several billion years hence. This impending convergence promises to reshape not only Andromeda's satellite system, but the entire local galactic neighbourhood. The gravitational ballet will intensify, mergers will accelerate, and new streams of stars will be pulled into ever more intricate patterns, continuing the grand story of cosmic evolution. Even as astronomers study these interactions, each discovery deepens the sense of wonder. The satellites of Andromeda are not static points of light. They are dynamic worlds, each with its own history, each contributing to the growth and transformation of a galactic giant. From the compact brilliance of M32 to the diffuse story-filled M110, from the star-forming exuberance of IC10 to the serene ancient dwarfs like NGC 147 and NGC 185, each satellite tells a tale of survival, struggle, and adaptation in the face of Andromeda's formidable gravity. Together they form a complex interwoven tapestry that reveals the hidden rhythms of galactic life, a universe in miniature playing out on the largest scales imaginable. By tracing the motions, structures, and interactions of these satellites, astronomers gain insight not only into Andromeda's past, but also into the invisible forces shaping all galaxies. Each orbit mapped, each tidal stream observed, is a clue to the distribution of dark matter, the forces that sculpt the cosmos and the mechanisms that drive galaxy formation. In this way, the satellites of Andromeda are more than companions. They are guides, helping us to decipher the grand cosmic puzzle and revealing that the universe is far more interconnected and dynamic than previously imagined. When a massive star comes to the very end of its life, the universe prepares for one of its most spectacular fireworks displays. This event is called a supernova. To human eyes, a supernova might seem like just another distant twinkle in the night sky, but in reality, it is one of the most powerful and transformative forces in the cosmos. Supernovas are not simply the quiet fading of a star, they are violent, dramatic, and world-changing explosions that shake entire galaxies. There are two main ways a supernova can occur. The first path happens when a single giant star, one many times larger than our own Sun, reaches the end of its natural fuel supply. A star survives by balancing two opposite forces, the inward pull of gravity and the outward push of energy produced in its core through nuclear fusion. For millions or even billions of years, this balance holds steady. But when the star runs out of the fuel it needs, gravity wins. The star collapses inward at breathtaking speed, and this sudden collapse triggers a violent explosion that blasts the star's outer layers into space. The second path to a supernova involves not one star, but two. In certain binary systems, where two stars orbit one another like cosmic dance partners, a smaller but extremely dense star called a white dwarf may quietly sit next to a larger companion. A white dwarf is already the burned-out core of a once-living star, but in a binary system it can continue to feed on material pulled from its partner. As this stolen matter piles onto the white dwarf, the star becomes dangerously unstable. If the white dwarf collects too much material, it cannot hold itself together. At that point, it undergoes a runaway thermonuclear explosion, completely tearing itself apart. No matter the cause, the result is the same. The star explodes with almost unimaginable power. In just a few moments, a supernova can release more energy than our Sun will radiate over its entire lifetime. This colossal blast sends shockwaves rushing outward in every direction. Along with the energy, the explosion flings newly forged heavy elements, things like iron, calcium, nickel, and gold, into the depths of space. These elements are essential for building planets, for forming atmospheres, and even for the chemistry of life itself. In a very real sense, every person on Earth carries within their bones and blood the ancient ashes of stars that exploded long before our world was born. Supernovas are not only dramatic finales to a star's life, they're also beginnings. The shockwaves produced by these explosions ripple through their surrounding neighbourhoods. When these shockwaves crash into nearby clouds of gas and dust, they squeeze and compress them. Sometimes this compression ignites the birth of brand new stars. In this way, the death of one star can spark the creation of many others. Without the cycle of stellar death and rebirth powered by supernovas, galaxies like Andromeda and our Milky Way would be barren, lacking the ingredients for rocky planets, oceans, forests, and living creatures. The Andromeda Galaxy, the closest major galaxy to our own Milky Way, has its own dramatic history of supernovas. These events have shaped its stars, sculpted its nebulae, and enriched its chemical composition. When we look at Andromeda today, a vast spiral of hundreds of billions of stars, we are not just seeing quiet, eternal light. We are seeing the results of countless explosions that occurred over millions of years, explosions that forged the galaxy's very structure. One of the most famous and well-studied supernovas in Andromeda took place in the year 1885. This event, known as SN 1885A, was observed from Earth and left behind a remnant that continues to fascinate astronomers. Unlike many supernova remnants that fade into the obscurity of time, this particular one remains a key subject of research because of its location and unique features. SN 1885. A was a Type Ia supernova, meaning it was the result of a white dwarf in a binary system accumulating too much mass and undergoing a runaway thermonuclear explosion. What makes this supernova especially interesting is that it erupted very close to Andromeda's galactic core. When it blew apart, it scattered iron and other heavy elements into the surrounding region. Even today, astronomers using modern telescopes can detect the faint traces of this explosion, like a ghostly shadow imprinted upon the galaxy's heart. This event also helped astronomers confirm something very important. Andromeda is not fundamentally different from our Milky Way in its ability to host such cataclysmic explosions. In both galaxies, stars can live, die, and explode in similar ways. By studying SN 1885A and others like it, scientists learned that supernovas are universal processes that help shape galaxies across the cosmos. But Andromeda is not home to just one or two famous explosions. Across its sweeping spiral arms and dense central regions, there exists a vast network of supernova remnants, the glowing shells of gas and energy left behind after a star's violent death. Some of these remnants are relatively young, only a few thousand years old. To human beings, 1,000 years might seem impossibly long, but on the timescale of galaxies, it is the blink of an eye. These young remnants still shine brightly in X-ray and radio light, their shock waves actively reshaping the space around them. Their expanding shells can be seen as glowing bubbles of gas, slowly stretching outward into the dark. Others are ancient, perhaps tens of thousands or even hundreds of thousands of years old. With time, their once distinct shells fade and their energy disperses. Eventually, their structures blend into the wider interstellar medium, the vast ocean of gas and dust that fills the galaxy. But even when their shapes have disappeared, their influence remains. The heavy elements they expelled continue to float through the galaxy, seeding future generations of stars and planets. By studying these remnants, astronomers can trace the past history of Andromeda. They can determine where massive stars once thrived, which regions of the galaxy were once bustling with star formation, and how these events shaped the galaxy's chemical makeup. Many remnants are clustered along Andromeda's spiral arms, the same places where new stars are still being born. This makes sense, since massive stars that end in supernovas tend to form in dense star-forming regions. But other remnants appear in surprising locations, in quieter areas where starbirth does not seem as active today. These unexpected placements suggest that Andromeda has experienced bursts of activity in the past. star-forming events that may have since quieted but left their fingerprints behind. The role of supernovas in shaping Andromeda cannot be overstated. The shock waves they generate act as galactic sculptors. Imagine a ripple spreading across the surface of a pond after a stone is thrown in. Now magnify that idea to a scale of hundreds of light years. These ripples stir up clouds of gas, triggering collapses that lead to new stars. Without them, Andromeda's spiral arms would not glow with such vigour, and many of its current stars might never have formed. Beyond star formation, supernovas also serve as chemical factories. Lighter elements like hydrogen and helium were created in the Big Bang, but heavier elements, the kind necessary for complex chemistry, are forged in stars and released during supernova explosions. Without supernovas, there would be no iron for blood, no calcium for bones, no oxygen for lungs, and no carbon for life itself. In essence, supernovas are the engines of creation for life's essential ingredients. Not all supernova remnants in Andromeda are alike. Some are unusually powerful, glowing more brightly or releasing more energy than expected. In certain cases, these remnants are associated with neutron stars, the collapse cores of massive stars that survived the explosion. Neutron stars are incredibly dense, packing more mass than our Sun into a sphere only about 20 kilometers across. Some of these neutron stars spin rapidly and emit beams of radiation like cosmic lighthouses. Astronomers call them pulsars. These pulsars continue to shine long after the supernova itself has faded, serving as beacons that can be detected across vast distances. By studying pulsars in Andromeda, astronomers gain insights into the physics of extreme matter, the behaviour of gravity under intense conditions, and the role such exotic objects play in shaping their galaxies. The influence of supernovas does not end with their remnants. The expanding shock waves accelerate cosmic rays, particles that move through space at nearly the speed of light. These high-energy particles zip through Andromeda, heating gas, altering its chemistry, and even ionizing clouds of hydrogen. The presence of cosmic rays affects how new stars are born, how gas clouds evolve, and how energy flows through the galaxy. Some supernova remnants in Andromeda also suggest a more complex past. If certain remnants appear in unexpected places or display unusual properties, it could mean that Andromeda has swallowed smaller galaxies in the past. These dwarf galaxies, torn apart by Andromeda's gravitational pull, may have carried their own massive stars that later exploded as supernovas. In this way, some of the most ancient remnants we observe today may not even belong originally to Andromeda but to galaxies it absorbed long ago. When we step back and think about the larger picture, the story of supernovas in Andromeda is also the story of life itself. Without the cycle of stars exploding, scattering elements, and triggering new generations of stars, there would be no Earth and no people. The iron in your blood, the oxygen in your breath, the calcium in your bones, all of these were once forged in stars that lived and died billions of years ago. When astronomers look into the night sky, they do not just see distant suns twinkling like tiny points of light. They are in fact witnessing a grand symphony of change, motion, and energy. Among the most fascinating players in this cosmic orchestra are variable stars, celestial bodies whose brightness does not remain steady. These stars act like natural beacons, flickering lanterns in the dark, guiding scientists as they try to measure distances, understand how stars evolve, and uncover the secret workings of galaxies. Unlike the steady glow of most stars, variable stars change their brightness. Sometimes they brighten and dim in predictable rhythms, much like the steady beating of a drum. At other times, their light shifts chaotically, with sudden bursts of energy followed by fading silence. Each variation tells a story. By studying these stars, astronomers can piece together how galaxies like Andromeda, the great spiral neighbour of our own Milky Way, live and change over billions of years. Within Andromeda, astronomers have already identified many thousands of variable stars, and no doubt countless more remain waiting to be discovered. Each one acts like a messenger, carrying clues about the past, present, and even the future of this majestic galaxy. One of the most famous types of variable stars is the Cepheid variable. These stars have played an extraordinary role in the history of astronomy. Long ago, in the early years of the 20th century, the astronomer Henrietta Swan Leavitt discovered that Cepheid variables pulse in a regular pattern. The brighter they are, the longer their cycle of brightening and dimming. This relationship gave astronomers a way to measure distances across the universe. By observing how long it takes a Cepheid to cycle from bright to dim and back again, scientists can calculate its true luminosity. By comparing this with how bright it appears from Earth, they can determine how far away it lies. Even today, Cepheids remain one of the most trustworthy rulers for measuring cosmic distances. Within Andromeda, Cepheid variables have been used to refine our knowledge of the galaxy's true scale. When astronomers measure the light of these stars, they are not just studying single points of brightness. They are stretching invisible measuring tapes across the cosmos, gauging the size of one of the largest and nearest spiral galaxies beyond our own. But Cepheids are not the only variable stars shining within Andromeda's sprawling arms and luminous heart. Other stars, some smaller, some older, also hold secrets in their flickering light. Another important group is the RR Lyrae stars. These are older, smaller cousins of the Cepheids. While Cepheids help astronomers measure great cosmic distances, RR Lyrae stars serve a different purpose. They are often found in ancient environments such as globular clusters and the extended halo surrounding Andromeda. The rhythmic pulses of RR Lyrae stars allow scientists to trace the oldest structures in the galaxy. Their presence reveals where the most ancient stars are gathered, some of them more than 10 billion years old. These flickering stars are like living fossils. They record the early days of Andromeda's formation, whispering of times when the galaxy was still assembling itself from gas clouds and smaller galaxies that collided and merged. By mapping the positions of RR Lyrae stars, astronomers can trace the invisible skeleton of Andromeda, identifying regions that have remained unchanged for billions of years. Unlike Cepheids, which act as lighthouses pointing the way to far-off galaxies, RR Lyrae stars are more like archaeologists, helping us reconstruct the history of the stars that were born long before our Sun existed. Not all variable stars change their brightness because of inner pulsations. Some vary because of external events. One of the most dramatic examples comes from eclipsing binaries, pairs of stars that orbit around each other like dancers locked in a cosmic waltz. From Earth, we watch as one star passes in front of the other, blocking part of its light. Each time this happens, the system's brightness dips, only to brighten again as the stars move apart. The timing and depth of these dips reveal remarkable secrets. By studying them carefully, astronomers can calculate the stars' sizes, masses, orbits, and even their temperatures. Andromeda is full of such pairs. Some are massive blue giants, burning furiously and living only a few million years before collapsing into supernovae. Others are tiny red dwarfs, cool and dim, circling each other for billions of years in slow, patient dances that may last for decades. These eclipsing binaries are laboratories of astrophysics, showing how gravity, motion, and light all interact in the heavens. Another dramatic class is the cataclysmic variables. These occur in binary systems where one star steals matter from its companion. Imagine a vampire star siphoning gas from its partner, piling it onto its own surface until the pressure grows so intense that an explosion occurs. In that instant, the system flares dramatically, releasing a burst of light so powerful that a once invisible star can suddenly blaze forth, only to fade back into obscurity days or weeks later. Within Andromeda, countless such systems lie hidden, waiting for their next eruption. Each nova outburst adds to the galaxy's tapestry of change, reminding astronomers that even the smallest stars can produce enormous drama. Some variable stars change on much longer timescales. These are the long-period variables, often giant red stars nearing the ends of their lives. One common type is the Mira variable, named after the star Mira in the constellation Cetus. These stars can take months or even years to move from bright to dim and back again. As they pulsate, they shed their outer layers into space, releasing carbon and heavier elements that enrich the interstellar medium. In this way, dying stars provide the raw material for new stars, planets, and perhaps even future life. Within Andromeda, Mira-type variables can be seen as cosmic gardeners, seeding the galaxy with the ingredients that will one day form new generations of suns. By following the slow rhythms of these giants, astronomers witness the very last chapters of stellar evolution. Some will eventually collapse into white dwarfs, surrounded by glowing planetary nebulae, delicate shells of gas expanding into space. Each of these elderly stars is a reminder that death in the cosmos is never an end, but always a transformation, giving birth to something new. Andromeda is not uniform in its distribution of variable stars. Different regions of the galaxy host different populations. In the central bulge, where stars are packed tightly together, many variables are old, their light dimmed by age. Here our Lyrae stars are common, serving as markers of ancient stellar groups. In the spiral arms, where gas and dust swirl in ongoing waves of star formation, young and brilliant variable stars dominate. Cepheids and bright blue variables shine here, their youth and energy testifying to recent bursts of starbirth. In the outer halo, far from the galaxy's shining heart, lie the globular clusters, ancient spherical gatherings of stars. Here our Lyrae and other old variables flicker faintly, tracing the remains of galaxies long ago absorbed by Andromeda. Thus, by mapping the distribution of variable stars, astronomers can trace the very architecture of Andromeda, reading its history like chapters in a book. At first glance, Andromeda seems like a classic spiral galaxy, a bright bulge at the centre, elegant arms spiralling outward, and a halo of stars surrounding it all. But closer study reveals that its structure is not as symmetrical as it first appears. One of the strangest features is that Andromeda seems to have two overlapping spiral patterns. Unlike the Milky Way, which has a single clear set of arms, Andromeda's spirals do not line up perfectly. This double pattern may be the scar of a collision in the past, perhaps when Andromeda absorbed one of its smaller satellite galaxies. The crash would have stirred the stars and gas, leaving behind the mismatched spirals we see today. Another anomaly lies in the uneven brightness of the arms. In most spiral galaxies, the arms are continuous, well-defined ribbons of stars, gas, and dust. But in Andromeda, the arms appear fragmented. Some sections are thick with clusters of young stars, while others look faint, diffuse, and scattered. This unevenness suggests that gravitational interactions, both past and ongoing, are constantly tugging at the galaxy's form. Beyond the major arms, astronomers have also detected faint outer filaments and structures stretching into space. These are difficult to see without deep imaging, but they reveal more about Andromeda's turbulent past. Some of these filaments may be tidal debris, remnants of smaller galaxies shredded and pulled apart by Andromeda's gravity. Others may be density waves, temporary gatherings of stars and gas moving through the galactic disk. Unlike the main arms, which last for millions of years, these smaller features shift and change more quickly, reshaping the galaxy's face from one cosmic age to another. By studying the variable stars and the unusual structure of Andromeda, astronomers are uncovering a story of complexity and change. Each variable star is like a word in a grand cosmic language. Cepheids measure distances, RR Lyrae trace ancient populations, eclipsing binaries reveal stellar masses, cataclysmic variables show violent outbursts, and long-period variables demonstrate the graceful endings of stars. Meanwhile, the strange double spirals, uneven arms, and faint filaments tell of collisions, mergers, and ongoing evolution. Andromeda is not just a calm and orderly spiral. It is a galaxy still in motion, still healing from past encounters, and still reshaping itself under the pull of gravity. One of the most striking and puzzling things about Andromeda's design is the unusual shape of its inner disk. At first glance, it looks like a familiar spiral. But when astronomers studied it more closely, they noticed something odd. The spiral pattern is not symmetrical. One side of the galaxy's core has a spiral arm that looks stronger and more pronounced than the other side. Instead of being balanced like a neat wheel, the inner disk seems a little lopsided, as though something tugged on it unevenly and left a lasting scar. For a galaxy as massive and majestic as Andromeda, this kind of imbalance is surprising, because galaxies of its size are usually more orderly. This odd structure has led scientists to wonder, why is Andromeda's inner spiral so uneven? What event, force, or hidden influence twisted its shape? One explanation that astronomers put forward is that Andromeda may still be recovering from a close encounter with another galaxy in its past. Galaxies are not isolated islands floating in silence. They are social giants, constantly tugging on one another with their immense gravitational pull. When two galaxies pass close to each other, even without colliding head-on, the forces between them can create dramatic effects. Stars and clouds of gas can be pulled outward, twisted into streams, or shoved into unusual patterns. If the encounter is strong enough, entire spiral arms can be stretched, bent, or even torn away. It is possible that some millions or even billions of years ago, Andromeda brushed against another smaller galaxy or swallowed it completely. The tug-of-war from that interaction may have left the uneven structure we now see in its inner disk. In this sense, the galaxy we observe today may still carry the bruise of an ancient cosmic collision. Unlike humans who heal from wounds, galaxies can take billions of years to smooth themselves out, if they ever do. But an external encounter is not the only possible explanation. Some astronomers believe that the unusual spiral features in Andromeda may also be shaped by something even more mysterious: dark matter. Dark matter is a type of mass that does not shine, reflect, or absorb light. We cannot see it directly, but we know it exists because of the way it tugs on the matter we can see. In Andromeda, as in many galaxies, dark matter forms an invisible halo that surrounds the visible stars and gas. This halo may contain far more mass than the bright disk of stars itself. As normal matter, stars, dust, and gas, moves within this unseen framework, the dark matter may disturb it, nudging it into new paths and creating irregularities. If the dark matter in Andromeda is not spread evenly, it could explain why certain arms or regions look more distorted than others. In other words, the ghostly hand of dark matter may be tugging at the spiral arms, bending them out of balance and guiding the future growth of the galaxy in ways that we still struggle to understand. Another fascinating puzzle in Andromeda is the way new stars form inside it. In many spiral galaxies, including our own Milky Way, star formation tends to occur along the spiral arms. This is because the arms act like traffic jams in the galaxy's disk. As clouds of gas and dust orbit around the galactic center, they pile up and compress when they pass through the arms. This compression makes the gas collapse, sparking the birth of new stars. The glowing young stars then light up the arms, tracing the spiral pattern like a trail of cosmic fireworks. But in Andromeda, the story is more complicated. Astronomers have discovered that some regions of active star formation are not located inside the main spiral arms at all. Instead, clusters of young, brilliant stars are scattered outside the traditional arm structure, forming islands of light where no strong spiral pattern exists. This suggests that something other than the spiral arms is helping to trigger starbirth. One possible factor is the movement of interstellar clouds, huge drifting seas of hydrogen and dust that can crash into one another, creating shockwaves that compress the gas and ignite star formation. Another possibility is that past collisions sent ripples through Andromeda's disk, like a rock tossed into a pond, and those ripples continue to trigger bursts of new stars even far from the arms. Adding to the complexity, Andromeda does not only have spiral arms. When astronomers studied the galaxy in different wavelengths of light, they noticed faint circular patterns surrounding the core, almost like ripples on water. These structures look like ghostly rings of stars and gas, layered around the galaxy's heart. Where did they come from? The leading explanation is that they are the scars of past collisions. If a smaller galaxy plunged through Andromeda's disk in the distant past, it would have sent waves spreading outward, pushing stars and gas into expanding circles. Over time, these circles became the faint rings we see today. Some of them may slowly dissolve, blending back into the spiral arms, while others could evolve into completely new structures. They are like wrinkles in the fabric of the galaxy's history, reminders that Andromeda has endured a long and violent past. Beyond the bright spiral arms and faint rings lies another part of Andromeda that is even stranger: its enormous outer halo. This halo is made up of stars, gas, and dark matter that stretch far beyond the parts of the galaxy we can see clearly. Unlike the smooth glow of the inner disk, the halo is patchy and irregular, full of streams and shifting patterns. Some of these may be the leftovers of smaller galaxies that were torn apart and absorbed by Andromeda. Others may be tidal tails, ribbons of stars pulled outward by Andromeda's gravitational dance with its many satellite galaxies. This outer region is one of the least understood aspects of Andromeda. It is so faint that astronomers need sensitive instruments to study it, and even then, much remains uncertain. But one thing is clear: the halo is not empty space. It is a record of Andromeda's interactions, a scrapbook of every galaxy it has ever touched, collided with, or consumed. When we put all of these pieces together, the lopsided spiral arms, the scattered star-forming regions, the faint rings and the shifting halo, we see that Andromeda is not a neat textbook spiral. Instead, it is a living, evolving system. Its shape tells a story of encounters, disturbances, and constant change. Over billions of years, forces both visible and invisible have sculpted it into what we see today. The discovery of planets beyond our own solar system is one of the most breathtaking and mind-expanding achievements in modern astronomy. For centuries, humanity looked up at the night sky and wondered if other worlds circled distant stars, if somewhere out there in the vast reaches of the universe there might be planets like Earth, perhaps even with life of their own. For a long time, these questions could not be answered. Telescopes were powerful enough to show us galaxies, nebulae, and the fiery details of stars, but planets orbiting those distant suns remained hidden. That began to change only in the final years of the 20th century. By the year 1992, astronomers announced the discovery of the first confirmed exoplanets, planets orbiting stars beyond our Sun. Since then, the progress has been astonishing. In just a few decades, scientists have confirmed thousands upon thousands of exoplanets within our own Milky Way galaxy, with thousands more waiting to be confirmed. Some are gigantic gas giants larger than Jupiter, others are rocky worlds more like Earth, and some are strange types of planets that we never imagined before. Yet, as incredible as this explosion of discovery has been, a greater challenge looms: finding planets beyond our own galaxy. The thought of discovering exoplanets in the Andromeda galaxy, or perhaps even further away, feels almost like science fiction. And yet, astronomers are beginning to take their first real steps toward making it possible. Before diving into how we might find planets in another galaxy like Andromeda, it helps to understand how we already find them in our own Milky Way. Over the years, scientists have developed a handful of clever techniques for detecting planets circling distant stars. The most successful technique so far is called the transit method. This works like a cosmic shadow play. Imagine a tiny planet orbiting its star. From our perspective, if that planet happens to pass directly in front of its star, it blocks a tiny fraction of the star's light. The star dims very slightly, then brightens again once the planet moves past. By carefully watching for these repeating dips in brightness, astronomers can tell not only that a planet is there, but also how big it is and how long it takes to orbit its star. NASA's Kepler Space Telescope and its successor, TS, used this method to discover the majority of the known exoplanets. Another key technique is the radial velocity method. This one doesn't rely on seeing a planet's shadow, but instead on detecting its gravitational tug. A planet, even a small one, pulls on its star as it orbits, causing the star to wobble very slightly. By measuring the star's light and the way its spectrum shifts back and forth, astronomers can detect that wobble and infer the presence of a planet. This method has been especially useful for finding massive planets close to their stars. Other methods exist too, like directly imaging a planet, which is rare but possible for giant worlds far from their stars, or detecting planets by how they affect pulsars, spinning dead stars that emit regular beams of light. But for most discoveries, the transit and radial velocity methods remain the workhorses. These techniques work beautifully for stars that are relatively close to us in the Milky Way. But the farther away a star is, the harder it becomes. Detecting a tiny dip in brightness or a tiny wobble in motion requires exquisite precision, and when the stars are millions of light years away, those signals are far too faint for our current instruments. This is why the challenge of finding planets in the Andromeda galaxy is so immense. Andromeda, also called M31, is the nearest large spiral galaxy to us, yet it is still unimaginably far, about 2.5 million light-years away. To put that into perspective, if you could somehow travel at the speed of light, it would take 2.5 million years to reach Andromeda. For comparison, modern humans as a species have only been around for about 300,000 years. Andromeda is colossal. It contains well over 1 trillion stars, several times more than the Milky Way. With so many stars, it almost certainly contains an even greater number of planets. Some might be rocky and Earth-like, some might be gas giants like Jupiter, some might be icy worlds frozen in eternal winter, and others might be so exotic that we cannot yet imagine their nature. But how can we hope to find them from so far away? Here is where a remarkable technique called gravitational microlensing comes into play. This method uses a trick of gravity itself, as described by Albert Einstein's theory of general relativity. Gravity does not just pull on matter, it bends light. If a massive object like a star passes directly in front of a more distant star, its gravity can act like a lens, bending and magnifying the light from the background star. The background star appears to brighten for a short time and then fade back to normal. This is called a microlensing event. Now here is the clever part. If that intervening star has a planet orbiting it, the planet's gravity can create a second, smaller brightening in the light curve. In this way, astronomers can detect the presence of a planet, even if they cannot see the star itself clearly. Unlike the transit or radial velocity methods, microlensing does not require us to distinguish individual stars in distant galaxies. Instead, it allows us to spot planets indirectly through their gravitational fingerprints. This method has already been used successfully within the Milky Way to find planets that would otherwise be invisible. And in the year 2020, astronomers reported something extraordinary: the possible detection of a planet in another galaxy, the Whirlpool Galaxy, located about 23 million light-years away. Using X-ray observations, they noticed subtle distortions in the emissions from a binary system, which could only be explained if a planet were present. Although this detection remains unconfirmed, it was the first tantalizing hint that extragalactic planets might truly exist and might one day be found in larger numbers. Andromeda, with its dense and crowded core full of overlapping stars, is the perfect target for microlensing. In theory, if astronomers monitor Andromeda long enough, they should observe microlensing events that reveal the existence of planets orbiting its stars. Each event might last only hours or days, so patient and consistent monitoring is crucial. Even if we succeed in detecting planets in Andromeda, the reality is that what we can know about them will be limited. In the Milky Way, when a new exoplanet is discovered, astronomers often follow up with additional observations to estimate its size, its mass, and sometimes even clues about its atmosphere. Using space telescopes like Hubble or the James Webb Space Telescope, scientists can analyze starlight as it passes through an exoplanet's atmosphere, revealing gases like hydrogen, helium, carbon dioxide, or even water vapor. But with Andromeda, the distance makes such follow-up impossible. For the foreseeable future, we will only be able to detect the presence of planets, not their details. We may not know whether they are rocky or gaseous, whether they have thick atmospheres, or whether they could support life. Still, the simple knowledge that planets exist in another galaxy would itself be one of the most profound discoveries in the history of science. Within the Milky Way, astronomers often discuss the concept of the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. Water, as far as we know, is essential for life. Many of the exoplanets discovered so far orbit within the habitable zones of their stars, raising the exciting possibility that they could be hospitable to life. Applying this idea to Andromeda is much trickier. Even if we detect a planet in Andromeda and calculate that it lies within its star's habitable zone, confirming whether it actually has water or an atmosphere is beyond our capabilities right now. And yet, given the similarities between Andromeda and the Milky Way, it seems reasonable to assume that there must be planets there that resemble Earth in important ways. Perhaps some have oceans, continents, and atmospheres thick with clouds. Perhaps others are frozen wastelands or burning deserts. There may even be worlds with conditions utterly alien to us, planets covered in exotic ices or orbiting dim, red stars where life might evolve in forms we cannot easily imagine. What makes Andromeda especially fascinating is its history. Unlike the Milky Way, which has enjoyed a relatively calm existence, Andromeda has undergone multiple mergers with smaller galaxies. Over billions of years, it has swallowed and absorbed many neighbours. These cosmic collisions stir up stars and planets alike, disrupting stable systems. As a result, Andromeda may contain many rogue planets, worlds that were ejected from their solar systems during these chaotic mergers and now drift freely through interstellar space, no longer orbiting any star. These orphaned planets would be extremely difficult to detect, but they may be very numerous, lurking in the galaxy's halo far from the bright spiral arms. If planets do exist in Andromeda, their environments would be shaped by the regions of the galaxy in which they lie. In the core of Andromeda, planets would orbit stars crowded tightly together, bathed in intense radiation and gravitational forces. Habitability there would be unlikely. In the spiral arms, conditions might be more familiar, comparable to our own solar neighbourhood in the Milky Way. Here, planets might circle stars in relative stability, with a mix of gas giants, rocky planets, and icy bodies. In regions rich with supernova remnants and star clusters, planetary formation might be disrupted or altered, leading to unusual systems. Near black holes scattered throughout the galaxy, planets might face extreme gravitational challenges. The search for exoplanets, especially in distant galaxies, produces enormous amounts of data. Sifting through this data for the faintest signals is a job well suited to artificial intelligence. Already, machine learning algorithms are being used to reanalyze old data from Kepler and TESS, finding planets that humans overlooked. As these tools improve, they may become essential in detecting subtle microlensing signals from galaxies like Andromeda. Of course, discovering planets in Andromeda immediately raises a tantalizing question. Could we ever travel there? The idea of intergalactic travel is one of the most ambitious and speculative dreams in physics. The challenges are staggering. Andromeda is about 2.5 million light-years away. Even if we could build a spacecraft capable of travelling at the speed of light, which current physics says is impossible, it would still take 2.5 million years to get there. The fastest spacecraft ever built by humans, NASA's Parker Solar Probe, travels at about 430,000 miles per hour. At that speed, a trip to Andromeda would take longer than 4,000 times the entire span of recorded human civilization. Clearly, chemical rockets and current propulsion systems will never take us beyond the Milky Way. Scientists are therefore exploring radical new ideas. Light sails powered by giant lasers could, in theory, accelerate spacecraft to a significant fraction of the speed of light. The Breakthrough Starshot initiative is already testing this concept on a small scale, aiming to send tiny probes to Alpha Centauri, our nearest star system, within a human lifetime. Scaling this up for intergalactic travel would be a monumental challenge, but it is not entirely outside the realm of physics. Antimatter propulsion is another idea. Antimatter releases enormous amounts of energy when it meets normal matter. If we could create and store it safely, it might one day drive spacecraft to near-light speeds. Nuclear fusion engines, powering spacecraft the way stars power themselves, could provide long-term, efficient thrust. These ideas remain theoretical, but they keep the dream alive that one day, perhaps in the far future, humanity might leave the Milky Way and journey to galaxies like Andromeda. Antimatter is perhaps the most astonishing and powerful substance that modern science has ever imagined. Unlike ordinary matter, which makes up everything we see around us, antimatter carries the potential to release unimaginable amounts of energy when it meets its opposite twin, regular matter. When the two touch, they annihilate each other completely, leaving behind nothing but pure energy. This makes antimatter the most energy-rich material ever known, far more powerful than the fuels we use in rockets today. To put it in perspective, even a very tiny amount of antimatter, just a few grams, could release more energy than thousands of tons of chemical fuel. This is why many scientists and engineers dream of one day building spacecraft powered by carefully controlled antimatter reactions. Such a ship could travel at speeds vastly greater than anything chemical rockets could ever hope to achieve. With our current rockets, which rely on burning fuel, we can only reach a fraction of the speed of light. But with antimatter, the dream of travelling across the stars begins to look more realistic. Of course, there is a major obstacle. Creating and storing antimatter is something we cannot yet do on a useful scale. In modern laboratories, scientists have managed to make only a few atoms of antimatter at a time, and even then, keeping it stable is almost impossible. The tiniest contact with matter destroys it in an instant, releasing dangerous amounts of energy. For now, antimatter-powered spacecraft remain an exciting idea on paper, waiting for breakthroughs in both physics and engineering. But let us imagine, just for a moment, that humanity overcomes these barriers. Suppose we manage to build a spacecraft capable of reaching speeds close to the speed of light. Something extraordinary happens when objects move at such incredible speeds. time itself begins to behave differently. According to Einstein's theory of relativity, travellers on a near-light speed ship would experience time passing much more slowly than people who remain behind on Earth. This strange effect is called time dilation. For example, while the journey to the Andromeda galaxy might take millions of years when measured from Earth, those on board the ship could experience the trip as lasting only a few short decades. In their personal frame of time, the impossible distance becomes manageable. Yet, antimatter propulsion is not the only idea dreamers and scientists have put forward. Some have wondered if we might harness the power of nature's most extreme objects, black holes. A black hole is so massive and dense that not even light can escape from it. Some theoretical proposals suggest that black holes could be used as energy sources, as gravitational slingshots, or perhaps in ways we cannot yet imagine, to help propel ships across the cosmos. Another bold concept is the Alcubierre warp drive, a theoretical solution to Einstein's field equations. Instead of pushing a spacecraft through space at incredible speeds, the warp drive would bend space itself. Space in front of the ship would contract, while space behind it would expand, effectively moving the ship forward without the ship itself breaking the universal speed limit of light. From the outside, it would appear as though the ship were travelling faster than light, but in reality it would be space that was doing the moving. However, such a drive would require forms of energy that we have never observed in the real universe, things like negative mass or exotic energy. These are not materials we know how to create, and they may not even exist at all. For now, the warp drive remains a fascinating mathematical idea, more suited to science fiction than the engineering blueprints. Beyond these human-made ideas, there is also the possibility that nature has already provided shortcuts across the universe. One of the most famous possibilities is the wormhole. A wormhole, if it exists, would be like a tunnel through space and time, connecting two distant points. Imagine folding a sheet of paper so that two faraway points touch. A wormhole would act like the shortcut through the fold. With such a bridge, a spacecraft could bypass the unimaginably vast distances between galaxies in an instant. The problem, however, is that no one has ever found evidence that wormholes exist, and even if they do, keeping one stable and open long enough for a ship to pass through would likely require exotic matter with properties unknown to physics. Still, many physicists believe that if advanced civilizations exist somewhere in the universe, they might have already mastered such technologies. Even if we figure out how to travel faster or take shortcuts, there is still another problem: survival. A trip across galaxies is not like a road trip across countries. We are talking about thousands, perhaps even millions of years of travel. How could human beings survive such long journeys? One solution might be to sustain life aboard the ship for endless generations, with children, grandchildren, and their descendants continuing the mission. Another possibility is far more futuristic: placing travellers in suspended animation. This concept is inspired by nature. Some animals, like bears, enter hibernation, slowing down their bodies for months at a time. Scientists are studying whether humans could one day be placed into similar deep sleep states for space journeys. Another approach is cryogenic freezing, preserving the body at extremely low temperatures and reviving it later. But the biological challenges of freezing and safely bringing a human back to life are enormous and remain unsolved. There is also a more radical alternative. Perhaps we should not send humans at all. Instead, we could send machines. One particularly fascinating proposal is the idea of self-replicating robotic probes. This idea was first suggested by the mathematician John von Neumann. He imagined spacecraft that would carry advanced artificial intelligence and the ability to build copies of themselves. When such a probe reached a new star system, it could harvest local resources, build another probe, and send it further on. Over time, these machines could spread across the entire universe, carrying information and exploring galaxies without the risks and difficulties of human travel. The beauty of this idea is that, once launched, the system would be self-sustaining. The probes could continue traveling indefinitely, perhaps for billions of years, spreading human knowledge and presence far beyond what human bodies could endure. Some scientists even speculate that if intelligent civilizations exist elsewhere, their first contact with us might not be through living beings, but through such probes. For now, all these possibilities — antimatter rockets, warp drives, wormholes, hibernation chambers, and robotic explorers — remain in the realm of theory and imagination, but history has shown us that human technology advances in leaps we often fail to predict. Ideas that once seemed impossible, flying across the sky, speaking across the world instantly, or walking on the moon, are now part of everyday reality. Perhaps one day, the dream of travelling to distant galaxies will move from fantasy to possibility. When we imagine journeys across the stars, it is easy to picture sleek spacecraft darting between galaxies, their glowing engines leaving trails of light behind them, carrying bold explorers into the cosmic unknown. Yet behind this dream lies a reality so difficult, so immense, that it makes our present space missions seem like small steps taken on a village road compared to the challenge of crossing an entire continent. Travelling across vast cosmic distances is not only a matter of speed, but of survival, precision, and endurance on a scale beyond anything humanity has ever attempted. A spacecraft trying to leave our home galaxy, the Milky Way, and reach our nearest galactic neighbour, the great Andromeda, would face challenges far greater than anything our technology has yet solved. The distance between the two galaxies is measured not in mere millions of kilometres, but in millions of light years. To put this into perspective, light itself, the fastest traveller in the universe, takes more than 2 million years to make the journey. For a human spacecraft, the problems are not just about moving fast. They include surviving deadly environments, carrying enough energy and resources, repairing inevitable damage, and navigating through a dark void where almost nothing exists to help or sustain travellers. Let us unfold this extraordinary challenge piece by piece, seeing not only the physical obstacles but also the human and philosophical ones that come with trying to cross the abyss between galaxies. One of the first dangers that any deep space traveller would face is radiation. Here on Earth, life is shielded in two powerful ways. The first protection comes from Earth's magnetic field, which acts like a giant invisible umbrella, bending away many harmful charged particles from space. The second protection comes from the Sun's heliosphere, a vast bubble created by the solar wind that pushes back some of the dangerous cosmic radiation from deeper space. But once a spacecraft leaves the solar system entirely, those protections vanish. The galaxy beyond is filled with high-energy cosmic rays, tiny subatomic particles moving at nearly the speed of light. These deadly particles are born in the most violent places in the universe, exploding stars called supernovae and gigantic black holes that hurl matter outward with unimaginable force. Over time, exposure to such radiation could damage the DNA of human travellers, leading to genetic mutations, cancer, and other health problems. Even if no crew were aboard, the radiation would slowly break down the delicate electronic circuits that control the ship. Protecting against this storm of invisible bullets is no simple matter. The easiest way would be to cover the spacecraft with thick shielding, perhaps many meters of lead, water, or other protective material. But this creates a terrible engineering problem. The heavier the shield, the more fuel is needed to move the ship, and the more impossible the journey becomes. An alternative is to develop active shielding, where artificial magnetic fields or plasma bubbles would be generated around the ship, imitating Earth's magnetic defense. Scientists are still struggling to make such concepts practical, but without them, long-term intergalactic travel may never be safe for humans. Once beyond the edges of the Milky Way, travellers would face a challenge even stranger than radiation: the overwhelming emptiness of space itself. Inside a solar system, there are at least occasional planets, moons, and asteroids that might provide resources. Space probes today can at least rely on Earth for directions and sometimes even resupply, as in the case of the International Space Station. But between galaxies, there are no way stations, no resource points, no scattered asteroids rich in minerals to mine. There is only an immense ocean of near-nothingness stretching across millions of light years. This means that every single resource, fuel, food, water, air, spare parts, must be carried from the very beginning. Now consider what this means. A journey lasting perhaps thousands, even millions of years cannot depend on simple storage. Food spoils, water can leak or evaporate, machinery breaks down. How could travellers store and preserve everything for such unimaginable spans of time? Our present chemical rockets are hopelessly inadequate. They burn fuel too quickly and provide too little efficiency for long-term travel. Even more advanced methods like nuclear propulsion or ion drives technologies far beyond what we have already used would likely fall short. Some scientists have dreamed of a Bussard ramjet, a theoretical spacecraft with enormous magnetic fields that scoop up the thin hydrogen gas drifting between the stars, feeding it into a fusion reactor to produce energy. On paper, this sounds perfect. A ship that never runs out of fuel because it gathers fuel as it flies. But the physics of making such a design work remain unsolved. For now, it is just an idea, a spark of imagination pointing to the kind of creative solutions humanity may one day need. Even if a spacecraft could move and carry its own resources, it would face another staggering challenge: finding its way. Within our solar system, spacecraft navigate by constantly receiving radio signals from Earth, using planets and moons as clear landmarks to confirm their position. But once in the deep intergalactic void, the familiar beacons of the solar system vanish. The stars themselves, though countless, grow faint and indistinct. How then would a spacecraft travelling to Andromeda know where it is and how to stay on course? One possible answer is pulsar navigation. Pulsars are neutron stars, remnants of exploded suns, that spin with incredible regularity and send beams of radiation sweeping across the universe like cosmic lighthouses. By reading these signals, a spacecraft might triangulate its position with remarkable accuracy, far more reliably than waiting for faint instructions from Earth that could take centuries or millennia to arrive. Still, such systems would have to be fully autonomous, operating without Earth's guidance for countless generations of travel. In space, even the smallest things can become deadly. A spacecraft flying at tremendous speeds would constantly face impacts from grains of dust and tiny fragments of rock called micrometeoroids. Each one may be no larger than a grain of sand, but at such speeds, even these tiny objects strike with explosive force. Over centuries, such impacts could tear away at the ship's protective shielding, weakening it until the safety of the crew and the integrity of the systems are in jeopardy. To survive this, ships of the future may need self-repairing materials, substances that can heal cracks automatically like living skin, or armies of robotic maintenance units that constantly patrol the hull, patching and reinforcing damage. If the spacecraft spins parts of its structure to create artificial gravity, those rotating systems must run without failure for thousands of years. No human-built machine has ever lasted so long, and inventing one that could may be one of the greatest engineering challenges in history. Today, one of our most distant spacecraft, Voyager 1, is still sending faint signals back to Earth from the edge of the solar system. Even at that relatively small distance, its messages take more than 22 hours to arrive. Imagine then a ship travelling not just billions of kilometres, but millions of light years. The delay in communication would quickly grow from hours to years, then centuries, and eventually millennia. If such a spacecraft were to send a message home after 1,000 years of travel, the civilization that launched it might no longer even exist when the signal arrived. The descendants of those who built the ship could be gone, and Earth itself might have changed beyond recognition. For this reason, an intergalactic vessel must be almost entirely independent, able to make decisions, solve crises, and even establish its own rules of governance without guidance from Earth. The crew, or perhaps the artificial intelligence running the ship, would be alone in the truest sense. Another problem awaits in the long dark: power. Inside our solar system, solar panels provide a dependable source of energy. The International Space Station, for example, relies almost entirely on solar power. But in the intergalactic void, far away from any star, solar energy becomes useless. The light of distant stars is simply too faint to generate meaningful power. Instead, a spacecraft would need to rely on more permanent energy systems, fusion reactors perhaps, or other yet-to-be-invented sources that could provide energy for millennia without constant refueling. Generating power is not enough. It must also be done sustainably, without degrading over unimaginable stretches of time. If humans are on board such a mission, then life support becomes one of the greatest challenges of all. Breathing air, drinking water, and eating food may seem simple on Earth, but in deep space, they demand flawless recycling. On the International Space Station, systems already recycle water and filter air, but supplies of food and certain materials must still come from Earth. For a journey between galaxies, such resupply is impossible. The only solution would be to create a fully closed ecosystem where every molecule is reused over and over again. Plants grown through hydroponics or aeroponics might provide food and oxygen, while human waste is broken down and returned to the cycle. In theory, this would work. In practice, keeping such a system balanced for centuries without collapse is extremely difficult. A single failure could mean the slow suffocation or starvation of the entire crew. Beyond the physical and technical challenges lies an even deeper one: the human spirit. A journey to Andromeda would not be completed in a human lifetime. Even if the spacecraft somehow travelled at a significant fraction of the speed of light, the trip would take millions of years. The people who boarded such a ship would never see the destination. Their children, grandchildren, and countless generations after them would live and die on the ship, knowing they were born to a voyage with no return. What would this do to a society trapped inside a spacecraft? How would they preserve their culture, their knowledge, their sense of purpose? Would they continue to believe in the mission after hundreds of generations, or would despair and rebellion threaten to end it? Perhaps new forms of governance, new religions, and entirely new ways of living would emerge on such a ship. The isolation of such a multi-generational journey might create an entirely new branch of humanity, forever separated from Earth. Some of these overwhelming difficulties might be avoided if the travellers were not humans at all. Robotic probes, powered by artificial intelligence, would not need air, food, or protection from radiation. They could drift for millennia without despair or cultural collapse. Perhaps the first ships to cross the abyss between galaxies will not carry human explorers, but machines acting as our messengers, carrying the knowledge and stories of humanity into the stars. Before diving into the galactic collision itself, let us imagine how such distant futures might be studied or even witnessed. Events that happen billions of years ahead lie far beyond the reach of any human lifespan. Even the most durable spacecraft we have built so far survive only decades, perhaps a century at best, before their systems break down. But one possibility is the use of highly advanced artificial intelligence machines. These would not only make decisions on their own, but also repair themselves and keep operating for millions of years without human intervention. Unlike biological life, these machines would not need food, air, or water. They would not require homes or life support systems. They would only need energy and raw materials. Yet even machines wear down. Metal corrodes, circuits fail, software errors accumulate. Over billions of years, even the most carefully designed robotic explorer would degrade. To face this challenge, scientists and dreamers have suggested something even more ambitious: self-replicating machines. These would not only fix themselves, but could also build entirely new versions of themselves, using the materials they find drifting in space: asteroids, comets, dust, or even planetary matter. Such machines could potentially survive for as long as the galaxies themselves, watching the cosmic drama unfold and recording it for whatever intelligent species may come after. Now let us return to the central story: the meeting of Andromeda and the Milky Way. Astronomers already know the outcome. Unlike guessing about tomorrow's weather, this prediction is not plagued with uncertainty. The Andromeda galaxy is moving directly toward us at a speed of roughly 110 kilometers every second. In more human terms, this means Andromeda is racing toward us at nearly 400,000 kilometers every hour. At this pace, the first close encounter will take place in about 4.5 billion years. That number is so vast it almost defies imagination, but in the life of galaxies it is simply the blink of an eye. When we hear the word collision, we imagine cars crashing, asteroids slamming into planets, or glass shattering. But the meeting of two galaxies is very different. Galaxies are unimaginably vast compared to the size of the stars within them. If you imagine a galaxy as big as a city, each star would be no larger than a single grain of sand. That means that when the Milky Way and Andromeda collide, the chance of two stars striking one another directly is extremely small. Instead, the most powerful effects will be invisible yet overwhelming: gravity. Each galaxy is a massive web of stars, gas, dust, and dark matter, all bound together by gravity. As they draw close, the gravity of one will tug and stretch the other, distorting its elegant spiral arms. Enormous streams of stars and glowing clouds of gas will be pulled outward, creating sweeping arcs across space known as tidal tails. The shapes of both galaxies will twist and warp, becoming less like the graceful pinwheels we know, and more like chaotic whirlpools. To predict these changes, scientists feed enormous amounts of data into supercomputers. They input everything they know about the mass of each galaxy, the distribution of stars, the speed at which each part moves, and the mysterious contribution of dark matter. Then the computer runs the laws of gravity forward in time, step by step, to simulate the unfolding encounter. Because even small differences in the starting conditions can lead to different results, astronomers run many simulations with slightly varied data. Some predict tighter passes, others wider swings. Yet all the simulations agree on one thing. Andromeda and the Milky Way are bound to merge. It will not be quick. Instead, they will pass through each other multiple times, like two dancers circling and crossing, before finally settling into one great embrace. The first close pass will be dramatic beyond words. As Andromeda swings into range, its gravitational pull will reach deep into the Milky Way, tugging on the arms of our galaxy and sending stars flying outward. At the same time, the Milky Way's gravity will stretch and distort Andromeda. The densest parts, the galactic cores, will likely pass through one another. Imagine two storm systems colliding and spiraling together. Gas clouds in both galaxies will be squeezed by these gravitational tides, and when gas is compressed, it collapses into new stars. Astronomers expect that this first passage will trigger a furious burst of star formation. Bright blue stars, enormous and short-lived, will flare to life, turning the colliding galaxies into a dazzling beacon. Many of these newborn stars will cluster together in dense groups, forming new star clusters. Some of the most massive stars may end their lives quickly, exploding as supernovae and collapsing into black holes. Others will settle into stable systems, creating new solar systems that may last for billions of years. But this will not be the end. After the first pass, the two galaxies will not merge instantly. Instead, gravity will slow them, pull them back together, and then draw them into another pass. With each encounter, more of their ordered spiral structures will be stripped away. The once proud arms of the Milky Way and Andromeda will be torn and flung into long tidal streams, glittering like ribbons across the darkness of space. Some stars will be hurled completely out of the system, ejected into intergalactic space where they may drift alone for billions or even trillions of years. Others will fall into new orbits, swirling around the growing heart of the combined galaxy. This slow-motion process will continue for billions of years until finally the two galaxies will lose their individual identities and settle into a single, larger structure. What kind of galaxy will emerge from this union? Simulations suggest that the final product will not be a spiral like its parents. Spirals are delicate structures, maintained by orderly rotation, but mergers randomize the paths of stars, scattering them into all directions. The result will be an elliptical galaxy, rounded, massive, and more chaotic in its stellar motions. This new galaxy will be larger than either the Milky Way or Andromeda alone. Astronomers have even given it a name, Milkomeda. Its stars will no longer circle in neat spiral arms, but will wander in a more three-dimensional swarm. Over time, its appearance will become smoother and more uniform. Its colour will shift as well. Right now, both the Milky Way and Andromeda sparkle with blue regions of star formation. But as time passes and the youngest, hottest stars burn out, the galaxy will glow more with the red and golden tones of older, cooler stars. At the heart of both galaxies lies a supermassive black hole, each millions of times the mass of the Sun. When the galaxies merge, these black holes will drift toward one another. They will orbit for some time, spiraling ever closer, until they too merge in one of the most violent and energetic events the universe can produce. This merger will release titanic ripples in space-time known as gravitational waves, echoes that could, in theory, be detected by future observers billions of years from now. The new central black hole will be even more massive, anchoring the core of Milkomeda with its overwhelming gravity. What about our own solar system? By the time the first encounter occurs, the Sun will already be near the end of its life. In roughly 5 billion years, the Sun is expected to expand into a red giant, swelling so large that it may engulf Mercury, Venus, and possibly even Earth. Life as we know it will not survive such a transformation. However, humanity or its descendants, whether biological, digital, or mechanical, might by then have spread far beyond Earth. For them, the galactic merger would present opportunities as well as dangers. New stars and planets formed in the burst of starbirth could create fresh worlds, some of which might be suitable for colonization. The rearrangement of stellar orbits might also shift travel routes, perhaps making interstellar journeys easier in some regions. There is even a slim chance that our solar system could be flung into a new orbit, pulled closer to the galactic center, or even ejected entirely into intergalactic space. If that happens, our sun and its planets would wander the void, carrying with them the remnants of a civilization that once belonged to the Milky Way. Eventually, after many billions of years, Andromeda will settle into a stable form. Its chaos will calm, its stars will drift into new positions, and its overall shape will become that of a vast elliptical galaxy. But the story does not end there. The universe itself is expanding, and it has been doing so since the Big Bang nearly 14 billion years ago. As time goes on, distant galaxies move farther and farther away. Their light becomes redder, stretched by expansion, until it fades entirely from view. In the far future, the only galaxies still visible will be those that are gravitationally bound to us now: Andromeda, the Milky Way, and their smaller companions. Once they have all merged, Andromeda will stand alone, a brilliant island of stars adrift in an increasingly empty cosmic ocean. The night sky, for whatever beings exist then, will look very different from ours. Instead of a sprinkling of distant galaxies, they may see only the shining heart of their solitary home. This vision of the future is not based only on theory. All across the universe, astronomers can observe galaxies in various stages of collision. Some are just beginning to interact, their arms distorted but still recognizable. Others are in the throes of violent mergers, their shapes twisted beyond recognition. Still others have already merged, forming the massive elliptical galaxies we see today. By comparing these real-world examples with computer simulations, scientists refine their models, ensuring that their predictions of the Milky Way-Andromeda merger are as accurate as possible. Each new discovery adds detail to the story of our future. When we gaze into the night sky, most of the stars we see belong to our own galaxy, the Milky Way. Yet, far beyond our familiar starry band lies another giant system, the Andromeda Galaxy, the closest spiral neighbour to our cosmic home. At first glance, the two galaxies look similar. Both are barred spirals with long sweeping arms. Both are members of the same galactic family called the Local Group, and both are titans compared to their smaller companions. But when astronomers study them more closely, important differences emerge. Differences that reveal not only how each galaxy has lived its life, but also where they might be headed in the future. The Milky Way and Andromeda are not isolated islands in space. Instead, they belong to a galactic neighbourhood known as the Local Group. This collection contains more than 50 galaxies, ranging from giant spirals to tiny, faint dwarfs. Among this group, Andromeda and the Milky Way are by far the largest and most influential. They dominate the gravitational landscape, shaping the paths and destinies of smaller galaxies that orbit around them. One might imagine them as two great monarchs presiding over a court of lesser companions, each pulling at the others with invisible strings of gravity. Within this group, size and mass matter. The gravitational power of these giants determines which smaller galaxies remain bound to the group and how interactions unfold. Understanding the differences between Andromeda and the Milky Way is therefore not just a matter of curiosity. It helps astronomers trace the story of galactic evolution across billions of years. One of the clearest differences between the two spirals lies in their visible diameters. Andromeda stretches across an enormous span of space, measuring about 220,000 light-years from edge to edge. By comparison, the Milky Way is smaller, with estimates ranging from 100,000 to 160,000 light-years across. Even at the smaller end of that range, Andromeda appears as the more extended system, its luminous arms sweeping farther into the cosmic dark. This larger disk hints at a more eventful past. Galaxies grow not only by forming stars within themselves, but also by swallowing smaller galaxies that wander too close. Andromeda's wide disk may be evidence of many such meals, each adding new stars, gas and dust to its structure. The Milky Way has grown too, but the more modest size suggests it may have consumed fewer large companions. While Andromeda looks bigger, bigger does not always mean heavier. astronomers believe that the Milky Way might actually outweigh its neighbour when the hidden mass of dark matter is taken into account. Dark matter, the mysterious invisible substance that outweighs normal matter by more than 5 to 1, forms halos around galaxies, extending far beyond the stars we can see. The Milky Way's dark matter halo seems to be especially massive and dense, possibly making our galaxy the heavier of the two despite its smaller visible disk. This puzzle raises an important scientific question. How do galaxies build their mass? Does visible size matter more than hidden dark matter? Or do interactions and collisions play the greatest role? Andromeda's wide arms and the Milky Way's heavy halo are different answers to the same cosmic riddle. When it comes to the number of stars, Andromeda again takes the crown. Astronomers estimate that it holds around 1 trillion stars. That is 1,000 billion blazing suns scattered across its vast spiral arms and central bulge. The Milky Way, in comparison, has somewhere between 200 and 400 billion stars, a dazzling number, but still less than half of Andromeda's population. Why the difference? Part of the answer lies in Andromeda's history of star formation and galactic mergers. By consuming other galaxies and efficiently converting gas into stars, it has built a more crowded city of suns. The Milky Way, though smaller in population, still maintains a healthy star-forming environment, with glowing blue clusters and bright nebulae scattered along its arms. The present pace of star formation tells a more surprising story. Despite its immense size and population, Andromeda has slowed down dramatically in creating new stars. Much of its gas has been used up or blown away in past bursts of activity, leaving fewer raw materials for new generations. In contrast, the Milky Way is still relatively active. Large clouds of gas and dust in our spiral arms continue to collapse under gravity, giving birth to new suns that light up regions like the Orion Nebula. This means that while Andromeda shines with the accumulated brilliance of past star-making, the Milky Way remains more youthful in spirit, still forming stars at a lively pace. In simple terms, Andromeda looks like an older city where most of the construction is finished, while the Milky Way resembles a bustling town still building new neighbourhoods. At the heart of both galaxies lies a dense central bulge of stars. Andromeda's bulge is especially large and bright, packed with older, redder stars. Its prominence suggests that Andromeda has gone through more violent events in its past. When galaxies collide or merge, enormous amounts of gas can be driven into the centre, triggering intense bursts of star formation. Over time, these stars grow old, redden, and gather into a dense core. Andromeda's bulge is a fossil record of such dramatic encounters. The Milky Way's central bulge, though still dense and bright, is less pronounced. This may mean that our galaxy has avoided major collisions for much of its history, or that its interactions were gentler, funneling less material into the centre. The difference reveals contrasting life stories. Andromeda as the more turbulent and aggressive sibling, the Milky Way as somewhat quieter and more measured. Both galaxies harbour monstrous black holes at their centres, objects so massive that not even light can escape their gravity. Andromeda's central black hole, often called M31, weighs in at around 140 million times the mass of the Sun. By contrast, the Milky Way's central black hole, Sagittarius A, is much smaller, at about 4 million solar masses. The enormous difference suggests that Andromeda's centre has experienced more dramatic growth. It may have swallowed multiple smaller black holes brought in by merging galaxies, or it may have accreted vast amounts of gas over billions of years. Whatever the process, the result is a far larger gravitational anchor that shapes the motions of nearby stars and creates a more energetic environment in the galaxy's core. Galaxies do not sit still, they spin. Stars in their disks orbit the centre at incredible speeds, creating the graceful spiral patterns we see from afar. In Andromeda, stars whirl around at an average speed of about 250 kilometers per second. In the Milky Way, the average speed is closer to 220 kilometers per second. Though the difference may seem small, it reflects Andromeda's larger mass distribution and denser bulge. These motions are part of the cosmic dance that holds galaxies together. Without the invisible hand of dark matter, the outer stars would fly away into space. The fact that they remain bound is further evidence that a vast halo of unseen mass surrounds each galaxy. Despite their differences, both galaxies share the same fundamental structure, a barred spiral shape. Their central bulges are crossed by elongated bars of stars, which act as channels, funneling gas inward toward the centre. This process fuels star formation and feeds the central black hole, ensuring that the core remains active. Such bars are common among spiral galaxies and are thought to arise from gravitational instabilities over time. Beyond the bar, sweeping spiral arms extend outward, dotted with star-forming regions, clusters and nebulae. These arms are the visible skeleton of the galaxy, marking the places where density waves compress gas into new stars. In photographs, the resemblance between the Milky Way and Andromeda is striking, two majestic pinwheels shining in the dark. Neither galaxy stands alone. Each is surrounded by a swarm of smaller companions, ranging from dwarf galaxies to globular clusters. The Milky Way's best-known satellites are the large and small Magellanic Clouds, irregular galaxies visible in the southern sky, along with the Sagittarius dwarf galaxy, which is currently being shredded by our galaxy's gravity. These companions provide fresh material and occasional collisions that shape the Milky Way's future. Andromeda, too, has its court. Its satellites include M32 and M110, both of which show signs of past interactions with their parent galaxy. Interestingly, recent studies suggest that Andromeda's satellites are not randomly scattered, but lie in a surprisingly ordered plane, as if they were arranged in a cosmic disk. The Milky Way's satellites, by contrast, appear more randomly distributed. This subtle difference hints at divergent histories of formation and interaction. Perhaps the most dramatic fact about Andromeda and the Milky Way is that they are on a collision course. Gravity is slowly pulling them together, and in about 4 billion years they are expected to meet. At that time, the two giants will merge in a titanic cosmic event. Stars will be flung into new orbits, gas will ignite in bursts of star formation, and the central black holes may eventually coalesce into a single, even more massive monster. For now, though, both galaxies continue their separate journeys, each telling a different story of growth, struggle, and survival. By comparing their anatomy, astronomers learn not only about these two neighbours, but also about the grand processes that shape galaxies throughout the universe. The Andromeda Galaxy is one of the grandest and most captivating objects in our night sky. It is the nearest large spiral galaxy to our own Milky Way, and for centuries it has drawn the attention of stargazers, storytellers, and scientists. At first glance, especially when seen through simple telescopes or even with the naked eye from very dark locations on Earth, Andromeda looks like a faint misty cloud stretched across the heavens. Yet what the human eye can see is only a tiny fraction of the galaxy's true nature. Much of Andromeda's extraordinary complexity remains hidden, cloaked behind immense curtains of interstellar dust. This dust is not like the dust we sweep from our homes, but rather fine grains of carbon, silicates, and ice scattered through space. These cosmic particles absorb and scatter visible light, the same type of light our eyes are tuned to detect. As a result, large portions of Andromeda's structure vanish behind this dusty veil, leaving astronomers with only fragments of the bigger picture. Trying to study Andromeda using only visible light is a bit like trying to peer through a smoky window. You might catch glimpses of what lies beyond, but the full scene stays obscured. Infrared light, however, changes the game entirely. Unlike visible light, infrared wavelengths can pass through much of the dust. This allows astronomers to look beyond the dark curtains that block our view and see Andromeda in an entirely new way. Using infrared observatories, both space-based telescopes like the Spitzer Space Telescope and ground-based instruments equipped with infrared detectors, scientists have revealed astonishing details about Andromeda's structure, history, and ongoing processes. These revelations have not only deepened our understanding of this nearby galactic neighbour, but also helped us unlock broader truths about how galaxies form, evolve, and interact. One of the most striking discoveries that infrared light has revealed is the detailed structure of Andromeda's dust lanes. In ordinary visible images, these dust lanes appear as dark streaks weaving through the galaxy's spiral arms. They look like ominous scars across the glowing starlit disk, blocking the light of millions of stars that lie behind them. But when astronomers switch their gaze to infrared wavelengths, these very same lanes undergo a dramatic transformation. Instead of appearing dark, they begin to glow with a faint but steady warmth. Infrared detectors can sense the energy emitted by dust particles that have absorbed starlight and then re-radiated it at longer wavelengths. Through this view, the once invisible becomes visible. What was once only a shadowed patch of nothingness now reveals itself as an intricate network, a skeleton that traces the hidden structure of the galaxy. This dust is far more than just an obstacle for astronomers. It is a key ingredient in the life cycle of stars. Dust, together with clouds of hydrogen gas, forms the raw material from which stars are born. In regions where the dust and gas grow especially dense, gravity begins to pull matter together. Over millions of years, this process can trigger the collapse of a gas cloud, eventually giving birth to new stars. By mapping these reservoirs of coal dust in infrared, astronomers are able to pinpoint where the next generations of stars in Andromeda will emerge, long before they flare to life in visible wavelengths. It is almost as if infrared astronomy grants us the power to see into the future, revealing the nurseries of stars before they awaken and shine brightly in the night. If the spiral arms of Andromeda are like majestic pathways winding through the galaxy, then its core is the beating heart. The central region of Andromeda is densely packed with stars, so many that in visible light they blend together into a single blinding glow. This makes it extremely difficult for traditional optical telescopes to study the finer details of the core. But once again, infrared light offers a solution. By cutting through the glare, infrared telescopes can unveil the hidden structures and motions at the very centre of the galaxy. At the heart of Andromeda lies a supermassive black hole, one with a mass equal to millions of suns. Surrounding this black hole is a dense, rotating disk of stars. In visible light, this region often appears as nothing more than a featureless bright blob. But in infrared, astronomers can distinguish the complex movements of stars as they orbit under the influence of the black hole's powerful gravity. They can watch as entire star systems trace their paths around this invisible monster, offering crucial clues about the dynamics and history of the galaxy's core. This ability to cut through the glare has given scientists an intimate look at a galactic nucleus, allowing them to explore questions about how supermassive black holes grow, how they influence the stars around them, and how such central regions evolve over billions of years. Not all stars shine the same way. As stars age, they undergo profound changes, many of which make them stand out more strongly in infrared light. Red giant stars, in particular, are bright in the infrared spectrum. These stars have exhausted the hydrogen in their cores and expanded to enormous sizes, glowing with a cooler but more powerful radiance that peaks in longer wavelengths. By mapping the distribution of these red giants, astronomers can effectively trace the long-term history of Andromeda. These older stars act like fossils, preserving the memory of events that shaped the galaxy across cosmic time. For example, if a certain region of Andromeda contains a particularly high concentration of red giants, it likely experienced a burst of star formation billions of years ago. On the other hand, areas with fewer of these aging stars might be younger, still dominated by middle-aged suns. Infrared surveys of Andromeda have allowed astronomers to piece together a timeline of its growth, showing where ancient stars settled and how the galaxy has gradually matured. Through these observations, Andromeda ceases to be just a flat image in the sky, and becomes a living history book written in starlight. Galaxies are not isolated islands in space. They often interact, collide, and merge with one another. When such encounters occur, they leave behind subtle signatures, tidal tails, stellar streams, and vast, faint arcs of dust and stars stretching across intergalactic space. Detecting these features in visible light is extremely difficult, as they tend to be very faint and spread over enormous distances. Infrared surveys, however, are particularly adept at picking up the warm glow of dust and the faint emissions of stars left behind by these interactions. In Andromeda, astronomers have discovered multiple stellar streams, ghostly remnants of smaller galaxies that were torn apart by Andromeda's immense gravity in the distant past. These streams are the scars of ancient galactic cannibalism, each one telling the story of a smaller system swallowed into Andromeda's vast expanse. By tracing these features in infrared, astronomers have been able to reconstruct episodes of Andromeda's past encounters. They can identify when and where dwarf galaxies merged into its structure, reshaping its spiral arms and contributing new material for star formation. These faint echoes of cosmic collisions remind us that galaxies, like living organisms, grow and evolve by consuming their smaller neighbours. One of the most surprising advantages of infrared observations is their ability to detect low-mass objects that are nearly invisible in ordinary light. Among these are brown dwarfs, sometimes called failed stars. Brown dwarfs form much like regular stars collapsing from clouds of gas and dust. But unlike true stars, they never grow massive enough to ignite sustained nuclear fusion in their cores. This means they cannot shine with the steady brilliance of stars like our Sun. Instead, they emit most of their faint radiation in the infrared spectrum, glowing gently with the leftover heat of their formation. Because they are so dim in visible light, brown dwarfs were almost entirely hidden from astronomers until the rise of infrared technology. Now, thanks to advanced infrared surveys, scientists have identified populations of brown dwarfs scattered throughout Andromeda. These discoveries are filling in the missing pieces of our understanding of the galaxy's stellar population. Brown dwarfs may not shine like true stars, but they are nonetheless important. They represent the lower end of the spectrum of cosmic objects, bridging the gap between stars and giant planets. By studying them, astronomers gain insight into the full range of processes that govern star and planet formation. In Andromeda, the identification of these faint companions shows just how diverse the galaxy truly is. Infrared astronomy has given us the ability to peel back the layers of dust, glare, and invisibility that once limited our understanding of galaxies like Andromeda. Through this new vision, astronomers have revealed the glowing skeleton of dust lanes, the star-forming nurseries of the future, the hidden dance of stars around a central black hole, the fossil record of ancient stellar populations, the faint scars of past mergers, and the hidden population of brown dwarfs. In a sense, to see Andromeda in infrared is to see it in its truest form. It is to witness not just the glittering facade of starlight, but also the deeper machinery that drives the galaxy's evolution. Each infrared image adds another chapter to the unfolding story of Andromeda, one of creation, transformation, and cosmic memory. When we look at the great Andromeda galaxy with our eyes or with ordinary telescopes that capture visible light, we see a glorious spiral of stars wrapped in lanes of dust. When we turn to infrared light, we pierce through some of that dust and catch glimpses of hidden stars, glowing clouds, and the warmth of cosmic structures. But when astronomers turn their ears toward the sky, listening with instruments that capture radio waves, a very different portrait of Andromeda is revealed. Radio astronomy does not show us twinkling stars or glowing dust. Instead, it paints a picture shaped by invisible magnetic forces, by cold and ghostly clouds of gas, and by the faint, almost secretive whispers of cosmic events that have been echoing through space for millions upon millions of years. This radio portrait is strange, unfamiliar, and yet vitally important, for it reveals aspects of the galaxy that cannot be seen in any other way. One of the most important tools of radio astronomy in the study of Andromeda is the mapping of hydrogen gas. Hydrogen, the most common element in the universe, is usually invisible to ordinary telescopes. But when hydrogen is in its neutral form, meaning its atoms are not charged, it gives off a very faint radio signal. This signal has a very specific wavelength of 21 centimeters, a fact so precise and universal that it is often called the hydrogen line. By tuning their radio instruments to this wavelength, astronomers can trace where hydrogen gas lies throughout the galaxy. It is like tuning a radio dial to exactly the right station, only instead of music, what comes through is the soft and steady voice of hydrogen atoms scattered across space. By collecting this signal from countless locations across Andromeda, researchers can construct detailed maps of its gaseous skeleton. These maps reveal not only where hydrogen is, but also where new stars may be born, since dense hydrogen clouds often collapse to form stars. They also show how the spiral arms of Andromeda are shaped, and how they continue to grow and twist over time. These hydrogen maps have revealed something astonishing. Andromeda's disk is far larger than it appears in optical images. With visible light, the bright portion of the galaxy seems to stretch about 220,000 light-years across. But radio maps, which trace the hydrogen gas, show that Andromeda's gaseous disk extends even farther, fading gradually into the vast intergalactic medium, the thin and ghostly matter that lies between galaxies. This means Andromeda is even more immense and sprawling than our eyes could ever guess. Visible light shows us the shapes of stars. Infrared light shows us the warmth of dust. But radio waves reveal something more elusive: the influence of magnetic fields. The universe is filled with charged particles, tiny fragments of matter like electrons and protons, that move at incredible speeds. When these particles spiral around magnetic field lines, they produce a faint kind of radio emission known as synchrotron radiation. It is not bright or flashy, but it is steady and dependable. By detecting and mapping this radiation, astronomers have discovered that Andromeda has a surprisingly organized magnetic field that stretches across much of the galaxy. This magnetic field is not just a curiosity. It plays an active role in shaping Andromeda. It guides the paths of cosmic rays, those mysterious high-energy particles that streak across space. It also helps influence how interstellar gas moves, clumps, and sometimes collapses into stars. In this way, the unseen magnetic field becomes a quiet architect of star formation, sculpting the future of the galaxy in ways that optical light could never reveal. Another wonder revealed through radio astronomy is the presence of pulsars inside Andromeda. Pulsars are the rapidly spinning remains of massive stars that have exploded in supernovae. What is left behind is a neutron star, a city-sized sphere so dense that a teaspoon of its material would outweigh mountains. As these neutron stars spin, they emit powerful beams of energy, like the rotating beams of a cosmic lighthouse. Each time the beam sweeps across Earth, our telescopes detect a pulse of radio waves. From this comes their name, pulsars. Andromeda lies millions of light-years away, yet its pulsars can still be heard across the cosmic gulf. Sensitive radio telescopes on Earth have identified several of these rhythmic beacons within our neighbouring galaxy. Every pulse is a heartbeat from a long-dead star, a message carried across the ages that tells us about the final stages of stellar life in a galaxy beyond our own. At the centre of Andromeda lies a supermassive black hole. Astronomers call it M31 star, though it is not nearly as active as the monstrous black holes found at the centres of galaxies like quasars. Even so, Andromeda's central black hole whispers in radio waves. These faint emissions come from charged particles caught in the powerful magnetic fields near the black hole. Spiralling at nearly the speed of light, these particles radiate energy that radio telescopes can pick up. By studying this glow, astronomers can peer into the turbulent heart of Andromeda and learn about the feeding habits of its black hole. Sometimes the black hole swallows matter greedily, at other times it starves, and these patterns are written into the radio emissions that spill out into space. Andromeda holds more secrets than astronomers have yet solved. Beyond the central black hole, radio telescopes have detected strange sources of radio waves scattered throughout the galaxy. Many of these sources have no clear match in visible or infrared images. Some may be the echoes of ancient supernovae, star explosions that blasted material outward in shock waves, energizing the surrounding gas and causing it to radiate in radio wavelengths. Others may be nurseries of new stars, places where massive young stars pour energy into their neighborhoods, ionizing the gas around them and creating bursts of radio emission. But not all of these sources are so easily explained. Some remain enigmatic, flickering on radio maps without any obvious cause. Identifying and understanding them is one of the ongoing challenges of modern astronomy, requiring more sensitive instruments and patient observation. Radio astronomy has also been pressed into service for one of humanity's boldest questions: are we alone? Because radio waves can travel vast distances without being easily absorbed or scattered, they are an ideal choice for communication across space. Human beings themselves use radio signals for everything from music broadcasts to deep space communication with spacecraft. It is not unreasonable to think that if intelligent civilizations exist elsewhere, they might also choose radio waves as their voice. With this thought in mind, astronomers have aimed radio telescopes at Andromeda, hoping to catch a pattern in the static, something structured, intentional, and different from the random noise of natural processes. So far, no such signal has been found. But the search continues, as part of the broader project known as SETI, the search for extraterrestrial intelligence. The idea that beings in another galaxy might one day call out across the void is too compelling to ignore. The future of radio astronomy promises even more discoveries. A giant new telescope called the Square Kilometre Array is under construction. As its name suggests, its combined collecting area will stretch over 1 square kilometre, making it the most powerful radio telescope ever built. When completed, This instrument will allow astronomers to map Andromeda's magnetic field in far greater detail than ever before. It will be sensitive enough to detect the faintest hydrogen signals, revealing the most delicate tendrils of gas that feed the galaxy. It will also uncover hidden sources of radio waves that today remain invisible to our best instruments. Through radio astronomy, Andromeda reveals itself not just in light, but in whispers. Its hydrogen gas hums quietly at 21 centimeters. Its magnetic fields glow with faint synchrotron radiation. Its pulsars beat like cosmic drums. Its black hole murmurs with particles caught in its grasp. Even its mysteries, those unexplained radio sources, add to the chorus. When most people think of galaxies, they imagine collections of stars, planets, gas and dust spiraling together in immense formations. But galaxies are more than just glowing islands of light floating in the universe. They're also massive engines of gravity, bending and shaping space itself. One of the most fascinating effects of this bending is something called gravitational lensing. In simple terms, gravitational lensing happens when the gravity of a massive object, like a galaxy or even a single star, bends the path of light travelling from something behind it. This bending works much like a magnifying glass, distorting and enlarging the image of the distant background object. The Andromeda galaxy, being both large and close in cosmic terms, can act as such a natural lens. This effect is not just a scientific curiosity, it is one of astronomy's most powerful tools. Through Andromeda's gravity, astronomers can glimpse hidden galaxies from the early universe, galaxies so faint and distant that even our most powerful telescopes could not normally detect them. Thanks to Andromeda's cosmic magnifying glass, we're able to look back billions of years into the past, to a time when the first stars and galaxies were only beginning to form. Without this natural assistance, these delicate and ancient structures would remain forever invisible to us. Of course, using Andromeda as a lens is not simple. Unlike faraway galaxies that appear as faint smudges in the sky, Andromeda is relatively close to Earth, only about 2.5 million light-years away. Because of this closeness, it shines brightly, and its own stars, glowing clouds of gas and heavy curtains of dust can easily overwhelm the faint signatures of the background galaxies. This means that detecting gravitational lensing within Andromeda is like trying to spot a dim candle flickering behind a blazing spotlight. Yet astronomers are not easily discouraged. Over decades, they have developed sophisticated methods to separate the foreground noise of Andromeda's own light from the fragile whispers of the background galaxies. By studying the way light is bent, stretched, and amplified in different parts of Andromeda, they can map the hidden distortions caused by its gravity. These distortions form delicate patterns, cosmic fingerprints, that reveal the presence of gravitational lensing at work. Andromeda does not only act as one massive gravitational lens. In certain rare cases, individual stars within the galaxy can serve as miniature lenses, a process known as microlensing. Here is how it works. Imagine a star in Andromeda perfectly lining up with another much more distant star directly behind it. For a brief moment, the closer star's gravity bends the background star's light, making it appear brighter. To us, it looks like a sudden, short-lived flash. These microlensing events are incredibly valuable. They can reveal things we normally cannot see, like rogue planets drifting in the dark, black holes hiding silently, or invisible clumps of dark matter moving through the galaxy. Microlensing has already helped astronomers find planets outside our own solar system, inside the Milky Way. Now, they are pushing further, hoping that by applying the same technique to Andromeda, they might one day detect planets orbiting stars in a galaxy beyond our own. If confirmed, such a discovery would be nothing short of historic, the first known extragalactic planets. That would mean we had extended our hunt for worlds from our local star neighbourhood to an entirely new galaxy. Gravitational lensing is not only useful for spotting hidden galaxies or planets, it can also help answer some of the biggest questions in physics and cosmology. Light passing through a gravitational field does not simply bend. It also slows down slightly due to the way gravity warps space and time. This creates tiny time delays in the arrival of lensed light. If a distant galaxy or quasar, a brilliant flickering object powered by a supermassive black hole, is lensed by Andromeda, multiple images of it may appear in the sky. Each image represents light that has travelled along a slightly different path, and so the flickering patterns of the quasar will reach Earth at slightly different times. By carefully measuring these tiny differences, sometimes only a few hours or days apart, astronomers can refine their calculations of the Hubble constant, the number that tells us how fast the universe is expanding. In this way, Andromeda does not just act as a lens for hidden galaxies, it also becomes a cosmic laboratory, allowing us to test the very laws of physics. While gravitational lensing gives us a natural telescope, there are even bolder ideas in theoretical physics that suggest space itself might contain shortcuts. One of the most famous of these is the concept of a wormhole. The idea comes from Albert Einstein's theory of general relativity. His equations showed that space-time, the fabric of the universe, can bend and curve under the influence of gravity. In rare and extreme cases, the mathematics even allows for the possibility of space-time folding in such a way that two distant points become directly connected through a tunnel-like bridge. This bridge is called an Einstein-Rosen bridge, or more popularly, a wormhole. If a stable wormhole existed between the Milky Way and Andromeda, it could in theory allow instant travel between the two galaxies, skipping the 2.5 million light-years of empty space between them. No rocket fuel, no centuries-long journeys, just a cosmic doorway. Unfortunately, wormholes are not easy to maintain. According to Einstein's equations, a wormhole would collapse almost instantly after forming, snapping shut before anything could travel through. To keep such a passage open, something extraordinary would be required: exotic matter with negative energy. This strange form of matter, unlike anything we have ever observed, would act like an anti-gravity substance. Instead of pulling inward, it would push outward, bracing the wormhole's tunnel against collapse. Without it, a wormhole is like a sand tunnel on a beach, doomed to collapse under its own weight the moment you try to crawl through. Scientists have not yet discovered such exotic matter, though some believe that hints of it may appear in the study of quantum physics. Because we cannot build wormholes, researchers instead look for signs that nature might already have created some. The idea is that wormholes, like black holes, could have unique gravitational effects. Light passing near them might be distorted in unusual ways, different from the bending caused by ordinary gravity. Some have even speculated that certain black holes could actually be wormholes in disguise, hidden gateways to other regions of space. For example, astronomers have carefully studied Sagittarius A star, the supermassive black hole at the centre of our Milky Way, to see if it might show wormhole-like properties. So far, the evidence suggests it is just an ordinary black hole, but the search continues. Even if a wormhole could exist, travelling through one would present enormous challenges. The mouth of a wormhole would likely be surrounded by extreme gravitational forces and deadly radiation. Reaching the entrance could be impossible for any spacecraft. Even if a ship could cross the threshold, the tunnel itself might not be smooth. Theoretical models suggest that the inside of a wormhole could twist, stretch, or compress anything that entered. A traveller might be torn apart before reaching the other side. Time also adds another layer of complexity. In Einstein's theory, space and time are woven together. This means that a wormhole might not only connect two places but also two moments in history. A ship entering one end could emerge not just in another galaxy, but in another time, possibly even before it left. Such scenarios raise strange paradoxes. What if you arrived in the past and prevented your journey from happening? Physics does not yet have clear answers to these puzzles. Wormholes are not the only proposed pathways through space. Another theoretical idea involves cosmic strings, ultra-thin but unimaginably dense filaments of energy that may have formed in the early universe. If two such strings passed near each other at high speeds, they might warp space-time in ways that create shortcuts between distant points. On an even smaller scale, some scientists speculate that tiny wormholes could exist at the quantum level, flickering in and out of existence as part of the fabric of space-time itself. Normally, these are unimaginably small, but some imagine that an advanced civilization could one day learn to stabilize and enlarge them, turning them into usable passages between stars or galaxies. To do this, however, would require harnessing energies far beyond anything humanity has ever achieved. It would mean mastering the very structure of space-time itself. Some scientists propose that our universe may not stand alone but could belong to an immense web of space and time, where unseen tunnels, wormholes, connect to distant galaxies and perhaps even whole universes. Though wormholes remain surrounded by mystery and uncertainty, exploring their possibilities continues to be a vital pursuit in theoretical physics. Whether or not they are ever discovered or built, the very effort to understand them has already deepened our knowledge of gravity, the fabric of space-time, and the fundamental nature of the cosmos itself. When scientists talk about the conditions needed for life, they usually start with the same set of rules no matter where in the universe they are looking. These are the foundations of what we call habitability. First, a planet needs a steady orbit around its parent star. If the orbit is too unstable, the planet might swing wildly closer or farther from the star, causing extreme changes in temperature that would make life nearly impossible. Second, that planet must lie within a special region known as the habitable zone. This is the sweet spot around a star where temperatures are just right for liquid water to exist. Water is considered essential because on Earth, every form of life depends on it. Third, a planet needs to hold on to an atmosphere, one thick enough to protect it and rich enough in chemicals to support complex chemistry, the building blocks of biology. When astronomers study planets inside our own Milky Way, these requirements are fairly well understood. We have discovered many exoplanets, and we can measure whether they meet some of these conditions. But when these same ideas are applied to the Andromeda galaxy, the situation becomes much more complicated. Andromeda lies over 2 million light-years away, far beyond the reach of our current telescopes to directly study individual planets. Instead of observing those planets directly, scientists must take a broader approach. They study Andromeda's stars, its structure, and its history of planet formation. From this, they try to piece together an educated guess about where life might stand the best chance of existing. One of the most important clues comes from the stars themselves. Planets suitable for life cannot form out of just hydrogen and helium, the simplest gases that made up the early universe. They need heavier elements such as carbon, oxygen, and nitrogen, which are vital for creating atmospheres, water, and the molecules of life. These heavier elements, what astronomers call metals, even if they are not metals in the everyday sense, are forged in the hearts of stars and spread through space when those stars die in supernova explosions. In this regard, Andromeda is rich in possibilities. It contains a diverse mix of both young and old stars. The presence of younger stars suggests that planet formation is still ongoing, much like what we see in the Milky Way. This increases the chances that rocky Earth-like planets have formed within habitable zones around those stars. But Andromeda also carries scars of a turbulent past. Over billions of years, it has swallowed up smaller galaxies through a series of mergers and cosmic collisions. These violent events have shaped its structure but also posed risks for planets and life. Galactic collisions can disrupt the orbits of stars, flood regions with harmful radiation, or fling planets out into the cold emptiness of interstellar space. Today, much of Andromeda has settled into a relatively stable state, but certain regions, especially close to its crowded galactic core, or in areas with very high star density, may still be too chaotic to support long-term stable planetary systems. By contrast, the outer spiral arms of Andromeda may offer safer neighbourhoods. Here, stars and planets could orbit in peace for billions of years, giving life the time it needs to develop and evolve. In our own Milky Way, we have already discovered exoplanets that carry water, as well as icy moons orbiting gas giants that may hide oceans beneath thick crusts of ice. These frozen moons remind us that life might not be confined to planets within the traditional habitable zone. Beneath their icy surfaces, internal heating from tidal forces or radioactive decay can keep subsurface oceans liquid, providing potential homes for life. If similar moons exist in Andromeda, they too might serve as cradles for biology. The difficulty, of course, is that detecting such details in Andromeda is vastly harder than in the Milky Way. At such an enormous distance, we cannot yet resolve individual planets well enough to see whether they carry water or atmospheres. For now, it remains out of reach for our technology. Still, scientists allow their imagination to stretch further. What if life in Andromeda does not even follow the same rules as life on Earth? Some researchers speculate that in extreme environments, organisms could be based not on carbon, as we are, but on silicon, which has chemical properties that might allow it to form complex structures. Such life could thrive in places toxic to us. Andromeda contains every kind of star, from faint red dwarfs to massive blue giants, and the planets orbiting them may face conditions very different from anything we know. Some could have thick atmospheres filled with gases such as ammonia or methane. If so, then life might arise there in strange, unfamiliar forms, expanding the possibilities of what we call habitability. In the Milky Way, astronomers searching for life look for biosignatures, chemical markers in exoplanet atmospheres that suggest biological activity. These markers include oxygen, methane, and carbon dioxide, which together can hint at processes that only life can maintain. Finding such signatures in Andromeda would be extremely difficult with today's instruments, but perhaps in the future, new generations of telescopes will be able to analyze exoplanet atmospheres even at such staggering distances. Scientists could then look for atmospheres that seem out of balance, where the mix of gases could not be explained by geology alone and would require biology to make sense. And what if Andromeda does not just contain life, but also civilizations? This is a question that stretches the imagination even further. If an advanced species arose there, it might leave behind signs of its technology. Just as the search for extraterrestrial intelligence, SETI, listens for radio signals in our own galaxy, astronomers could search for artificial signals from Andromeda, radio waves, laser pulses, or even gigantic energy harvesting structures such as Dyson spheres. Such megastructures, if they existed, would give off infrared radiation that might one day be detectable with powerful instruments. But the obstacles are immense. Andromeda is not just far away. It is vast, containing hundreds of billions of stars. Alien civilizations may use technologies or communication methods utterly unlike anything humans can imagine. If so, their signals might pass unnoticed, hidden in plain sight. Another intriguing factor is Andromeda's age. It has been forming stars for billions upon billions of years, far longer than the short span of human history. If intelligent life appeared early in its timeline, it could now be millions of years ahead of us in development. Such a civilization might wield powers beyond our comprehension, or it might have already vanished, leaving behind only echoes of its existence. If one day humanity dares to look beyond the familiar stars of the Milky Way and set its sights on colonizing the mighty Andromeda galaxy, the challenge would be unlike anything we have ever faced. Such an undertaking would not be a single bold leap, but rather a carefully designed and step-by-step journey. It would demand technology far beyond what we currently possess, a vision that stretches across centuries, and a deep mastery of how life can survive in the silent, unforgiving ocean of interstellar space. To prepare for this, visionaries have imagined what might be called the Andromeda Protocol, a grand and theoretical blueprint that would guide humanity's expansion beyond its home galaxy. This protocol would not be a simple instruction manual, but rather a roadmap that spans generations, beginning with the very first scouting missions and ending only when fully self-sustaining colonies flourish in a galaxy millions of light-years away. The very first and most crucial step would be to solve the riddle of travel itself. Andromeda is not just around the cosmic corner, it lies more than 2 million light-years from us. Ordinary rockets, the kind that carried astronauts to the moon, or even robotic explorers to the far planets, would be hopelessly inadequate. Humanity would need intergalactic propulsion systems, machines that can push ships across distances so vast they defy human imagination. To achieve this, breakthroughs would be required in technologies that today seem almost like dreams, engines powered by antimatter, or perhaps even the fabled Alcubierre warp drive, which could in theory bend space itself to shorten the journey. Before a single human ever leaves the Milky Way for Andromeda, the first wave of explorers would not be people at all, but machines. Robotic probes, armed with powerful artificial intelligence, would make the initial leap. These would not be the slow and limited probes we have now, which send radio signals that take minutes or hours to reach Earth. Intergalactic probes would have to think and decide for themselves, acting as scouts in a wilderness so distant that waiting for instructions from Earth would be impossible. Their mission would be to identify habitable worlds, measure the dangers of strange stars and black holes, and map out the resources scattered through Andromeda. To send their findings home, they might use communication methods that border on the speculative, perhaps even quantum entanglement, which would allow information to travel instantly across the cosmic gulf. Once a suitable destination is found, the next stage of the Andromeda Protocol would begin. Self-replicating robotic factories would be dispatched, carrying the seeds of industry within them. Equipped with nanotechnology and advanced three-dimensional printing systems, these factories could mine asteroids, harvest planetary materials, and build the first structures of a future civilization: orbital stations, energy collectors, and shelters capable of enduring harsh alien conditions. Even before humans set foot on a planet, robotic terraformers might begin altering atmospheres, releasing bioengineered microbes that produce oxygen and reshape barren worlds into living environments. Yet, the most difficult question remains: how will people themselves make the journey? If faster-than-light travel is never achieved, the trip to Andromeda could take hundreds of thousands or even millions of years. This means that human travelers would have to live not on a planet, but aboard colossal starships known as world ships, moving civilizations in themselves. A world ship would carry not only people, but entire ecosystems of plants and animals, recycling systems, manufacturing centers, and cultural life. Generations of people would be born, live their lives, and die within the ship, never setting foot on Earth or any planet, yet carrying forward the hope of reaching a new galaxy. Other possibilities exist. If humans perfect the science of deep hibernation, colonists might slumber in dreamless sleep for centuries, only to awaken upon arrival in Andromeda. Or perhaps minds could be copied and transferred into digital form, riding the journey as streams of information within vast artificial intelligence systems. Upon arrival, these minds could be reborn, either through robotic bodies or bioengineered human clones, stepping out onto alien soil as if awakening from a long dream. When humanity finally reaches Andromeda, the true challenge of settlement would begin. The first bases might not be on planets at all, but in orbit, great space stations positioned near worlds rich in resources. These would act as command centers, overseeing exploration and building the foundation for planetary colonies. Over time, networks of such outposts could link together across Andromeda, like stepping stones in a new frontier. Meanwhile, terraforming efforts would continue, slowly shaping alien worlds into places where future generations could breathe without machines. One of the greatest tasks of all would be building ecosystems from nothing. On Earth, nature had billions of years to weave forests, oceans, and breathable skies. In Andromeda, humans would have to create such environments in mere centuries. Artificial biospheres, carefully balanced with genetically engineered food crops and synthetic life, could sustain early settlers. These colonies would have to be self-sufficient, for they would be cut off from Earth for thousands of years, perhaps forever. Without constant contact, these distant human societies would evolve on their own, developing cultures, technologies, and governments that might look nothing like those left behind on Earth. The Andromeda Protocol would also have to prepare for the unknown. If intelligent civilizations already exist within Andromeda, humanity would face the delicate matter of first contact. Such an encounter could lead to cooperation, cultural exchange, and mutual growth, or it could spark conflict on a scale larger than anything our species has ever known. Rules for diplomacy, cautious exploration, and respect for other beings would be essential. Alongside this, defense strategies would be needed, not only against potential hostile civilizations, but also against the raw dangers of space itself: asteroids, deadly gamma-ray bursts, supernovae, and even rogue black holes drifting silently between stars. Despite the almost unimaginable difficulties, the colonization of Andromeda would stand as one of the greatest turning points in human history. It would transform us from a species bound to a single galaxy into an intergalactic civilization. To achieve it would be to test every boundary of human creativity, courage, and endurance. It would not simply expand our place in the universe, it would change what it means to be human. We would carry life across the void between galaxies, building bridges where once there was only darkness, and proving that imagination and determination can conquer even the greatest of cosmic distances. One of the greatest achievements of modern astronomy, and perhaps one of the most exciting triumphs of human curiosity, has been the steady improvement of telescopes. For thousands of years, our ancestors lifted their eyes toward the heavens, watching the faint shimmer of stars and the cloudy glow of the Milky Way. They told stories about the constellations and imagined gods and heroes living among them. But today, with our enormous telescopes, both on Earth and in space, we no longer only imagine. We observe, measure, and uncover truths about galaxies that lie millions of light years away. Among all these galaxies, none captivates our imagination as much as Andromeda, the great spiral neighbour of the Milky Way. Telescopes are, in essence, the eyes of humanity stretched across the vastness of space. The larger the telescope, the more light it can collect, and the clearer the image it produces. The new generation of giant ground-based telescopes is nothing short of breathtaking. In the deserts of Chile, where the skies are clear and dark, scientists are building the extremely large telescope, often shortened to ELT. As its name suggests, this machine is truly gigantic. It will possess a mirror more than 30 meters across, wider than a school playground. With such a colossal mirror, the telescope will be able to gather light from the faintest objects, allowing astronomers to see deeper into space than ever before. But the ELT is not only about size, it also uses a clever technology known as adaptive optics. Normally, when light from a distant star travels through Earth's atmosphere, it becomes distorted, much like the ripples that blur objects when seen through water. Adaptive optics solves this problem by constantly adjusting tiny mirrors to counteract the turbulence of the atmosphere. The result is astonishing. Images so sharp and detailed that they nearly rival those captured by telescopes floating above Earth in space. Yet even the most advanced ground-based telescope still has one disadvantage: the atmosphere itself. No matter how good our corrections, the air around Earth always introduces some limitations. That is why astronomers also rely on space telescopes, which orbit high above the planet where the sky is perfectly clear. One of the most famous of these is the Hubble Space Telescope. For more than 3 decades, Hubble has been our window to the cosmos, sending back jaw-dropping images of distant galaxies, including Andromeda. Its photographs have revealed the spiral arms, the clusters of stars, and the glowing clouds of gas with astonishing beauty. And then came an even more powerful eye in the sky, the James Webb Space Telescope, known as JWST. Unlike Hubble, which mainly observed invisible light, Webb is designed to see in the infrared spectrum. Infrared light is especially valuable because it can slip through cosmic dust, unveiling stars and planetary systems hidden behind dark veils. With this new ability, Webb has opened doors to secrets once beyond our reach. By studying infrared emissions, astronomers can now explore the cooler corners of the universe, distant exoplanets, regions where stars are just beginning to form, and galaxies so ancient that they shine from the dawn of time. In the case of Andromeda, Webb has already provided fresh insights into the movements of gas and the distribution of stars across its disk. Yet, astronomy is not limited to visible or infrared light. The cosmos speaks in many languages, and one of the most powerful is radio. Soon, the Square Kilometre Array, a vast network of radio antennas spread across continents, will become the most advanced radio observatory in the world. Unlike optical telescopes, radio telescopes can operate during the day or even under cloudy skies. They will help scientists map how Andromeda's stars and clouds of gas drift over time, giving us a dynamic view of the galaxy's evolution. Light itself holds many secrets, and one of the most valuable techniques in astronomy is called spectroscopy. Just as a prism splits sunlight into a rainbow, a spectrograph breaks starlight into its component wavelengths. Hidden in those patterns are clues to the temperature, speed, and chemical makeup of stars and gas. Instruments like those at the Keck Observatory in Hawaii use this method to peer into Andromeda's core, measuring the speed of its stars and revealing the existence of a massive black hole at its centre. Spectroscopy even allows astronomers to distinguish different generations of stars, piecing together how Andromeda's stellar population has grown and evolved over billions of years. Another revolution in astronomy came with the Gaia Space Observatory, a mission of the European Space Agency. Gaia has mapped the positions and motions of more than 1 billion stars in the Milky Way with breathtaking accuracy. Now, similar techniques are being applied to Andromeda. By carefully tracking individual stars, scientists can reconstruct the galaxy's past encounters, identify stellar streams left behind by smaller galaxies that were absorbed, and even predict how Andromeda will change in the future. The scale of these surveys is immense. The Vera C. Rubin Observatory, for example, is creating images of millions of galaxies, producing more data than a human mind could ever process alone. To handle this flood of information, astronomers rely on artificial intelligence. Machine learning algorithms scan the skies for hidden patterns, faint tidal streams, and subtle hints of gravitational interactions. In Andromeda, these tools are already helping uncover evidence of ancient mergers with smaller galaxies. But our exploration of the universe is not limited to light and radio waves. In recent years, an entirely new messenger has joined the conversation: gravitational waves. These are ripples in the very fabric of spacetime, first predicted by Albert Einstein. Observatories such as LIGO in the United States and Virgo in Europe have already detected waves from the collisions of black holes and neutron stars. In the future, the proposed space mission LISA, the Laser Interferometer Space Antenna, may detect signals from supermassive black holes at the centers of galaxies. If the enormous black hole at the heart of Andromeda were to merge with another, the resulting ripple in spacetime could be strong enough to be detected across the cosmos. Another frontier is neutrino astronomy. Neutrinos are ghostly, nearly massless particles that pass through matter, almost without interacting. They are born in extreme environments, supernova explosions, the surroundings of black holes, or the hearts of distant galaxies. On the frozen continent of Antarctica, the IceCube Neutrino Observatory has already captured high-energy neutrinos streaming from space. With future improvements, these detectors may reveal hidden activity in Andromeda's core, offering a glimpse into processes invisible in any other way. The journey of discovery does not end here. Future missions are already on the drawing board. The Habitable Worlds Observatory and Le Voir, the large ultraviolet optical infrared surveyor, promise even sharper views of distant galaxies and, perhaps, the first detection of habitable planets around stars in Andromeda. These observatories will probe questions at the heart of human wonder. How do galaxies form? Do other planets harbour life? And are we alone? Yet, for all that we know, Andromeda still keeps many mysteries locked away. One of the deepest puzzles lies in its invisible companion, dark matter. Like the Milky Way, Andromeda appears to be wrapped in a vast halo of this unseen substance. But observations of its satellite galaxies suggest that the dark matter is not evenly spread. Some regions are denser than expected, while others are thinner. This uneven distribution raises profound questions about whether our current theories of dark matter, or even of gravity itself, are complete. Andromeda also holds mysteries in its structure. Its spiral arms, though beautiful, do not behave like those of the Milky Way. Some scientists think a past collision shaped them, while others believe they formed from processes inside the galaxy's own disk. Telescopes like Hubble, and soon the Nancy Grace Roman Space Telescope, are working to map these arms in ever greater detail, hoping to piece together their story over billions of years. Another enigma lies in Andromeda's unusually high number of globular clusters, dense balls of ancient stars bound together by gravity. More than 500 have been identified, which is more than double the number in our Milky Way. Some astronomers believe these clusters are the remnants of dwarf galaxies swallowed long ago, while others think Andromeda was simply more efficient at producing them. Studying their chemical composition may reveal secrets about the galaxy's violent past. And then there is the great mystery at its core, Andromeda's supermassive black hole. Despite the Milky Way and Andromeda being similar in size, the black hole at Andromeda's centre is much larger. Why is this so? How did it grow so enormous, and what role has it played in shaping the galaxy around it? Future radio and X-ray observatories may finally provide answers. The future of Andromeda is also our own. In about 4 billion years, the Milky Way and Andromeda will collide. The thought of such a titanic event might sound terrifying, but it is not necessarily a tale of destruction. When galaxies merge, their stars usually pass by one another without colliding directly, because the distances between stars are so vast. What does collide are their clouds of gas, triggering bursts of star formation in a cosmic rebirth. Some worlds may be destroyed, but others may be born anew. Entire planetary systems may find themselves cast adrift as rogue planets, wandering the galaxy alone yet still carrying the potential for life. This raises the most profound possibility. Life itself may endure and even thrive in the chaos of galactic collisions. Just as Earth's most resilient microbes can survive in boiling vents or frozen wastelands, life elsewhere may persist through upheavals we can barely imagine. A new galaxy, born from the union of Andromeda and the Milky Way, may carry with it seeds of life scattered far and wide. And perhaps, hidden among Andromeda's stars, there may already be civilizations far older and wiser than our own. Some scientists have speculated about the existence of megastructures, vast artificial constructions built by advanced beings. A Dyson sphere, for instance, could surround a star to harvest nearly all of its energy. Other concepts imagine ring worlds or stellar engines capable of moving entire suns. None of these have been detected, but astronomers search the skies for strange signatures, stars that shine less in visible light but glow more in infrared, or unusual stellar motions that cannot be explained by gravity alone. If such a discovery were ever made in Andromeda, it would change human history forever. Even if no alien architectures are found, the act of searching deepens our understanding of what is possible. Each unanswered question, each puzzle about dark matter or black holes, each whisper of a gravitational wave or flicker of a distant star pushes humanity to expand its knowledge. Imagine standing at the very edge of Earth's atmosphere, where the blue sky fades into blackness and gravity loosens its grip. One more step and you're no longer bound to our world. You've crossed into space, a place of endless silence and chilling mystery. But here's the real question. What comes after that? What lies beyond the edge of space? Is it just more stars, more galaxies? Or is there something truly that defies the rules of physics, time, and imagination? Before we begin, let us know where in the world you're watching from and what time it is for you right now. Drop it down in the comments below and settle in for a fascinating journey through space. To truly understand the mind-blowing discoveries made by the James Webb Space Telescope, also known as JWST, we first need to travel all the way back to the very beginning of everything, the birth of the universe itself. This incredible moment is known as the Big Bang. But don't picture a typical explosion, like fireworks or a bomb. The Big Bang was something entirely different. It was the sudden and unbelievably fast expansion of the universe from a single point that was unimaginably small, scorching hot, and densely packed with energy. This cosmic event happened around 13,800 million years ago, and it wasn't just the beginning of the universe. It was the moment when space, time, and all matter burst into existence. In the first few seconds after the Big Bang, the universe was like a stormy sea of energy, filled with tiny particles zipping around in every direction. It was so incredibly hot, hotter than anything we can imagine, with temperatures reaching trillions of degrees, that atoms couldn't even form. Everything was pure chaos, with no stars, no planets, and no galaxies, just glowing, blinding energy. For hundreds of millions of years, the universe stayed in this strange state. Slowly but steadily, it expanded and cooled down. Then, something extraordinary happened. Around 400 million years after the Big Bang, the first atoms came together, mainly hydrogen and helium. These simple gases were pulled together by the force of gravity, and as they clumped together, they heated up and ignited the very first stars. These newborn stars didn't shine alone. They gathered into the first primitive galaxies, lighting up the darkness of space and creating what scientists call the cosmic dawn. This was a magical era when the universe was beginning to form its first structures, and this is exactly the moment in time that the James Webb Space Telescope is now peering into. It's capturing breathtaking pictures and precious data from when the first galaxies were just starting to glow, helping us uncover the mysteries of our universe's earliest days. The James Webb Space Telescope is unlike anything humans have ever built. It was launched into space on the 25th of December 2021, a cosmic Christmas gift to humanity. But JWST doesn't orbit the Earth like most satellites. Instead, it travels around the Sun, parked at a special spot called the Second Lagrange Point, or L2. This point is about 1 million miles away from Earth. It was carefully chosen so the telescope could stay stable and far away from Earth's heat and light, giving it a crystal clear view of the universe. What makes JWST truly special is its ability to see the universe in a kind of light our eyes can't detect: infrared light. While visible light is blocked by clouds of cosmic dust, infrared light can sneak through, revealing hidden stars, galaxies, and other objects that other telescopes can't see. This is especially important for studying the oldest and most distant objects in space. As the universe expands, the light from faraway galaxies gets stretched into longer, redder wavelengths. This stretching, called the cosmological redshift, turns visible light into infrared light. Because JWST is designed to detect this faint, stretched-out infrared glow, it can look farther into space, and farther back in time, than any telescope before it. It's like having a time machine that shows us what the universe looked like more than 13 billion and 500 million years ago, just a few hundred million years after everything began. When JWST sent back its very first images, scientists were amazed. The telescope had looked deep into the ancient past and captured pictures of galaxies forming only a few hundred million years after the Big Bang. This was the universe's baby stage, and yet it was already full of surprises. Astronomers expected to find only a few tiny galaxies, but they found far more than they had imagined. These early galaxies came in all kinds of strange shapes and sizes, much different from what scientists expected. It turned out that the early universe was more lively, more crowded, and more chaotic than anyone had guessed. One of the most exciting things JWST discovered was the presence of proto-galaxies. These were the first clumps of stars that would eventually grow into the massive galaxies we see today. But they didn't look neat or orderly. Instead of smooth spirals or round shapes, these early galaxies were messy, clumpy, and wild. New stars were being born at an incredible pace, with entire clusters lighting up in bursts of energy. This discovery challenged older ideas that galaxy formation was slow and gentle. JWST showed us that the early universe was full of energy and drama, changing our entire view of how the cosmos took shape. JWST also brought us closer to finding the very first stars ever formed, called Population 3 stars. These stars were unlike anything we see in today's skies. They were made from the purest ingredients left behind by the Big Bang, mostly hydrogen and helium, without any heavier elements like carbon or oxygen. Because of this, scientists believe these stars were huge, far larger than our Sun, and burned extremely hot and bright. But they lived fast and died young, burning up their fuel quickly and exploding in massive blasts called supernovae. Some of these explosions were so powerful that they became rare events called pair instability supernovae, the most intense explosions in the universe. When these ancient stars exploded, they scattered heavier elements into space, which later helped form new stars, planets, and even the building blocks of life. By uncovering clues about these long-gone giants, scientists are slowly solving the mystery of how the universe grew from simple beginnings into the rich, complex place we live in today. But JWST doesn't stop at looking into the distant past. It is also helping scientists understand two of the biggest puzzles in the universe: dark matter and dark energy. These strange forces make up about 95% of everything in the universe, yet we can't see or touch them. Dark matter doesn't shine or give off any kind of light, but we know it's there because of the way it pulls on galaxies with its powerful gravity. JWST helps detect dark matter by watching how it bends the light from galaxies behind it, a trick of nature called gravitational lensing. This lets astronomers map where dark matter might be hiding and figure out how it helps shape the structure of the universe. Then there's dark energy, which is even more mysterious. It's a force that's causing the universe to expand faster and faster over time. By measuring how quickly galaxies are racing away from us, JWST gives scientists new clues about how dark energy works. These discoveries are incredibly important, because they might help answer one of the biggest questions of all. Will the universe keep expanding forever, or will it eventually stop and collapse? JWST is also on the hunt for something even closer to home: life beyond Earth. One of its most exciting missions is to study planets outside our solar system, known as exoplanets. Some of these distant worlds may have just the right conditions to support life. Using its advanced tools, JWST can examine the gases in a planet's atmosphere and look for special chemical signs that might hint at life. If it finds water vapor, That could mean the planet has clouds or even rain. If it finds methane, it might come from volcanic activity, or maybe even microbes. And if it finds lots of oxygen, scientists will start to wonder, could there be plants or alien life forms producing it? Just imagine the moment when we finally find proof that we're not alone in the universe. That would change everything we thought we knew. However, the James Webb Space Telescope is much more than a camera in space. It is a window into the deepest mysteries of time and space. It has already confirmed some theories and shattered others. One of its most surprising discoveries is that fully formed galaxies seem to appear much faster than anyone expected. According to older theories, it should have taken billions of years for galaxies to slowly grow and develop. But JWST is showing us galaxies that came together in a cosmic blink of an eye. This means scientists might need to rewrite major parts of our understanding of the universe. One of the most surprising discoveries made by the James Webb Space Telescope has to do with the huge black holes found in the centers of some of the oldest galaxies ever seen. According to what scientists believed before, these black holes should have been small, because there simply hadn't been enough time in the early universe for them to grow so large. But the James Webb Space Telescope has spotted black holes that are much bigger than expected. This means that black holes might form and grow much faster than scientists ever imagined. It's a mystery that challenges everything we thought we knew about how black holes begin and how they evolve over time. These strange and unexpected findings show us that the universe is still full of secrets, and thanks to the incredible technology of the James Webb Space Telescope, we're only beginning to discover what's out there. Now, let's pause for a moment and take a closer look at the amazing machine behind these discoveries. The James Webb Space Telescope, often called JWST, is one of the most advanced tools humanity has ever sent into space. It has a massive mirror covered in gold, which stretches more than 21 feet across. That's about the size of a small house. This mirror was specially designed to collect the faintest rays of infrared light coming from faraway galaxies. But what makes it even more fascinating is how it's built, not as one single piece, but from 18 golden hexagon-shaped segments. These pieces unfolded like petals in space, creating a beautiful pattern that looks like a giant golden flower blooming in the darkness. But JWST's power doesn't stop with its giant mirror. It's loaded with advanced instruments, like powerful cameras and spectrographs. These tools don't just take pictures, they analyze light in incredible detail. They can break down the light from stars and galaxies that are millions or even billions of light years away. By studying this light, scientists can learn what stars are made of, how they're moving, how old they are, and much more. It's like doing archaeology, but instead of digging into the Earth, scientists are digging into the ancient history of the universe, uncovering stories written in light that has travelled across space and time for billions of years. The James Webb Space Telescope is more than just a brilliant piece of engineering, it's also a symbol of international teamwork. While the project was led by NASA, the space agency of the United States, two other major partners helped make it possible: the European Space Agency and the Canadian Space Agency. The European Space Agency provided important scientific instruments, and the Canadian Space Agency added high-tech equipment and funding to help the mission succeed. This global partnership shows what humanity can achieve when we work together. Scientists, engineers, and dreamers from all over the world joined forces to build something truly extraordinary. The JWST proves that when people unite around a common goal, like exploring the universe, we can reach new heights and make discoveries beyond imagination. Looking at what JWST has already found, it's impossible not to feel excited about what's still to come. The telescope is gathering so much valuable data that scientists will be studying it for many years into the future. These discoveries will inspire new generations of astronomers and scientists to keep asking questions and to keep pushing the boundaries of what we know. And JWST is just the beginning. In the coming years, more amazing space missions are getting ready for launch. One of them is the Nancy Grace Roman Space Telescope, which will give us an even wider view of the cosmos. Another is the European Extremely Large Telescope, a giant observatory being built on Earth, which will give us incredibly sharp views of distant galaxies. All of these tools will work together, helping us uncover even more secrets about the universe, how it started, how it works, and where we fit in. These efforts are about more than just science. They're also about human curiosity. the drive to understand where we came from, and the deep connection we feel with the stars above. Every mission like JWST helps us feel a little closer to the universe and a little more connected to each other. The James Webb Space Telescope has already changed the way we see the universe. By looking back over 13.5 billion years into the past, it's giving us a view of the cosmos as it was just after the Big Bang. The universe is unimaginably vast, stretching out farther than our minds can fully grasp. For thousands of years, people have looked up at the night sky, wondering where it all began and how it came to be. Over the last few centuries, scientists have worked tirelessly to solve the mysteries of the cosmos. They've asked big questions. How did the universe start? What has happened to it over time? One of the most fascinating clues to answering these questions comes from something called redshift. Though it might sound like a science fiction term, redshift is a real and powerful phenomenon that helps scientists understand how the universe has been expanding ever since it was born. To understand what redshift is and why it matters, we first need to talk about light. Yes, the same light that shines from a flashlight or the sun. Light moves in waves, just like the ripples you see when you toss a stone into a calm pond. These waves come in many different lengths. Some waves are short and others are long. The length of a light wave is what gives it its colour. Shorter waves look blue or violet, while longer ones appear red. Now, here's where things get exciting. When scientists study the light coming from stars and galaxies, they look very closely at those waves. By measuring how long or short they are, they can learn all sorts of things, like what the object is made of, how far away it is, and even how fast it's moving. Redshift happens when those waves of light get stretched out during their long journey through space. When the light's stretched, its waves grow longer and begin to shift toward the red side of the colour spectrum. That's why we call it redshift. Think of it like this. Imagine a car zooming past you. As it comes closer, the sound it makes is high-pitched. But as it speeds away, the sound drops to a lower pitch. This is called the Doppler effect. And it doesn't just happen with sound, it also happens with light. When a star or galaxy moves away from us, the light it gives off stretches, and its colour shifts toward red. In space, this redshift tells us that galaxies are moving away from us, and not just a little bit. Some are racing away at incredible speeds, and the farther away they are, the faster they seem to be fleeing. That's where redshift becomes incredibly important. By measuring how much the light from a galaxy is redshifted, scientists can figure out how fast that galaxy is moving and how far it is from Earth. This discovery changed everything we thought we knew about the universe. Back in the early part of the 20th century, in the year 1929, an American astronomer named Edwin Hubble made a groundbreaking observation. While studying distant galaxies through his telescope, he noticed something truly astonishing. Every galaxy he looked at seemed to be moving away from Earth. And not only that, the farther away the galaxy was, the faster it was moving. From this, Hubble came up with what is now called Hubble's law, which says that the universe is expanding. This means that space itself is stretching, like dough rising in an oven. The galaxies aren't flying through space, they're being carried farther apart as space itself grows. This was one of the biggest clues that helped support the Big Bang theory. The idea that the entire universe began from one incredibly hot and dense point around 13.8 billion years ago. Since that moment, the universe has been growing, and redshift is one of the ways we can track that growth. Whenever scientists detect redshifted light coming from a galaxy, they can estimate how far away that galaxy is, and more incredibly, how long ago that light started travelling toward us. In fact, the more redshifted the light, the longer it has been journeying through space. This means that redshift doesn't just tell us about distance, it lets us look back in time. Imagine this. When we observe a galaxy that is billions of light years away, we're seeing it as it was billions of years ago. The light from that galaxy has taken a very, very long time to reach us, sometimes more than 13 billion years. So, in a way, telescopes are like time machines. When we detect strong redshift, we're not just seeing how far away something is, we're seeing how it looked when the universe was still young. The galaxies with the highest redshifts, the ones furthest from us, show us what the universe looked like only a few 100 million years after the Big Bang. These galaxies are incredibly valuable to scientists because they offer a rare peek into the universe's early days. Back then, everything was different. Space was hotter, denser, and packed with more raw materials like gas and dust. The first stars and galaxies were just beginning to form, lighting up the cosmos for the first time. Studying these early galaxies is like peeling back the layers of time. Every new discovery helps us understand how the universe changed from a tiny, blazing hot point into the gigantic and complex structure we see today. To study these faraway galaxies and their redshifted light, astronomers use extremely powerful telescopes. The Hubble Space Telescope, launched in the year 1990, and the newer James Webb Space Telescope, launched in December of the year 2021, have been essential for this mission. These space telescopes can see incredibly faint light coming from galaxies that are located billions of light years away. Light so dim and ancient that no ordinary telescope could ever detect it. When scientists examine the light from these distant galaxies, they measure exactly how much it has been stretched. The more it's stretched, the higher the redshift, and the older the light is. This allows astronomers to map out the history of the universe, piece by piece, light by light. So what do we see when we look at these high redshift galaxies from the early universe? Surprisingly, they look nothing like the big, beautiful spiral or elliptical galaxies we see today. These early galaxies were small, clumpy, and often strange in shape. They were still being built, still forming stars and still gathering gas and dust to grow. Many of them were crashing into each other and merging, huge cosmic events that caused bursts of star formation and reshaped their structures. Over billions of years, these early galaxies slowly grew larger, calmer, and more organized, eventually turning into the majestic galaxies we see in the modern universe. But by studying them in their youth, through the redshifted light they left behind, astronomers can learn how galaxies grow up, how stars are born, and how the universe itself has evolved over time. One of the most exciting things about studying galaxies that are extremely far away is that they let us look deep into the past, into a time when the very first stars in the universe were born. These first stars are called population 3 stars, and they are unlike any stars we see today. Scientists believe they formed shortly after the Big Bang, a time when the universe was still incredibly young and everything was made mostly of two very simple gases, hydrogen and helium. Back then, the universe was a quiet, dark place, filled only with these gases floating in all directions. But slowly, over millions of years, gravity started to pull the gases together, squeezing them tighter and tighter. Eventually, this pressure caused the gas clouds to collapse, and that's when the first stars burst into life. These early stars were massive, many times larger than our Sun, and they burned much hotter and brighter than anything we see today. But they were missing something important. They didn't have heavier elements like carbon, oxygen, or nitrogen, which are essential for creating life. Instead, they were made almost entirely of the two lightest elements, hydrogen and helium. When these giant stars finally reached the end of their lives, they exploded in powerful blasts called supernovae. These explosions were incredibly violent and spread newly created heavier elements into space, elements that didn't exist before. It was only through the deaths of these stars that things like carbon, oxygen, and iron were made. These elements later came together to form new generations of stars, planets, and eventually even life, including us. In many ways, the birth and death of these first stars were some of the most important events in the universe's history. They were like the first building blocks in the construction of everything that followed: galaxies, solar systems, Earth, and all living things. By studying these very old and distant galaxies, scientists are slowly uncovering the story of how the simple early universe transformed into the complex and beautiful place we see today. One of the most fascinating periods in this early cosmic story is called the Epoch of Reionization. This was a time when the universe went through a dramatic change. Before this era, the universe was dark and cloudy, and light couldn't travel very far. But when the first stars started to shine, their light began to ionize the surrounding gas, basically giving energy to the atoms and breaking them apart. This changed the gas from being thick and foggy to becoming clear and see-through. Suddenly, light could move across the universe more freely. This important moment helped shape the clear, star-filled sky we see today. Now, you might be wondering, how do we know all this? We weren't there after all. The answer lies in something called redshift. Redshift is what happens to light from faraway galaxies as it travels across the vast distances of space. As this light moves toward us, it stretches out and shifts to a redder colour because the universe is expanding. The farther the galaxy, the more stretched out the light becomes, and the older the image we're seeing. So when astronomers look at galaxies with very high redshift, they are actually looking back in time. They are seeing what those galaxies looked like billions of years ago when the universe was young. This isn't time travel like in science fiction movies, where people hop into machines and fly into the past. Instead, it's more like reading an ancient message carried by light that's been on a journey for billions of years. This light is like a time capsule. It holds clues about how the universe looked when the first stars and galaxies were just beginning to form. By studying it carefully, scientists can piece together the story of how the universe evolved, from a simple, empty space full of gas to a place filled with stars, planets, and the potential for life. It's amazing to think that the light we see today from faraway galaxies, like the Andromeda galaxy or even more distant ones, has travelled through space for millions or even billions of years before finally reaching Earth. Every photon of light that hits our telescopes carries a piece of cosmic history. This idea makes us realise just how vast and old the universe is and how small we are in comparison. The study of redshift and ancient galaxies is one of the most exciting fields in modern science. In the next few decades, powerful new telescopes like the James Webb Space Telescope may help us learn even more. We could discover how the very first stars and galaxies came to be, how black holes formed in the early universe, and maybe, even more thrilling, if there are signs of life beyond Earth. Galaxies are enormous collections of stars, gas, dust, and something mysterious called dark matter. All of these things are held together by one powerful force, gravity. Galaxies come in many different shapes and sizes. Some, like our own Milky Way, are spiral-shaped, with long, curved arms spinning around a central core, kind of like a cosmic pinwheel. Others are shaped more like smooth, rounded balls. These are called elliptical galaxies, and they often contain older stars and look less detailed. Then there are irregular galaxies, which don't follow any clear shape at all. These often got their strange appearance from violent crashes or close encounters with other galaxies. But galaxies aren't just floating randomly through space. They are the main building blocks of the universe. Inside these giant star cities, new stars are born, live bright lives, and eventually die in dramatic ways, like exploding in powerful blasts called supernovae. These life and death cycles help shape the future of galaxies and create the ingredients needed to form new stars and planets. Galaxies also contain planets, moons, comets, asteroids, and all the other things that make up our known universe, including our own home, Earth. When it comes to size, galaxies can vary tremendously. Some are relatively small, with just a few billion stars. Others are incredibly huge, containing hundreds of billions or even trillions of stars. Our galaxy, the Milky Way, is somewhere in the middle. It holds about 200 billion stars. And here's the truly mind-blowing part. Scientists believe there are billions of galaxies scattered across the universe that we can see with telescopes. Each one has its own story, its own journey, and its own clues about how the universe began and how it continues to change over time. Every single galaxy, big or small, plays a part in this cosmic adventure. Experts think that galaxies started to form only a few 100 million years after the Big Bang, which is the term used to describe the powerful beginning of the universe. This incredible event is thought to have happened around 13.8 billion years ago. At that time, the universe was extremely hot, dense, and full of energy. The only elements around were hydrogen and helium, which are the lightest and simplest elements known. As the universe began to cool down, gravity started pulling together huge clouds of gas and dust. These clouds got denser and eventually collapsed in on themselves, creating the first stars. Over time, these newborn stars began to group together to form the very first galaxies. But these early galaxies were very different from the ones we see today. They were smaller, made mostly of hot, young stars, and had very few of the heavier elements that come from older stars. Even so, these early galaxies laid the foundation for the larger, more complex ones that would grow over billions of years. Since the time of the Big Bang, the universe has been expanding, stretching out in all directions. Galaxies have slowly drifted farther and farther apart. What's even more surprising is that this expansion is not slowing down, it's actually speeding up. Scientists don't fully understand why, but it's one of the biggest mysteries in cosmology today. Meanwhile, galaxies have continued to grow and change. They crash into each other, merge, and form even bigger and more detailed structures. These cosmic interactions have helped shape the beautiful, massive galaxy clusters and star systems we see all around us today. But in recent times, a powerful new telescope has completely changed the way we think about all of this. The James Webb Space Telescope, often called JWST, has made some discoveries that have stunned scientists around the world. One of the most surprising discoveries is the finding of very old galaxies that seem to have formed much earlier than anyone ever thought possible. According to earlier theories, the first galaxies should have started forming around 400 to 500 million years after the Big Bang. That's because the universe needed time to cool down before stars could begin forming from the leftover gas. But JWST has found galaxies that may have appeared even earlier, just a few 100 million years after the universe began. Even more shocking, these galaxies look mature. They have organized shapes and show signs of active star formation. This suggests that they came together much faster than we previously believed. One of the most jaw-dropping discoveries made by JWST was a galaxy that appears to have formed only 230 million years after the Big Bang. This is far sooner than anyone expected. For a galaxy to form in such a short time, the conditions in the early universe must have been very different from what we imagined. It hints that the process of galaxy formation might have been much quicker and more efficient, or that we're missing some key piece of the puzzle. These findings are extremely important because they challenge everything we thought we knew about how galaxies and the universe came to be. If galaxies could form this fast, it means the early universe may have had special conditions, perhaps unknown types of matter, faster star-making processes, or chemical mixtures we haven't yet identified. It forces scientists to go back and rethink their models of the early universe. And what's even more fascinating is that these ancient galaxies seem to be bursting with activity. They're full of young stars being born at a very fast rate. Scientists had believed that in the early universe, star formation would be slow. That's because there weren't yet enough heavy elements, like carbon and oxygen, which are created in the cores of dying stars and are needed to form new ones. But if these early galaxies are already forming stars so quickly, it could mean two things. Either the conditions for starbirth were better than we thought, or we were wrong about how the first stars came into being in the first place. Some of the galaxies discovered by the James Webb Space Telescope are turning out to be far larger and more complicated than anyone ever expected. And what's even more surprising, these galaxies are incredibly old, dating back to a time not long after the universe first began. Scientists always thought that the earliest galaxies were small, rough, and not very developed. They believed that it would take billions of years for galaxies to become large and filled with different types of stars. But JWST has revealed a very different story. These ancient galaxies already have beautiful, detailed shapes, some even with spiral arms and well-organized structures. They are home to all kinds of stars, not just one type, showing a surprising variety and richness. This completely challenges the older view that early galaxies were simple and messy. It's like opening a history book and suddenly finding a chapter that was never supposed to exist. These discoveries have raised many new questions, especially about two of the biggest mysteries in science: dark matter and dark energy. Together, these invisible forces make up about 95% of all the mass and energy in the universe. Yet even today, scientists still don't fully understand what they are or how they work. The strange shapes and fast formation of these early galaxies hint that dark matter might have played a much bigger role than anyone realized. Perhaps it acted like a hidden framework, pulling normal matter together faster and helping galaxies form more quickly. Dark energy, which is thought to be driving the universe's expansion, might also have been stretching space in ways we never expected. The more we discover, the more it feels like we've only just begun to uncover the universe's secrets. These recent findings are so important that they could completely rewrite what we thought we knew about the early days of the cosmos. Old theories are starting to fall apart, and scientists will now need to come up with new ideas to explain how these massive galaxies appeared so quickly after the Big Bang. This is a thrilling moment in the world of science because it means that in the next few years, we could uncover more discoveries that totally change how we think about the universe's beginnings. Because of what JWST has found, researchers now have to take a fresh look at how galaxies form and evolve. That means rethinking ideas about dark matter, how stars are born, and how the entire structure of the universe developed when it was still very young. The evidence points toward an era filled with activity, mystery, and rapid changes, especially during the first few 100 million years after the Big Bang. That early time, once thought to be quiet and slow-moving, now seems to have been bursting with energy and transformation. These discoveries open the door to a whole new level of exploration. Scientists may soon learn more about how early galaxies interacted with each other. Were they more connected than we ever imagined? Did they grow by merging together, or by feeding off the energy of nearby stars and gas? These are the kinds of questions JWST is helping to answer. Another area of interest is the role of supermassive black holes, giant objects thought to lie at the heart of most galaxies. These mysterious giants might have helped shape galaxies right from the start, acting like cosmic engines that influenced how fast galaxies grew and how stars formed around them. One of the most mind-blowing discoveries in modern astronomy came from the observation of a distant galaxy known as GNZ 11. This galaxy is located an astonishing 13.4 billion light-years away from Earth. That means we are seeing it as it looked only 400 million years after the Big Bang, at a time when the universe was still extremely young, just beginning to light up with stars. This makes GNZ 11 one of the very earliest galaxies ever seen by human eyes. What truly amazed scientists was how huge this galaxy already was, even though it had only existed for a relatively short time. You would expect such a young galaxy to be small and still forming, but GNZ 11 turned out to be packed with stars, hundreds of billions of them, making it as massive as the Milky Way, which is more than 13 billion years old and has had plenty of time to grow and evolve. Seeing such a large and complex galaxy so early in cosmic history was like finding a fully grown tree in a place where only tiny sprouts should exist. But there was more. GNZ 11 wasn't just big, it was growing incredibly fast. The speed at which it was forming stars and building its structure was far greater than what scientists thought possible for such an early point in the universe's history. This rapid growth suggests that the galaxy had access to a massive supply of gas, the raw material that stars are made from, right when the universe was still in its baby years. This discovery shook the foundations of everything astronomers thought they understood about how galaxies form. For a long time, the belief was that galaxies start small and slowly grow bigger over billions of years. But GNZ 11 didn't follow the rules. It seemed to skip ahead in cosmic time, becoming enormous and complex long before it was supposed to. Even more surprising was that GNZ 11 wasn't alone. Other ancient galaxies, also located billions of light years away, showed the same strange behaviour. They were enormous, filled with stars, and some had detailed, organised structures like spirals or bulges. A few even had supermassive black holes, giant objects with the mass of millions or even billions of suns right at their centres. This was a big shock because scientists thought these kinds of galaxies and black holes were something that only developed much later in the universe's history. The big mystery now was, how could galaxies grow so large and become so structured so quickly at a time when the universe was still just a few 100 million years old? One possible explanation is a process scientists call direct collapse. Usually, galaxies form gradually as gas clouds pull together under gravity, forming stars over millions of years. But with direct collapse, an enormous cloud of gas might have skipped the usual steps and collapsed quickly into a galaxy, or even a giant black hole. This shortcut would allow a galaxy to grow very fast, almost as if it had taken a leap through time. Another idea is that the conditions in the early universe were very different from what we see today. Back then, The universe was wild and energetic, filled with intense radiation, extreme heat, and vast clouds of gas. These chaotic conditions may have caused gas to clump together more quickly, speeding up the formation of stars and galaxies. It's like a cosmic storm that helped shape entire galaxies faster than anyone expected. Some scientists also think that dark matter played a key role. Dark matter is an invisible type of matter that doesn't emit light, so we can't see it, but it still has mass and gravity. That gravity might have acted like a powerful magnet, pulling in gas and helping galaxies come together much more quickly. If large amounts of dark matter were gathered in one area, they could have acted as a framework or skeleton around which a galaxy could form in record time. One of the most astonishing features of these ancient galaxies is the presence of supermassive black holes at their centers. These black holes are not the result of single stars collapsing. Instead, they are enormous, holding millions or even billions of times the mass of our Sun. And yet, they somehow formed incredibly fast, much faster than scientists had previously thought possible. Normally, a black hole takes billions of years to grow to that size. But here, in galaxies that are only a few 100 million years old, the black holes are already fully formed and gigantic. How did they grow so fast? One idea is that these massive black holes also formed through direct collapse. Instead of forming from a star, a giant gas cloud could have collapsed straight into a black hole, skipping the star stage entirely. Another theory suggests that once the black hole formed, it fed on enormous amounts of gas from its galaxy, growing at an incredible rate by swallowing everything around it. These discoveries have forced scientists to reconsider many of their old ideas about the early universe. For a long time, it was believed that the universe developed slowly and calmly, with galaxies taking their time to form and grow. But now, it appears that the early universe may have been much more exciting and full of sudden dramatic changes. It's possible that galaxies formed in a variety of ways. In some parts of the universe, they might have developed slowly, just as scientists once thought. But in other areas, galaxies may have exploded into existence at lightning speed, fueled by the intense energy, chaotic conditions, and mysterious forces like dark matter. All of this points to one powerful idea. The early universe was not a quiet, dark place slowly waking up. It was a booming, energetic time full of activity. Galaxies forming rapidly, stars lighting up the cosmos, and black holes growing at astonishing speeds. Even the period once called the Cosmic Dark Ages might not have been so dark and quiet after all. Instead, it may have been a time of brilliant explosions and fierce creation, as the first structures of the universe took shape far faster than anyone ever imagined. Most of the galaxies we see in the sky today fall into two main groups: spiral galaxies and elliptical galaxies. Spiral galaxies, like our own Milky Way, have long, curved arms that spin outward from a bright center. These arms are made up of stars, gas, and dust, all swirling around like dancers in a cosmic whirlpool. The whole galaxy moves in a graceful, organized way. Elliptical galaxies, on the other hand, don't have arms or patterns. Instead, they look more like giant glowing balls or stretched out footballs. The stars inside them don't move in neat circles but travel in many different directions, like people wandering through a crowd. These galaxies tend to be older and less active. But when scientists look deep into space, so deep that they are actually looking far back in time, they find something very different. The oldest galaxies, formed when the universe was still very young, do not look organized at all. They are messy, lumpy, and strange. They seem to be in the middle of forming rather than already shaped. This big difference in appearance comes from how galaxies form and change over time. In the early universe, just a few 100 million years after the Big Bang, galaxies were much smaller and didn't have the tidy structure we're used to. Instead of smooth spirals or clean elliptical shapes, these early galaxies looked more like cosmic puzzles with missing pieces. They were full of stars, gas, and dust clumped together in uneven patches. It's as if these galaxies were caught in the act of being built, with pieces still flying into place. This chaotic look reflects the wild and turbulent conditions of the young universe. Back then, galaxies were constantly bumping into each other, merging, breaking apart, and forming new structures. The universe was a busy, noisy workshop, not a quiet museum of well-arranged galaxies. For a long time, scientists believed that galaxies would slowly grow more organized and settled as they aged. They expected to find neat, smooth shapes, even in the earliest galaxies. But when astronomers began observing the farthest galaxies, the ones that formed more than 13 billion years ago, they saw something unexpected. These ancient galaxies didn't look calm or neat at all. Instead, they looked like tangled balls of stars and gas. Some were oddly shaped, with uneven lumps and jagged edges. Others looked like they were made of smaller galaxies that hadn't finished joining together yet. So, how do we even know what these ancient galaxies looked like, if they are so far away and the light from them has travelled for billions of years? The answer lies in a fascinating trick of nature: how light moves through space. Light doesn't move instantly, it takes time to travel. The farther away something is, the longer its light takes to reach us. So, when we look at a galaxy that is, say, 10 billion light-years away, we are not seeing it as it looks now. We are seeing it as it looked 10 billion years ago. It's like looking into a cosmic time machine. If we see a galaxy that is 1 billion light-years away, then the light we are seeing left that galaxy 1 billion years ago, and we are witnessing what it looked like all the way back then. To look this far back in time, scientists use very powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. These amazing tools can capture the faint light from galaxies that are billions of light-years away from Earth. They allow us to see what the universe looked like when it was still young and just beginning to form its first stars and galaxies. One of the most powerful tools for studying early galaxies is the James Webb Space Telescope, often called JWST. It was specially designed to look deep into space and far back in time. It can see infrared light, which is important because the light from distant galaxies gets stretched into longer, redder wavelengths as it travels across the expanding universe. JWST can pick up this ancient light, giving scientists incredibly clear views of galaxies as they looked more than 13 billion years ago. What JWST has shown us is surprising. Many of these early galaxies look far more irregular and chaotic than scientists had predicted. This discovery has challenged the old ideas about how galaxies form. Instead of slowly turning into neat, organized systems, it seems that many galaxies were born messy and stayed that way for a long time. But why were these early galaxies so messy and wild? One possible answer involves something mysterious and invisible: dark matter. Dark matter is a strange kind of matter that does not give off light or energy, so we can't see it with our eyes or telescopes. Yet, it makes up about 27% of everything in the universe. Scientists know it exists because it has a powerful gravitational pull. It tugs on the things we can see, like stars, galaxies, and even entire clusters of galaxies. In the early universe, dark matter wasn't spread out evenly. It formed dense blobs or clumps in different places. These clumps acted like giant magnets, pulling in gas and dust from their surroundings. This material then began to collapse under its own weight, forming new stars and, over time, entire galaxies. But because dark matter was clumped in random ways, the galaxies that formed around it didn't look smooth or regular. They were twisted and jumbled, still being shaped by the gravity of the dark matter. This may be why the earliest galaxies appear so strange. They were still under construction, shaped by invisible hands. Another reason early galaxies looked so unusual is that they were packed much closer together than galaxies are today. Back then, the universe was smaller and more crowded. Tiny galaxies floated near one another, and many of them crashed into each other. When galaxies collide, their stars usually don't crash into each other. There is just too much space between stars for that to happen. But the gas and dust inside the galaxies do crash, mix, and heat up. These cosmic crashes caused huge changes. The swirling clouds of gas and dust would get squeezed and heated, sparking the birth of new stars. Galaxies would get pulled into new shapes. Some would merge completely into bigger galaxies. Others would stretch, twist, or break apart. These violent events helped shape the galaxies into what we see today. Over time, this rough and chaotic dance gave rise to larger and more stable galaxies. But it all began in a time of cosmic turmoil. When the universe was still young, galaxies were still forming, and everything was changing rapidly. Even now, galaxies still collide and change, but it happens less often than it did in the early days. Back then, it was a regular part of the universe's wild and dramatic story of growth. Long ago, when the universe was still very young, only a few 100 million years after the Big Bang, galaxies looked and behaved very differently from the ones we see today. Back then, the early galaxies were filled with enormous amounts of gas, far more than the galaxies we see in the present. This gas was mostly made of hydrogen and helium, the two lightest and simplest elements in the universe. These gases were the main ingredients used to make new stars. Because there was so much gas flying around, early galaxies didn't have the neat and graceful shapes we often admire now, like spirals or smooth ellipses. Instead, they were wild and messy. The gas inside them was spread out unevenly, causing the galaxies to look lopsided, clumpy, and irregular. These young galaxies were like cosmic storms, turbulent, full of motion, and still trying to find their shape. Even the way stars were born in those early times was very different. In today's galaxies, like our own Milky Way, new stars usually form in special places, such as the spiral arms. These regions are organized and relatively calm, but in the early universe, star-making was much more chaotic. Stars could pop into existence almost anywhere inside a galaxy. Sometimes they were born in giant bursts, triggered by turbulence or by galaxies crashing into one another. This scattered and uncontrolled pattern of star formation gave early galaxies their clumpy and jumbled appearance. All of this happened because those galaxies were still in the process of growing up. Over billions of years, galaxies collided, merged, and matured. As this happened, they slowly began to form more organized shapes. Some turned into spiral galaxies with beautiful sweeping arms, while others became smooth and round, forming elliptical galaxies. By studying those early disorganized galaxies, astronomers can learn a lot about how galaxies grow and how the universe itself has changed over time. Deep in the center of almost every large galaxy, including our Milky Way, there lies something truly extraordinary: a supermassive black hole. These are unimaginably dense objects with gravity so strong that nothing, not even light, can escape once it gets too close. But black holes aren't just sitting quietly at the center of galaxies. They can actually shape the galaxies around them in powerful and surprising ways. Scientists believe that even in the earliest days of the universe, more than 13 billion years ago, supermassive black holes were already beginning to form in the hearts of young galaxies. Their intense gravitational pull could suck in huge amounts of gas, dust, and even entire stars. This powerful attraction didn't just affect the black hole's immediate surroundings, it could stir up the entire galaxy, making it even more chaotic. Stars might have been flung into odd orbits, and the whole galaxy could have become unstable. But black holes don't only pull things in, sometimes they explode with energy. As gas and dust spiral into a black hole, they heat up to extreme temperatures, creating enormous flashes of radiation. Some black holes even shoot out blazing jets of particles that travel at nearly the speed of light. These outbursts could punch through the surrounding space, pushing gas and dust away, and even stopping new stars from forming. In this way, black holes may have played a big role in shaping the strange and irregular shapes of early galaxies. Even now, scientists are still trying to fully understand how these cosmic giants influenced the early universe. But one thing is clear: supermassive black holes were not just silent observers, they were active, powerful forces that helped build the galaxies we see today. In the beginning, not long after the Big Bang, the universe was a wild and unruly place. Swirling clouds of gas, dust, and newborn stars filled the space, and galaxies looked nothing like they do today. Most of them didn't have smooth shapes or neat spiral arms. Instead, they looked like scattered clumps of stars and gas, without much structure at all. But over time, over billions and billions of years, something amazing happened. The invisible force of gravity began to pull everything together. Galaxies started to interact with one another, and sometimes they even crashed into each other. When two galaxies merged, their stars didn't usually collide because the space between them is so vast. But their gas and dust did interact, creating massive bursts of new stars. These galactic collisions, although violent and dramatic, actually helped galaxies settle down. The rough and messy shapes began to smooth out. Slowly, galaxies started to look more familiar. Some formed beautiful spiral arms like those of the Milky Way, while others became smooth and rounded like elliptical galaxies. Even today, this process isn't over. The universe is still changing. Galaxies continue to grow, merge, and reshape themselves. Our own Milky Way galaxy, for example, is heading toward a collision with the nearby Andromeda galaxy. This cosmic crash will happen in about 4 billion years. Eventually, the two will combine into one giant galaxy. This shows that the story of galaxy evolution is still being written. Recent discoveries have shocked scientists by showing that early galaxies were even more chaotic than anyone had guessed. These new findings are changing the way we understand galaxy formation. For a long time, scientists believed that galaxies slowly and steadily took shape over time. But now, we know the truth is much messier. The early universe was full of unpredictable and strangely shaped galaxies. Many of them looked like blobs or scattered collections of stars rather than anything structured. The forces that shape these galaxies are still not fully understood. The conditions back then were so different from today that researchers are still trying to figure out what exactly happened. Why were these galaxies so disorderly? What caused such wild bursts of star formation? These are questions that scientists are still working hard to answer. These strange early galaxies are like the universe's first building blocks. By studying them closely, scientists can trace the history of how galaxies grow, evolve, and change over time. Each clumpy, chaotic galaxy gives us a clue about how the universe went from a wild, swirling cloud of gas to the vast, structured cosmos we live in today. One of the most exciting and mind-blowing discoveries in modern astronomy is something scientists call the earliest light, a faint glow coming from galaxies that were born only about 200 to 300 million years after the Big Bang. Imagine that. This means we are looking at light that began its journey across space more than 13 billion years ago, giving us a rare and magical glimpse into the universe's very first chapter, a time when everything we now know was just beginning to form. Back then, the universe wasn't clear and open like it is now. It was filled with a dense, hot fog made of tiny particles. In this thick fog, light couldn't travel freely. The light particles, called photons, kept bumping into other particles, getting scattered in all directions. It was as if the whole universe was wrapped in a cosmic curtain that blocked any light from shining through. But over time, hundreds of thousands of years in fact, the universe slowly cooled down and expanded. As it did, the fog started to thin out. Finally, a turning point came when light was able to escape and travel freely across space. This incredible moment is known as the cosmic microwave background, or CMB. It's a faint glow that still lingers in the universe today, a kind of baby picture of the cosmos that tells us what things looked like when it was very young. But even more fascinating is what happened a little later, between 200 and 300 million years after the Big Bang. That's when the first galaxies and stars began to form, and the first real starlight filled the universe. This starlight didn't just brighten up the sky, it completely changed the cosmos. Before this, the universe was a dark, foggy place, but the birth of these first galaxies and stars helped clear away the fog, allowing light to shine freely for the first time. This transformation is known as the cosmic dawn, the beginning of a new era when the universe started to glow with stars, galaxies, and beauty. What makes this discovery so important is that the light from these very early galaxies has been travelling toward us for over 13 billion years. That's an unimaginable distance, and yet we can detect this ancient light today, like a whisper from the distant past. This light holds incredible secrets. It tells us about the moment when the universe started to build structure, when stars, galaxies, and eventually planets began to take shape out of the chaos of the early cosmos. Scientists had always believed that galaxies began forming this early, but proving it was extremely difficult. The problem is that the farther away a galaxy is, the longer its light takes to reach us. And since these galaxies formed so long ago, their light is incredibly faint by the time it gets to Earth. Also, as the universe keeps expanding, the light gets stretched out along the way, moving from shorter wavelengths like ultraviolet and visible light into longer wavelengths, especially infrared. That makes the light invisible to our eyes. To see this stretched ancient light, scientists needed very special tools. They used incredibly advanced telescopes like NASA's James Webb Space Telescope, the Hubble Space Telescope, and some of the world's most powerful ground-based observatories. These telescopes are designed to detect infrared light, which our eyes cannot see. Thanks to these amazing instruments, astronomers were finally able to pick up the faint signals coming from the universe's earliest galaxies, signals that have been travelling across space for more than 13 billion years. One of the biggest challenges in finding this early light is the way the universe has been stretching ever since the Big Bang. As space stretches, the light travelling through it gets stretched too, so the light that was once bright and blue, like ultraviolet light, is now so stretched that it looks like infrared light, which is much redder and softer. This is why infrared telescopes are so important. The James Webb Space Telescope was specially built to look into this infrared range. It allows scientists to see things that were completely hidden before, things that happened shortly after the universe was born. This light is more than just beautiful. It's incredibly useful. It shows that galaxies and stars began forming much sooner than scientists once thought. That helps answer a big question. How fast did the universe start organizing itself after the Big Bang? The answer is faster than expected. This early starlight proves that the universe didn't wait long to start creating, and this brings us to some of the most mysterious stars of all, known as Population 3 stars. These were the very first stars in the universe. They were nothing like the stars we see today. These ancient stars were made almost entirely of hydrogen and helium, the simplest and lightest elements created during the Big Bang. What made them unique is that they had no metals, nothing heavier than helium. Because of this, they burned much hotter and faster, shining brightly for only a short time before exploding in powerful supernovae. These stars helped shape the universe by sending out energy and spreading new elements into space. They also played a key role in a major event called ionization, which helped make the universe transparent, allowing light to travel freely across space. Studying this ancient light also helps scientists understand how galaxies were built. At first, the earliest galaxies were probably small and uneven, kind of messy compared to the massive, beautiful galaxies we see today. But over billions of years, these early galaxies crashed into one another, merged, and grew bigger and more complex. This process of growth and transformation eventually led to the creation of galaxies like our own Milky Way. The very first light that ever reached us from the ancient universe has a deep and mysterious connection to two of the strangest and most puzzling things in all of space: dark matter and dark energy. These two invisible forces are believed to make up almost all of the universe, much more than the stars, planets, and galaxies we can actually see. Yet, we still don't fully understand what they are or how they work. We can't see them with our eyes or even with the most powerful telescopes, but scientists know they're out there because of the strange effects they have on everything else in the universe. Dark matter is thought to act like a cosmic glue. It helps galaxies form and stay together, using its strong gravitational pull to gather stars and gas into clusters. Dark energy, on the other hand, seems to be the reason the universe is expanding faster and faster, pushing galaxies apart more quickly over time. These two invisible forces are shaping everything, but in secret. Now, here's where the first ancient light becomes incredibly important. This light, emitted from some of the earliest galaxies to ever exist, gives scientists a rare and powerful tool for peeking into the past. By studying this light, scientists can learn how dark matter affected the universe during its earliest moments. Although dark matter doesn't shine, glow, or reflect light, it does leave clues behind in the way galaxies moved and formed in those first billions of years. The light acts like a spotlight, revealing the hidden fingerprints of forces we cannot see. Every time we discover more of this ancient light, we are peeling back the layers of time. It's as if we are looking through a magical window into the distant past. This light began its journey billions of years ago, long before our solar system existed, even before the Earth was formed. When we observe it now, it's like watching a cosmic movie showing the birth and growth of the universe itself. One of the most breathtaking discoveries so far is the light coming from galaxies that formed only 200 to 300 million years after the Big Bang. Considering that the Big Bang happened about 13 billion and 800 million years ago, this means we're seeing light from a time when the universe was still very young, a newborn in cosmic terms. These early galaxies were just beginning to take shape, and their light has been travelling across space for almost the entire age of the universe to reach us today. And this is only the beginning of our journey into the past. Thanks to incredible advancements in technology, especially the powerful James Webb Space Telescope, we can now see farther and clearer than ever before. These new tools are opening up corners of the universe that were once completely hidden. With every new piece of ancient light we uncover, we gain new clues about how galaxies were built, how stars were born, and how the universe slowly transformed into the giant, beautiful place we live in today. But this search is not just about stars and galaxies, it's also about us, our story, our beginnings. As we keep learning about dark matter, dark energy, and the early days of the universe, we're also learning about our own place in the grand story of existence. The ancient light we study today helps us understand how everything we know, including our planet, our sun, and even life itself, came into being. Picture the universe just after the Big Bang, a moment when everything we know began. It was not calm or quiet. Instead, it was a wild and fiery place filled with blinding energy, scorching heat, and swirling particles racing in every direction. Time had just started ticking, and space itself was stretching and expanding at an unbelievable speed. In those first few heartbeats of existence, just fractions of a second after the Big Bang, something strange began to happen. The matter in the universe wasn't spread out evenly. Some parts had a little more stuff crammed into them than others. These small differences, though tiny, would change the course of everything. In the areas where matter was packed more tightly, gravity became stronger. And in some rare spots, this pull was so intense that space itself may have collapsed inward, creating what scientists call primordial black holes. These black holes are very different from the ones we usually hear about, the kind that form when giant stars burn out and die. Primordial black holes didn't come from stars at all. They may have been born directly out of the raw, chaotic energy of the early universe. They could have appeared in less than 1 second after the Big Bang, making them some of the very first objects ever to exist in the cosmos. Now, here's the really surprising part. Some of these black holes could have been incredibly small, maybe even as tiny as a single proton. That's unimaginably small, but despite their size, they could have been unbelievably powerful. Inside their tiny space, they might have held the mass of an entire mountain, or even a large asteroid. Some may have contained a mass close to that of a small planet like Earth. The reason this is possible is because black holes squeeze matter into an incredibly dense form. Imagine cramming something as big as a city, or even a planet, into a space no larger than a grain of sand. That's the kind of extreme density we're talking about. These mysterious black holes are called primordial because they may have been born before anything else, long before stars twinkled, before planets spun in orbit, and before galaxies formed their elegant shapes. Some of them may have vanished over billions of years through a strange process called Hawking radiation, where black holes slowly lose energy and fade away. But others, especially the larger ones, might still be out there, quietly drifting through space. Even though we can't see them, these ancient black holes could still be tugging on stars, bending light, or even passing through galaxies without being noticed. Some scientists believe that if these black holes exist in large enough numbers, they could explain one of the universe's greatest mysteries: dark matter. Dark matter is an invisible substance that makes up most of the mass in the universe. We can't see it, touch it, or shine a light on it, but we know it's there because of the way it affects the movement of galaxies and stars. Scientists have been searching for answers about dark matter for many decades, and primordial black holes might just be the key. If we can prove that these ancient black holes exist, it could unlock secrets about how the universe was formed and how it has grown over the past 13.8 billion years. It might even help us understand how gravity works on the most basic level. Let's go back to that chaotic beginning again. In the first tiny sliver of time, less than 1 second after the Big Bang, the universe was a thick, glowing soup of particles and energy. The temperature was unimaginably high. In this hot and crowded place, not everything was balanced. Some spots had just the right mix of density and pressure that gravity took over. These rare spots collapsed in on themselves, forming small but incredibly heavy black holes. They didn't need stars to be born. All they needed was the extreme environment of the newborn universe. When most people hear the term black hole, they usually think of a giant star that has collapsed under its own weight. These are called stellar black holes, and they form when massive stars, those several times heavier than our own sun, burn through all their fuel and collapse in on themselves. These cosmic monsters can weigh anywhere from a few times the mass of the sun to dozens of times more. But there's another kind of black hole that is far more mysterious and possibly much older. These are called primordial black holes, and they might have been born in the very first moments of the universe, right after the Big Bang, more than 13 billion years ago. Unlike stellar black holes, which come from dying stars, primordial black holes didn't come from stars at all. In fact, they may have formed before stars even existed. Scientists believe that in the chaotic and fiery newborn universe, everything was packed together tightly and swirling with incredible energy. Some tiny areas had more matter than others. These denser spots might have collapsed under their own gravity, instantly becoming black holes. And so, primordial black holes could have formed naturally from the raw energy of the early universe. What makes them even more fascinating is that they could be incredibly small. Some might be no bigger than a single atom. But don't let their size fool you. Even if one is that tiny, it could still hold an unbelievable amount of mass inside. That means they would be extremely dense, far more so than anything we can easily imagine. These ancient black holes may act very differently from the ones we usually study, and that's why scientists are so interested in them. Some even believe these tiny but powerful objects might help explain one of the biggest cosmic puzzles of all time: dark matter. Dark matter is a strange and invisible form of matter that we cannot see or touch, but we know it's there because it affects how galaxies move and how light bends around them. Scientists estimate that dark matter makes up about 85% of all the matter in the universe, yet no one has ever directly detected it. It's like a hidden force shaping the cosmos, quietly pulling the strings behind the scenes. Some researchers think that primordial black holes might actually be dark matter, or at least part of it. Because these ancient black holes would be tiny, dark, and scattered across space, they would be almost impossible to see. But they still have gravity, and gravity is something we can measure. If enough primordial black holes exist, their combined gravity could help explain the invisible pull of dark matter. And that's not all. If primordial black holes really did form right after the Big Bang, they could be scattered throughout the entire universe. Some scientists even believe there might be some floating around in our own galaxy, hiding in plain sight. They would be almost invisible, completely dark and too small to detect easily, but they might still leave subtle clues. Their presence could slightly bend the light from stars or affect the way objects move through space. Even though we haven't directly seen a primordial black hole yet, scientists are searching for evidence in several exciting ways. One method involves studying gravitational waves. These are like ripples in the fabric of space and time, created when massive objects like black holes crash into each other. Over the past few years, scientists have detected several of these waves, and some of them might have come from collisions between primordial black holes. If more of these mysterious waves are found coming from unexpected sources, it could be a big clue that these ancient black holes are out there. Another way researchers search for signs of primordial black holes is by studying something called the cosmic microwave background, or CMB for short. This is a faint glow left over from the Big Bang, still drifting through space almost 14 billion years later. If tiny black holes had formed in those early moments, they might have disturbed this ancient radiation. These disturbances could leave behind special patterns or fingerprints that we might be able to detect with powerful telescopes. Primordial black holes aren't just interesting because they're old or small, they could actually help us answer some of the deepest questions in all of science. They might tell us what the universe was like in its very first seconds, when time itself was just beginning to tick. They might help explain how everything, from stars and planets to light and matter, came to be. Even more exciting, these mysterious black holes could help scientists unite two of the most important ideas in physics: Einstein's theory of general relativity, which explains how gravity works and how massive objects bend space and time, and quantum physics, which explains how the tiniest particles behave. These two theories don't always get along, and scientists have been trying for many years to find a way to connect them. Some believe that studying primordial black holes could be the key to building a theory of everything, a single set of rules that explains how the entire universe works, from the smallest atoms to the largest galaxies. Primordial black holes are like ancient ghosts, whispering secrets from a time before stars, before planets, and even before light itself. They may be the oldest things in the universe, formed when everything was still wild, hot, and new. And although they remain one of the greatest cosmic mysteries, each new discovery brings us one step closer to understanding where we came from, and what might be hidden out there in the dark. These extremely old black holes are believed to have formed during the very first moments after the Big Bang, which happened around 13,800 billion years ago. Scientists think they might be hiding important clues about how galaxies were born, the strange and invisible material called dark matter, and the hidden forces that help shape the entire universe. As our telescopes become more powerful, satellites more advanced, and scientific tools more accurate, researchers are hopeful that they will find more signs of these ancient black holes. If they do, it could bring us much closer to finally understanding whether these so-called primordial black holes are real, and what role they may have played in building the universe we live in today. The universe is so huge that it's hard to even imagine its size, and even with all the amazing discoveries made so far, there is still an enormous amount we don't understand. One of the biggest mysteries is the possible existence of primordial black holes. These are not the usual black holes that form when stars die. Instead, they might have appeared right at the beginning of everything, within the first tiny moments after the Big Bang. These ancient black holes are completely invisible, which makes them even harder to study. But they are incredibly important, because they might help us understand how the universe itself began. If scientists can learn more about them, it could help solve some of the greatest cosmic puzzles. That's why many researchers are so excited about the search for primordial black holes. To them, these hidden objects represent one of the most exciting and mysterious areas of modern science, an adventure that could finally explain how our vast and beautiful universe came to be. When we gaze into the night sky with powerful telescopes, we're not just looking at distant stars and galaxies, we're actually looking back in time. This might sound like something from a science fiction movie, but it's one of the most incredible truths about the way light travels through space. Light doesn't move instantly. It travels at a set speed, about 186,000 miles every second. That's incredibly fast, but space is so enormous that even light can take a very long time to reach us. When we look at the most faraway galaxies, the light we see from them began its journey millions, or even billions of years ago. So we're not seeing them as they are now. We're seeing them as they looked a long, long time ago, sometimes when the universe was still in its earlier stages. As scientists study these ancient galaxies, they've made a discovery that is shaking the very foundations of what we thought we knew about the universe. Inside some of these early galaxies, they've found something astonishing: supermassive black holes. These are enormous, mysterious objects with gravity so strong that nothing, not even light, can escape them. What's so surprising is not just that these black holes exist, but how quickly they seem to have formed. According to the best scientific models we have, black holes usually start off small, forming when a giant star dies and collapses. After that, they grow very slowly over millions or even billions of years, gradually swallowing up gas, dust, and even entire stars. But the supermassive black holes found in these ancient galaxies were already gigantic when the universe was still very young. That means they somehow grew incredibly fast, much faster than science currently says should be possible. Normally, black holes take a very long time to grow this big. It's a slow process, like a snowball rolling down a hill gradually gathering more snow. But these black holes seem to have skipped the slow part entirely. They were already massive, like finished skyscrapers, at a time when the universe was just beginning to build its first bricks. Some scientists think that something very special may have happened in the early universe. Maybe a strange process allowed black holes to grow much faster than they do today. Others suggest an even more mysterious idea. Maybe some black holes were born in a completely different way. Instead of coming from dying stars, they might have formed from gigantic clouds of gas that collapsed straight into black holes. Before diving deeper into this cosmic mystery, let's take a moment to understand what a supermassive black hole actually is. Simply put, a black hole is a spot in space where gravity is so powerful that nothing can escape it. Not even light, the fastest thing in the entire universe. Once something passes the black hole's invisible boundary, called the event horizon, it's pulled in forever and disappears from view. Black holes come in different sizes. Some are small, formed when huge stars explode at the end of their lives. But then there are supermassive black holes, giants that make even large stars look tiny. These can be millions or even billions of times heavier than our sun. Imagine crushing the weight of an entire galaxy into a single point. That's how powerful these supermassive black holes are. These enormous objects don't just float around randomly in space. They are found right at the centers of galaxies, including our own galaxy, the Milky Way. It's as if they're the silent rulers of their galaxies, using their invisible strength to shape everything around them. Scientists believe they play a key role in how galaxies grow and change over time. Supermassive black holes affect the movement of stars, the gathering of gas clouds, and even how new stars are born. Sometimes, they release huge bursts of energy, powerful jets that shoot across vast stretches of space, changing the shape of entire galaxies. In our own Milky Way, scientists have found a supermassive black hole called Sagittarius A, sitting at the very heart of our galaxy. Even though we can't see it directly, we know it's there because of the way stars near it move. They spin around it at incredible speeds, like they're caught in a cosmic whirlpool. Despite their name, black holes aren't just empty spaces. They're among the most powerful and active forces in the universe, shaping it over billions of years. In fact, some scientists think that without supermassive black holes, galaxies might never have formed the way we see them today. Now, back to the mystery. Scientists believe that black holes start small, known as stellar mass black holes. These form when massive stars explode in events called supernovae. What's left behind is a core so dense that it collapses into a black hole. Over billions of years, that small black hole can grow bigger by pulling in everything around it: gas, dust, and even other stars. Eventually, with enough time and matter, it might grow into a supermassive black hole. But here's the shocking part. When astronomers look deep into space, which also means looking far back in time, they've found fully grown supermassive black holes in galaxies that existed less than 1 billion years after the Big Bang. This is a huge puzzle. The Big Bang, which created the universe, happened around 13.8 billion years ago. That means these gigantic black holes already existed when the universe was less than 1 billion years old. Still just a baby in cosmic terms. It's like walking into a nursery and finding a full-grown adult sitting in a crib. According to everything we understand about black holes, there simply wasn't enough time for them to grow so massive so fast. This discovery has left scientists both amazed and confused. It's forcing them to ask some very deep questions about whether we really understand how black holes grow. According to standard physics, black holes should form after massive stars die and collapse. These small black holes then grow bigger by merging with other black holes and feeding on gas and dust around them. A slow and steady process. But the black holes found in these ancient galaxies seem to have skipped all of that. They were already enormous when the universe was still very young. This brings us to one of the biggest mysteries in modern astronomy. How did these black holes grow so fast? Some scientists now believe that in the early universe something very unusual might have happened. Maybe some black holes formed directly from massive clouds of gas, skipping the star-forming stage completely. Others think these could be primordial black holes that were born in the first few moments after the Big Bang itself. If that's true, it would mean black holes have been around since the very beginning of time. And if that's the case, then we may need to rethink everything we thought we knew about the history of the universe. One of the most puzzling and surprising discoveries in modern astronomy is the existence of supermassive black holes in the early universe. These gigantic cosmic objects, some weighing millions to billions of times more than our sun, were already present just a few 100 million years after the Big Bang, which happened nearly 14 billion years ago. This doesn't make sense based on what scientists currently understand. Normally, black holes start off small, forming when huge stars explode and collapse under their own gravity. After that, They grow slowly over billions of years by swallowing nearby gas, dust, and even entire stars. But in this case, some black holes were already fully grown giants, while the universe itself was still a baby. It's like planting a seed and finding a massive tree just a few days later. Something about it just doesn't add up. At the time these black holes were found, the first galaxies were only just beginning to take shape. Stars were still being born, and there wasn't much material around for black holes to feed on. If black holes grow by eating the stuff around them, how could they have become so large so quickly when there was hardly anything there to consume? This strange discovery suggests that our current theories about how black holes form and grow might be missing something important. There could be a hidden process at work, something we haven't discovered yet, that allowed these ancient black holes to grow at lightning speed. To solve this mystery, scientists have come up with some fascinating ideas. One theory says that these black holes didn't start from stars at all. Instead, huge clouds of gas, some of them hundreds of thousands, or even millions of times more massive than the Sun, might have collapsed directly into black holes. This would mean they skipped the usual step of turning into stars first. By starting off big, these black holes wouldn't need as much time to grow into giants. Another idea is based on something called the Eddington limit. This is a kind of speed limit for how fast black holes can grow. As they pull in matter, they also give off a lot of radiation, which pushes outward and slows down how much more they can pull in. But some scientists think that, under very special conditions, black holes in the early universe might have broken this limit, allowing them to grow far faster than we thought was possible. There's also a theory about something called primordial black holes. These are black holes that might have formed right after the Big Bang, not from stars, but from the intense energy and pressure in the universe's first moments. If these black holes started off big, they would have had a major head start, allowing them to grow into supermassive black holes much earlier than usual, like joining a marathon halfway through and reaching the finish line before everyone else. Yet another idea suggests that black holes might have formed in groups, not one by one. These small black holes could have clumped together and merged with each other in the chaotic early universe. With so many collisions happening, they could have quickly grown into much larger black holes. In a short time, a bunch of tiny ones could have turned into a single, gigantic, supermassive black hole. But maybe the biggest surprise of all is that these early supermassive black holes might be telling us something entirely new about the universe, something we don't yet understand. Some scientists believe these black holes could lead to revolutionary discoveries in physics, like finding unknown forces or brand new types of matter that help black holes grow. These discoveries might even force us to rewrite some of the basic rules that we've believed for centuries. To solve this cosmic mystery, scientists are turning to one of the most advanced tools ever built, the James Webb Space Telescope, also known as JWST. This powerful telescope can see incredibly far into space, capturing light that's taken over 13 billion years to reach us. With each image, scientists are peering deep into the universe's past, back to the time when the first galaxies and black holes were forming. By studying these ancient galaxies and the supermassive black holes at their centres, astronomers hope to uncover the secrets of how such enormous objects appeared so early in the history of the universe. Every discovery brings us one step closer to solving this cosmic riddle. For thousands of years, human beings have looked up at the night sky with wonder, curiosity, and countless questions. They stared at the stars and asked themselves, is Earth the only place in this vast universe where life exists? The twinkling lights in the sky have always sparked the imagination, filling people's minds with dreams of other worlds. With billions upon billions of stars scattered across the endless cosmos, many began to believe that at least some of these stars might have planets like Earth, places where life could also thrive. For most of human history, though, this was only a dream. People imagined other Earths, but there was no proof. Scientists, stargazers, and dreamers kept searching and hoping, but they had no way to truly see what was out there. That all began to change in the last few decades of the 20th century. Thanks to powerful new telescopes and daring space missions, scientists have now discovered thousands of planets that orbit stars far beyond our own sun. These planets are called exoplanets, and their discovery has completely changed how we see the universe and our place in it. Some of these exoplanets might even have the right ingredients for life. While only a small number of them seem to have Earth-like conditions, each new discovery brings us one step closer to answering one of the greatest questions ever asked. Are we alone in the universe? Exoplanets are planets that orbit stars outside of our solar system. Some of them are rocky like Earth and might have oceans, atmospheres, or even temperatures that could support life. Others are massive gas giants like Jupiter, or strange worlds that defy what we thought was possible. Astronomers have found exoplanets in places and forms that are completely unexpected. Some are frozen in eternal winter, covered in thick sheets of ice. Others are blazing hot with entire oceans made of melted rock. There are even planets where it rains liquid metal as the extreme heat in their skies turns iron into droplets that fall like fiery rain from the clouds. The very first confirmed discovery of exoplanets happened in the year 1992. These early planets were found orbiting a pulsar, a dead, collapsed star that shoots out beams of radiation like a cosmic lighthouse. These planets were incredibly strange and showed that worlds could form even in the most unexpected corners of the universe. Then, in the year 1995, astronomers found a planet named 51 Pegasi b. This was the first exoplanet discovered around a star similar to our Sun. It was a gas giant, much like Jupiter, and its discovery proved that planets orbiting stars like our own are real. That single discovery opened the floodgates for a whole new era of exploration. Since then, scientists have confirmed the existence of more than 5,005 exoplanets, and that number continues to grow rapidly. New discoveries are being made all the time, especially with the help of advanced space telescopes like the James Webb Space Telescope. This powerful instrument is not only spotting new planets, but also studying the gases in their atmospheres, looking for signs of life and unlocking the secrets of worlds far beyond our solar system. But not all exoplanets are alike. Scientists group them into different types based on things like size, materials, and how close they are to their stars. One of the most important groups is the gas giants. Gas giants are huge planets, much bigger than Earth. Two well-known examples in our own solar system are Jupiter and Saturn. These giants are mostly made up of hydrogen and helium, two gases that are lighter than air. Because of their size and brightness, gas giants are easier to spot in space and are often among the first planets scientists find when observing distant star systems. To get an idea of just how big they are, consider this. More than 1,300 Earths could fit inside Jupiter. These planets don't have a solid ground like Earth. Instead, they are wrapped in thick clouds of gas. As you go deeper into the planet, the gas becomes heavier and hotter. In the deepest parts, the pressure is so intense that even hydrogen, which is usually a gas, turns into a strange liquid form. Scientists think there might be a solid core at the very center, but no one knows for sure because we can't send spacecraft deep enough to find out. We know a lot about gas giants like Jupiter and Saturn because they shine brightly in our sky and have been studied by telescopes and space probes for many years. These planets also give off more energy than they receive from the Sun, which makes them stand out even more in space. Gas giants are not rare. In fact, most of the exoplanets discovered so far are gas giants. One big reason for this is that they are easier to detect. When a gas giant passes in front of its star, it causes a slight dimming of the star's light, something known as a transit. These dips in brightness allow astronomers to notice and study the planet, even if it's located trillions of miles away. Some gas giants found outside our solar system are even more extreme than Jupiter. For example, there are hot Jupiters, which orbit their stars very closely and have incredibly high temperatures. Then there are ice giants like Uranus and Neptune, which, while still mostly gas, contain more water, ammonia and methane, chemicals that make them different from Jupiter and Saturn. The discovery of so many gas giants has raised many fascinating questions. How do these giant planets form? How different can they be from one another? And is it even possible for life to exist on or around one of them? Perhaps on a moon that orbits a gas giant like Jupiter's icy moon Europa? Although gas giants seem too harsh and wild to support life as we know it, studying them helps us understand the building blocks of planets, how solar systems are formed, and what other types of worlds might be waiting out there in the great unknown. Each gas giant we discover adds a new piece to the cosmic puzzle, bringing us closer to understanding the incredible diversity of planets in the universe, and maybe, just maybe, bringing us closer to discovering life beyond Earth. Secondly, let's explore the amazing Neptune-like planets, fascinating worlds that are similar in many ways to the distant planets Uranus and Neptune, which both live far out in the cold reaches of our solar system. These types of planets are often called mini-Neptunes, because like Neptune and Uranus, they are mostly made up of gases rather than solid rock or metal. However, unlike the giant gas planets such as Jupiter and Saturn, mini-Neptunes are much smaller in size. To truly understand what mini-Neptunes are, it helps to look at their bigger relatives. Neptune and Uranus are both famous for their thick, swirling atmospheres filled with gases like hydrogen, helium, and methane. This special mix of gases gives them their beautiful bluish colour and also leads to incredibly strong winds and violent storms. They're also known as ice giants because their atmospheres and inner layers contain frozen substances like water, ammonia, and methane, making them not just gas worlds but icy ones too. Mini-Neptunes, while smaller, share many of these traits. Unlike Jupiter, the biggest planet in our solar system, which is a gigantic ball of gas, mini-Neptunes are much less massive. Their smaller size means they can still have thick, fluffy atmospheres made mostly of hydrogen and helium, but they don't have the super dense cores that big gas giants do. Because of this, their atmospheres are lighter and thinner, though still made mostly of gas. One of the most interesting things about mini-Neptunes is that they usually don't have a solid surface like Earth or Mars. Instead, they are made up of layers of gas and ice. Some of them might have a rocky core buried deep inside, but it's hard for scientists to study these cores directly because of the thick gases that cover them. In fact, some mini-Neptunes have been found with cloudy skies, powerful winds, and stormy weather that make them look like smaller versions of Neptune or Uranus. Astronomers are especially fascinated by these Neptune-like planets because they appear to be quite common around other stars. So far, thousands of planets have been found outside our solar system. These are called exoplanets, and many of them fall into the mini-Neptune category. Some studies even suggest that mini-Neptunes could be one of the most widespread types of planets in our entire galaxy. What makes them even more exciting is how different each one can be. Some mini-Neptunes have thick clouds that trap heat, making them incredibly hot on the inside. Others may have lighter atmospheres mixed with different ices and gases, leading to unique weather patterns and wild storms unlike anything we see on Earth. Even though they look like Neptune, these planets are different in other ways too. Because they are smaller, they might not have the strong magnetic fields or giant storms that their larger cousins do. But they can still be very active, with mysterious weather systems and maybe even oceans hidden deep beneath their clouds. Studying these strange worlds gives scientists valuable clues about how planets form and change over time. Every new discovery helps us understand more about our universe and raises new questions about what might be possible on other planets. As our technology continues to improve, we may soon be able to take a much closer look at these mysterious worlds. Future space missions could send robotic spacecraft to explore planets like these in detail, helping us unlock their secrets and learn even more about what kinds of worlds exist beyond our solar system. Now let's move on to another exciting group of planets, super-Earths. These are planets that are larger than Earth but smaller than Neptune. They don't get as big as the huge gas giants like Jupiter or Neptune, but they are still quite a bit bigger than our own planet. The term super-Earth simply refers to how large and heavy they are. It doesn't mean they're exactly like Earth, or that they can support life. Some super-Earths may have solid surfaces made of rock just like Earth. Others might be wrapped in thick blankets of gas or covered in icy layers. What makes them especially exciting is that some of them could have the right conditions for life. Scientists believe that if a super-Earth is at just the right distance from its star, not too hot and not too cold, there might be liquid water on its surface. And since water is necessary for life as we know it, these planets could possibly host living things, from tiny microbes to more complex creatures. Another fascinating thing about super-Earths is their gravity. Because they are more massive than Earth, their gravity would be much stronger. If a person stood on one, they would feel much heavier and find it harder to walk or jump. But this stronger gravity could also help hold on to a thick atmosphere, which would protect the surface from dangerous space radiation, something important for life to survive. Super-Earths come in many forms. Some might be ocean worlds, with water stretching from one side of the planet to the other. Others could have thick clouds and hot atmospheres, more like the planet Venus. Some may be rich in valuable minerals or contain chemicals that don't exist anywhere on Earth. Because they are so large, super-Earths might also have very active insides, with molten rock and even volcanoes. This volcanic activity could help create and maintain a stable atmosphere by releasing gases over millions of years. And if they have magnetic fields, like Earth does, these planets could be protected from harmful solar winds, making them even more Earth-like and possibly friendly to life. Astronomers have already found many super-Earths around distant stars. Thanks to powerful new telescopes, we can now study them more closely than ever. Some famous examples such as Kepler 22b and TOI 700d have made headlines because they appear to be in what scientists call the habitable zone. This is the sweet spot around a star where the temperature is just right for liquid water to exist. In our solar system, there are 4 special planets known as terrestrial planets. These are Earth, Mars, Venus, and Mercury. What makes them stand out is that they are made mostly of solid rock and metal. They have strong, firm surfaces that you could actually stand on, unlike the big gas planets like Jupiter and Saturn. Those gas giants are mostly made of gas and don't have any solid ground beneath their clouds, so if you tried to land on them, you'd just sink. Because of their solid surfaces, terrestrial planets are especially interesting to scientists who are trying to find out whether other planets could support life. These rocky worlds may hold the key to discovering life beyond Earth. Earth is the most famous of all the terrestrial planets. Why? Because it's the only one we know for sure that has life on it. People, animals, plants, bacteria, everything we know that lives is right here. That's why scientists are always eager to find other planets that might be like Earth. They want to know, could there be another planet out there where life has taken root? This curiosity makes Mars, Venus, and Mercury especially fascinating to space explorers. Take Mars, for example. Often called the Red Planet, it has a dusty, rocky surface and shows signs that long ago, rivers and lakes may have flowed there. Some scientists think that billions of years ago, Mars might have had the right conditions for life. That's why space agencies like NASA have sent several robotic rovers, like Curiosity, Perseverance, and others, to drive around its surface, take pictures, dig into the soil, and search for any clues that life might have once existed there. Then there's Venus, which is sometimes called Earth's twin. That's because it's about the same size as Earth and made of similar materials. But don't let the nickname fool you. Venus is a very dangerous place. Its surface is extremely hot, even hotter than an oven, and it's covered in thick clouds filled with poisonous gases. Even though it's so different from Earth, scientists are still very curious about Venus. Studying it might help us understand how planets change over time, and why Venus became so harsh, while Earth remained a place full of life. Mercury, the smallest of the terrestrial planets, is closest to the Sun. Because of that, it has some of the most extreme temperatures in the solar system. During the day, Mercury gets so hot it could melt lead, but at night, without any atmosphere to keep the heat in, it becomes colder than an icy desert. Scientists are interested in Mercury because its surface is covered with craters from space rocks, and it gives us a good chance to study what happens when a planet doesn't have an atmosphere to protect it. What all these rocky planets have in common is that they have solid ground. That makes them different from the gas giants, and important for scientists searching for planets beyond our solar system, called exoplanets. Experts are especially interested in finding rocky exoplanets that lie in a special part of space called the habitable zone. The habitable zone is often called the Goldilocks zone, a term that comes from the famous fairy tale, where Goldilocks liked things that were not too hot, not too cold, but just right. In space, this zone is the area around a star where a planet is the right distance to have liquid water on its surface. Not frozen water, not steam, liquid water, like the kind we drink, swim in, and use for farming. This is very important because all living things on Earth, whether tiny microbes or large animals, depend on liquid water to survive. If a planet is too close to its star, like Venus, it gets way too hot. Any water would quickly boil away and vanish. It would be like standing next to a giant campfire. You'd burn up. On the other hand, if a planet is too far away, like Mars, it gets too cold. Any water would freeze solid, turning the planet into an icy wasteland. But Earth sits in that perfect middle ground. It's not too close and not too far from the Sun. This allows lakes, rivers, oceans, and even clouds to form and thrive, creating an environment where life can grow. This perfect distance from the sun is one of the reasons Earth is so special. It allows water to move freely, and that water supports countless forms of life, from fish in the sea to birds in the sky, and of course, people. But distance alone isn't enough. A planet also needs a protective atmosphere. Think of a planet's atmosphere like a cozy invisible blanket wrapped around it. This blanket helps trap some of the sun's warmth and protects the planet from harmful space radiation and meteors. Without an atmosphere, a planet's temperature could swing wildly from freezing cold at night to burning hot during the day. That would make it very hard for life to survive. Earth's atmosphere is made up of many different gases. One of the most important is oxygen, which we breathe in every second to stay alive. Another important gas is carbon dioxide. Even though we only need a tiny amount of it, it plays a big role. It helps keep Earth warm by trapping heat. This is called the greenhouse effect. If we didn't have enough carbon dioxide, Earth could become too cold, but if there's too much, it could become dangerously hot. So, it's all about balance. Let's start by thinking about the Moon. Unlike Earth, the Moon does not have an atmosphere at all. This means there's no air to breathe, no clouds in the sky, and no protection from the harsh environment of space. Because of this, the temperatures on the Moon swing wildly between extremes. When the sun shines on the Moon during the day, it becomes scorching hot, reaching over 250 degrees Fahrenheit. But once the sun goes down and night falls, the temperature drops to an icy cold -280 degrees Fahrenheit. There's nothing to hold in the heat, and nothing to block the sun's harmful rays. Without an atmosphere, the Moon is completely exposed. It's a beautiful place to look at from Earth, but it's not somewhere life could survive. Now let's take a look at Venus. Venus is very different from both the Moon and Earth. Instead of having no atmosphere, it has one that's far too thick. This thick blanket of gas is made mostly of carbon dioxide, a gas that traps heat very efficiently. Because of this, Venus has something scientists call a runaway greenhouse effect. In simple terms, this means heat keeps building up and doesn't escape. As a result, the surface of Venus gets unimaginably hot, around 900 degrees Fahrenheit. That's hotter than the inside of a regular kitchen oven set to its highest temperature. And on top of that, the air on Venus is full of poisonous gases. With deadly heat and toxic air, Venus is one of the most dangerous places in the solar system. Nothing we know of could live there. This shows how important an atmosphere is. For a planet to support life, it needs an atmosphere with the right mix of gases. The atmosphere has to trap just enough heat to keep the planet warm, but not too much. It also needs to block dangerous radiation from space. If a planet has too thin an atmosphere, it will freeze. If the atmosphere is too thick, it will bake. Earth is special because it has the perfect balance. It's just right, not too hot, not too cold, and safe for living things. But there's another invisible hero that protects life on Earth. Our planet's magnetic field. Think of it as a giant invisible shield that wraps around the Earth. This shield defends us from harmful energy that constantly pours out from the sun. This energy is called solar radiation, and without the magnetic field, it would hit Earth directly. Over time, it could even strip away our precious atmosphere, leaving us completely unprotected. Why is that so serious? Because our atmosphere does more than just hold in air. It gives us the oxygen we breathe and the nitrogen that helps keep everything in balance. It also acts like a blanket, keeping Earth's temperature steady and comfortable. If solar radiation were allowed to hit Earth without any defense, it would slowly tear the atmosphere away. Without air to breathe, without protection from the heat of the sun, Earth would become a lifeless, frozen world. Now let's turn our attention to Mars. Long ago, Mars may have had a magnetic field like Earth's, but at some point, it disappeared. Once Mars lost this protective shield, the sun's radiation started attacking its atmosphere. This didn't happen overnight, it took millions of years, but eventually much of the Martian atmosphere was blown away into space. Today Mars has only a thin layer of air, far too weak to trap heat or keep the surface safe from radiation. That's why the planet is now dry, cold, and empty. No oceans, no forests, and no signs of life. But there's something fascinating about Mars. Scientists believe it may once have looked more like Earth. It might have had a thick atmosphere, flowing rivers, and even shallow seas. Some think it may have had the right conditions for life to begin. But with no magnetic field to protect it, Mars couldn't hold on to these things. The sun stripped it bare. Today, it stands as a dusty, frozen reminder of what can happen when a planet loses its shield. This makes Earth's magnetic field even more important. It's not just a random feature, it's one of the key reasons why life is possible here. Without it, our world could have ended up just like Mars, cold, dead, and lifeless. Now let's talk about another ingredient that's crucial for life: water. Specifically, liquid water. Just being in the habitable zone isn't enough. This zone is the area around a star where a planet isn't too hot or too cold for water to exist. But even if a planet is in the right spot, it still needs water in the right form. Water in liquid form is incredibly important. It's the perfect place for the chemical reactions that life needs to begin and survive. Ice or water vapor isn't good enough. Life as we know it depends on having oceans, rivers, lakes, or even underground water flowing beneath the surface. Think about Earth. Our planet is full of life, and one big reason is because we have so much liquid water. The oceans cover most of Earth's surface. Without them, life would have a much harder time surviving. That's why, when scientists look for other worlds that might have life, the first thing they look for is signs of water. But finding water on other planets is not easy. Scientists use huge telescopes and advanced tools to look for tiny clues. They study the light from distant planets to see what kinds of gases are in their atmospheres. They look for temperatures that are not too hot or too cold, just right to keep water from freezing or boiling away. It's a tricky job, but finding liquid water gives us the best hope of discovering life beyond Earth. However, there's something else that matters when it comes to supporting life: the kind of star a planet orbits. Stars come in many sizes and temperatures, and that makes a big difference. Some stars are much bigger than our Sun. These stars are incredibly hot and bright, but they burn through their fuel very quickly. They live fast and die young, sometimes in just a few million years. That doesn't give planets orbiting them enough time for life to grow and evolve. The heat and radiation from these stars can also make conditions too harsh for life to survive. On the other end, there are smaller stars that are cooler and dimmer than the Sun. These stars live much longer, sometimes for tens of billions of years. But because they're not as hot, their planets have to be much closer to get enough warmth. If a planet is even a little too far away, it could be too cold for water to stay liquid. The best stars for life are the ones that are just right, like our Sun. Stars like the Sun are stable, warm, and live for billions of years. They shine steadily and give planets plenty of time to develop and support life. These stars offer the kind of balance that life needs. Even stars that are a little smaller than the Sun, called K-dwarfs, are good candidates. These stars burn their fuel slowly and shine for an incredibly long time, sometimes up to 40 or even 50 billion years. That's much longer than the Sun will last, and even though they're a bit cooler, they can still provide the right conditions for life on nearby planets. Exoplanets are planets that orbit stars far beyond our own solar system. These mysterious worlds can be millions or even billions of miles away from Earth. So far, in fact, that scientists cannot actually see most of them with their own eyes, not even through regular telescopes. But that doesn't stop them. Astronomers have come up with clever indirect ways to discover these distant planets. They study the light from faraway stars and how that light behaves. They also observe how stars move ever so slightly. With these techniques, they can uncover the hidden presence of planets that would otherwise remain invisible, giving us a peek into the vast and mysterious universe. One of the most popular ways scientists detect these hidden planets is called the transit method. Think of it like this. If you shine a flashlight and a tiny bug flies in front of the beam, you'll notice a brief shadow. That's exactly what happens on a cosmic scale when a planet passes in front of its star. Here's how it works. Scientists carefully watch a distant star, which could be located hundreds or even thousands of light years away from Earth. 1 light year is the distance light travels in a single year, about 6 trillion miles. These stars shine brightly, and when a planet moves across the face of the star from our point of view, it blocks a small bit of the star's light. This causes the star's brightness to dip slightly. The change is so tiny that you wouldn't notice it just by looking, but special instruments can measure it. This dip in brightness happens regularly, depending on how often the planet orbits the star. The amount of light the planet blocks tells scientists about the planet's size. The bigger the planet, the more light it blocks. By watching these dimming patterns over time, astronomers can tell that something is moving in front of the star, and that something is usually a planet. This clever method doesn't just help them find planets, it also gives clues about how big the planet is, how long it takes to orbit its star, and even if the planet might be in what's called the habitable zone, the perfect distance from the star where temperatures might be just right for life to exist. A special telescope called the Kepler Space Telescope, launched by NASA in the year 2009, used this method for many years. It kept its eye on more than 150,000 stars and discovered thousands of exoplanets. Thanks to Kepler, we now know that planets are extremely common in our galaxy, and some might even be similar to Earth. Another amazing method scientists use is called the radial velocity method, often nicknamed the wobble method. Here's the idea. When a planet orbits a star, its gravity tugs gently on the star. It's like a small child pulling on a parent's hand. The star doesn't stand perfectly still. It moves just a little, almost like a gentle wobble. This wobble is way too small for the human eye to see, but powerful scientific instruments can detect it. These instruments study the light coming from the star and notice tiny changes caused by something called the Doppler effect. You've probably noticed this effect when a car zooms by, and the sound changes as it moves, higher pitched as it approaches, lower pitched as it moves away. Light from stars does something similar. When a star moves toward us, its light shifts slightly to the blue side of the spectrum. When it moves away, the light shifts toward red. By measuring these color shifts, scientists can figure out that a planet is pulling on the star. Even if the planet is so far away that we'll never see it directly, this method lets scientists detect its presence. It can also tell them how heavy the planet is, how far it is from its star, and sometimes even what its orbit looks like. Over the years, this technique has helped discover hundreds, and possibly even thousands of exoplanets. It's like listening to the quiet footsteps of a hidden traveller walking through space. Sometimes scientists get lucky and are able to capture actual pictures of exoplanets. This rare and amazing technique is called direct imaging. But it's not easy. Stars are incredibly bright and the planets around them are much dimmer. Trying to take a picture of a planet next to a bright star is like trying to see a tiny candle flame next to a spotlight. To solve this, astronomers use special telescopes equipped with powerful technology that can block out the star's blinding light. This lets them focus on the much fainter light coming from the planet. It's like wearing sunglasses that help you see something small and dim next to something very bright. Direct imaging doesn't happen often, but when it does, it's a big deal. These rare images help scientists study a planet's size, color, and even its atmosphere. They can learn if the planet is rocky like Earth, icy like Neptune, or gassy like Jupiter. They can also look for signs that the planet might support life. Every time a new planet is photographed, it brings us one step closer to understanding the countless worlds that exist in the universe. Another incredible method used by scientists is called gravitational microlensing, and it sounds like something out of a science fiction movie, but it's very real and very powerful. Here's how it works. Gravity can bend light. So, when a massive object, like a star, passes in front of a more distant star, the gravity from the front star bends and magnifies the light from the one behind it. If there's a planet orbiting the front star, it can create a little extra blip in the brightness. This tiny flash of extra light is enough to tell scientists that a planet is there. This method doesn't require light from the planet at all. Instead, it relies on gravity and light from stars far behind it. That's why gravitational microlensing is so useful for finding planets that are way too distant or too faint for any other method. Even though it's rare and unpredictable, this technique can discover planets that no other method can. Some of the most distant and strange exoplanets we've found so far were detected this way. Imagine a lonely planet floating through the endless darkness of space. Far away, a distant star glows, sending out its light across billions of miles. Normally, the star's light travels in a straight line toward us here on Earth. But once in a while, something magical happens. If that wandering planet drifts directly in front of the star, it causes a surprising and powerful effect. Instead of just blocking the light, the planet's gravity bends it, like a magnifying glass bending sunlight. This bending makes the distant star look brighter, and sometimes even larger than it truly is. This strange effect happens because gravity isn't just a force, it also changes the very shape of space around it. That idea comes from Albert Einstein's famous theory of relativity. The heavier something is, like a planet, a star, or even a black hole, the more it pulls and twists the space around it. So, when a planet passes directly between us and a faraway star, its gravity slightly warps the light that's coming from the star. This warping creates a temporary brightening that we can see from Earth. Scientists call this amazing event gravitational microlensing. It doesn't last long, but it can reveal something we would never have seen otherwise. What makes gravitational microlensing so incredible is that it can uncover planets we can't see in any other way. Most planets are discovered by either watching how their light reflects, or by noticing how they gently tug on their parent stars with their gravity. But these usual methods don't always work, especially if the planet is very small or very far away from its star. Microlensing gives us a rare peek at these hidden worlds, even if they're light years beyond our reach. It's a bit like finding a hidden gem in the night sky. When that brief brightening happens, scientists on Earth quickly use powerful instruments to measure how much the star's light changes. From that tiny flicker, they can figure out amazing details: how big the planet is, where it is, and even how far it orbits from its star. But gravitational microlensing doesn't just help us find planets. It's also a way to discover other mysterious things in space, like black holes, neutron stars, or strange objects we still don't fully understand. Since many of the planets found using this method are located in distant corners of the galaxy or even the universe, this technique opens up a whole new way of exploring space. It lets astronomers reach farther than ever before, into places they once only dreamed of studying. Thanks to this and other advanced methods, astronomers have already discovered a number of fascinating exoplanets, planets that orbit stars outside our solar system. Some of these planets are especially exciting because they might have the right conditions to support life. Here are a few of the most promising examples. Proxima b. This planet orbits a star called Proxima Centauri, which is the closest star to our solar system. It lies just over 4 light-years away. Proxima b is located in what scientists call the habitable zone, the area around a star where the temperature might be just right for liquid water to exist. That's important, because water is essential for life as we know it. However, scientists are still trying to figure out whether Proxima b has an atmosphere strong enough to protect it and keep it livable. The TRAPPIST-1 system. About 40 light-years from Earth lies an extraordinary star system called TRAPPIST-1. This system contains 7 planets that are all roughly the same size as Earth. Even more exciting, 3 of these planets are in the habitable zone. If these planets have the right conditions, like water and an atmosphere, they could possibly support life. Because of this, TRAPPIST-1 has become one of the most closely watched systems in the universe. Kepler 442b. This planet, often called a super-Earth, is located around 1,200 light-years from Earth. It's larger than our planet, but it orbits within the habitable zone of its star. Scientists believe it might have the right temperature and possibly an atmosphere that could support life. That makes Kepler 442b one of the most interesting candidates for habitability. LHS 1140b. This rocky world lies about 40 light-years away from Earth. It has captured the interest of astronomers because it's believed to have a thick atmosphere and may even have liquid water on its surface. Its rocky terrain is similar to Earth's, making it another strong possibility in the hunt for alien life. One of the most mind-blowing and mysterious parts of our universe is something we cannot even see: dark matter. It's a strange, invisible kind of matter that acts like an invisible web, quietly holding the entire universe together. Even though we can't look at it with our eyes or take a picture of it with even the best telescopes, scientists are sure it exists. Why? Because of how it affects the things we can see, like stars and galaxies. Without dark matter, the way galaxies spin and move through space wouldn't make any sense at all. The universe would fall apart. Now, regular matter, the kind we're made of, the stuff that makes up stars, planets, and everything we can see, glows or reflects light. That's how telescopes pick it up. But dark matter is different. It doesn't shine. It doesn't reflect, absorb, or give off any kind of light or radiation. That's why scientists call it dark. Not because it's gloomy or shadowy, but because it's completely hidden. It's invisible, and yet its pull is powerful. Galaxies spin so quickly that the stars inside should be flying away into space, but they don't. Something invisible is pulling them inward, keeping them together. That something is dark matter, and it has been quietly shaping the universe since the beginning of time. To get an idea of how important dark matter really is, let's think of the universe as one gigantic puzzle. But here's the twist. Most of its pieces are completely invisible. Everything we can see, stars, planets, gas clouds, even people, makes up only about 5% of the entire universe. That means everything we've ever looked at in the night sky is just a small piece of the bigger picture. A much larger part, around 27%, is dark matter, the mysterious unseen substance that doesn't shine or glow. We can't see it directly, but it plays a huge role. It acts like a kind of invisible glue, holding galaxies together. Without it, galaxies like our own Milky Way wouldn't have their beautiful spiral shapes. Instead, stars would just drift apart, floating away into the emptiness of space. But that's not the end of the mystery. The biggest and strangest part of all is something even more puzzling. Dark energy. This force makes up the remaining 68% of the universe. And instead of pulling things together like dark matter, dark energy is doing the exact opposite. It's pushing the universe apart faster and faster as time goes on. Scientists still don't know what dark energy really is, but they believe it's the force behind the universe's rapid expansion. So, when we step back and look at the big picture, we realize something astonishing. Most of the universe, more than 95%, is made up of things we can't see and don't fully understand. Yet, these invisible forces are shaping everything, from tiny atoms to giant galaxies that stretch across the cosmos. For many years, actually for more than 80 years, scientists have been chasing down the mystery of dark matter. They are convinced it's real, not because they've seen it, but because of the strange way galaxies behave. When astronomers study galaxies that are millions or even billions of light years away, they see that these galaxies are spinning too fast for the amount of visible matter they contain. According to all the laws of physics we know, they should fly apart. But something invisible is holding them together. That something is dark matter. To understand how dark matter helped shape the universe, we need to travel back to the very beginning, just moments after the Big Bang, which happened around 13.8 billion years ago. Back then, the universe was extremely hot and wild, filled with energy and tiny particles flying around in chaos. But as the universe began to cool down, dark matter started playing its part. It acted like an invisible scaffold or framework, pulling gas and dust into place and helping form the first stars and galaxies. Without it, the early universe might have stayed a chaotic mess. No galaxies, no stars, maybe even no life. Even though dark matter has played such an important role, we still don't know what it's made of. Scientists are trying to figure out if it's composed of particles we haven't discovered yet, or if it's connected to mysterious forces we haven't imagined. To solve this puzzle, researchers are using all kinds of amazing tools: gigantic detectors buried deep underground, particle colliders that smash atoms together, and powerful telescopes in space. Every experiment, every clue, brings us closer to finding the truth. But the mystery isn't solved just yet. Understanding dark matter isn't just about solving a science riddle. It could completely change the way we understand the universe. If we figure out what dark matter really is, we might also learn more about how the universe was born, how it grew, and maybe even discover new laws of physics that could change everything we thought we knew. Recently, scientists have made exciting progress, thanks to some of the most advanced technology ever built. Even though dark matter remains invisible, these discoveries are giving us better and better clues. One of the most important pieces of evidence comes from something called the cosmic microwave background, or CMB for short. This is a faint glow of energy that was left over from the Big Bang, like a baby picture of the universe. It's the oldest light we can see, dating back nearly 13.8 billion years. When scientists study this ancient light, they see tiny ripples, small patterns that show how matter started to clump together. And these patterns suggest that dark matter must have been there from the beginning, helping shape the first stars and galaxies. But how can dark matter do this if it can't be seen? The answer is gravity. Even though dark matter doesn't shine, its gravity still pulls on regular matter. It helped gather gas and dust into huge clumps, leading to the creation of stars, galaxies, and massive clusters. Without it, the universe might have stayed scattered and empty. Today, scientists are still hunting for ways to detect dark matter directly. They're not just looking at how it moves galaxies, but they're also trying to find particles or signals that might reveal its true nature. Every new discovery brings them a step closer to solving this epic mystery. In the early days, right after the Big Bang, the universe was like a giant storm of heat and energy. Everything was extremely hot, packed together tightly, and moving wildly in all directions. As it started to cool, things began to slow down and form more organized structures. But this transformation wasn't easy. Think of the early universe like a boiling soup, full of wild, swirling particles. Something had to help bring order to that chaos. That something was dark matter. Even though it was invisible, it was everywhere. And because of its strong gravity, dark matter started to clump together into huge invisible clouds. These clumps pulled in irregular matter, which helped form the very first galaxies and stars. Without dark matter's invisible hand guiding everything, the universe might never have taken shape the way it did. There would be no galaxies, no planets, no people. Dark matter was like a hidden blueprint, shaping the universe from behind the scenes. And now, billions of years later, scientists are still trying to read that blueprint and unlock its secrets. One of the most fascinating things about dark matter is how it forms something called dark matter halos. Imagine these halos as gigantic invisible clouds that gently surround galaxies like a protective bubble. They are not made of anything we can see, touch, or shine light on, but they are absolutely real. These halos help keep galaxies from flying apart. Without them, the stars in a galaxy would spin out into space and the galaxy itself would fall apart like a merry-go-round without a center pole. Scientists believe that every single galaxy in the universe, including our very own Milky Way, is surrounded by one of these mysterious halos. This idea was a major turning point in our understanding of the universe. It showed not just that dark matter is real, but that it plays a vital role in keeping galaxies together and in shaping the way they grow and move through space. In fact, without these dark matter halos, galaxies might not even exist the way we know them. One of the most important tools scientists use to find evidence of dark matter is a clever trick of nature called gravitational lensing. Here's how it works. When something incredibly heavy, like a galaxy or a big cluster of galaxies, sits between us and a more distant object, its gravity bends the light coming from behind it. This bending doesn't just change the direction of the light, it actually makes the object behind look brighter or distorted, like you're looking through a glass lens. This cosmic lensing effect is incredibly useful. It helps scientists see mass that is invisible, because dark matter, while unseen, still has gravity, and gravity bends light. By studying how the light is stretched and curved as it passes through space, researchers can map out where the dark matter must be. Time and again, they've discovered that there's way more mass in galaxy clusters than we can see with any telescope. That invisible mass is believed to be dark matter. So even though we can't directly observe dark matter, we know it's out there because it pulls on light in a very noticeable way. This light-bending effect has become one of the strongest clues that dark matter really exists. When light from distant galaxies passes through massive clusters of galaxies, the light gets bent, just like a beam shining through a magnifying glass. Scientists study these strange patterns of distorted light to figure out how much dark matter is present and where it's hiding. This has helped us draw much clearer pictures of how dark matter is spread across the universe. But that's not the only method researchers are using. They are also looking at something called the cosmic microwave background, or CMB for short. This is the faint glow left over from the very first moments after the universe was born, about 13.8 billion years ago. By analysing tiny changes in this ancient light, scientists can find more clues about how dark matter influenced the early universe. Even though gravitational lensing and the CMB give us strong hints, scientists are still chasing the ultimate prize, discovering the actual particles that make up dark matter. According to one theory, dark matter might be made of special particles called WIMPs, which stands for weakly interacting massive particles. These particles are believed to be incredibly shy. They barely interact with regular matter at all, which makes them extremely hard to find. To try to catch one of these elusive WIMPs, scientists have set up some amazing experiments. Some of these detectors are buried deep underground, in quiet places where nothing else can interfere. Others are built into giant machines like the Large Hadron Collider, a powerful particle smasher located in Europe. These experiments are designed to see if, just maybe, a dark matter particle will bump into a regular particle, creating a tiny spark of evidence. So far, no one has seen a dark matter particle directly, but that hasn't stopped the search. In fact, every experiment, even the ones that don't find anything, helps narrow down the possibilities and brings us closer to the truth. Scientists say that even the smallest clue could unlock some of the deepest secrets of the universe. Dark matter remains one of the biggest mysteries in all of science. It is invisible, but its effects are everywhere. We can see its influence in the way galaxies move, in the shapes of galaxy clusters, and in the fingerprints it left on the cosmic microwave background. All of this proves that dark matter is real and powerful, even if we don't yet fully understand it. Studying dark matter is not just about the past, it's also about the future. The more we learn about it, the more we understand the invisible forces that have shaped the universe from the very beginning and continue to shape it today. Dark matter might even be linked to another cosmic mystery, dark energy, a strange force that is making the universe expand faster and faster. By unlocking the secrets of dark matter, scientists hope to learn more about how everything in the cosmos fits together, and what might happen to it billions of years from now. And the journey has only just begun. New missions in space are opening up even more ways to study the hidden universe. The James Webb Space Telescope, launched in the year 2021, is giving scientists the clearest view ever of faraway galaxies, stars, and cosmic structures. By looking farther and deeper than any telescope before, it could help reveal how dark matter shaped the universe from its earliest days. Back here on Earth, researchers are building even more advanced dark matter detectors, some placed deep under mountains, others even floating in space. These devices are designed to catch the faintest signals from dark matter particles. With every new tool and every new discovery, we come one step closer to solving this cosmic mystery. Dark matter may be invisible, but it is one of the most powerful forces in the universe. It has been shaping galaxies and stars since the dawn of time, and while we're still only beginning to understand it, the discoveries we've made so far are incredibly exciting. The discovery of the universe's very first stars is like opening a magical window into the deep, distant past. These ancient stars, known as Population 3 stars, are unlike any stars we see today. What makes them truly special is that they were made from only two basic ingredients, hydrogen and helium. These were the only elements floating around in space shortly after the universe was born in a powerful explosion called the Big Bang. These first stars didn't appear right away. They came to life during the universe's early, wild, and mysterious years, long before galaxies or planets had formed. Today, scientists are using the James Webb Space Telescope, or JWST for short, to search for clues about these stars. This incredible telescope allows us to look back billions of years, almost like using a cosmic time machine to glimpse moments that happened near the beginning of everything. To understand how these stars came to be, we have to go back around 13.8 billion years to the moment of the Big Bang. That was the instant when the universe began, an unimaginably hot and dense explosion that started it all. In just the first few minutes after this event, only the simplest elements could form. These were hydrogen, helium, and tiny traces of lithium. Hydrogen, which is the lightest and most common element in the universe, is made of just one proton. Helium comes next, with 2 protons and 2 neutrons in its nucleus. Together, these elements became the first building blocks of the universe. At that time, heavier elements like carbon, oxygen, and iron didn't exist yet. They would only be created later, deep inside the hearts of stars. In those early days, the universe was a dark and silent place. There were no stars, no galaxies, and no light, just vast clouds of invisible gas. This pitch-black chapter in the universe's story is called the Cosmic Dark Ages, and it lasted for hundreds of millions of years. It was a time of great stillness, but something powerful was slowly beginning to happen. Gravity, the force that pulls objects together, began to work its magic. Over time, gravity started pulling together the floating hydrogen and helium gas, squeezing it tighter and tighter. As these gas clouds collapsed under their own weight, they became hotter and denser. Then, finally, the first stars were born, and with them, the universe lit up for the very first time. These first stars, the population 3 stars, were nothing like the ones we see in our night sky today. They were absolutely massive, many of them hundreds or even thousands of times bigger than our sun. Because they were so large, they burned their fuel very quickly and lived short, brilliant lives. While stars like our sun can shine for billions of years, these giants only lived for a few million years before dying in dramatic explosions. Since they were made only of hydrogen and helium, they didn't have any of the heavier elements that stars today contain. That's why scientists gave them the special name Population 3, to separate them from younger stars, which belong to Population 2 and Population 1. The Population 3 stars did something incredibly important. They ended the darkness of the Cosmic Dark Ages. When they began to shine, they released powerful ultraviolet light that changed everything. This light started a major transformation called cosmic reionization. Before this happened, the universe was filled with neutral hydrogen gas, which blocked light from traveling. But the ultraviolet radiation from these early stars had enough energy to knock electrons off hydrogen atoms, turning the gas into ionized hydrogen. This process made space more transparent, allowing light to travel freely for the first time. It was a turning point in the history of the universe. These giant stars may have lived short lives, but their endings were spectacular. They didn't fade away quietly. Instead, they exploded in supernovae, huge cosmic blasts that scattered newly created heavy elements across the universe. During these explosions, elements like carbon, oxygen, iron, and even gold were thrown out into space. These materials would go on to form new stars, planets, and eventually life itself. In this way, the deaths of Population 3 stars were not just endings, they were also beginnings. They planted the seeds of everything that would come after: solar systems, oceans, trees, animals, and even people. Studying these stars is one of the hardest tasks in modern astronomy. Because they are so incredibly far away, the light they gave off has been travelling through space for more than 13 billion years. By the time it reaches Earth, that light is very faint and hard to detect. Instead of seeing the stars directly, scientists look for clues they left behind. One clue is the enormous bubbles of ionized hydrogen that may have formed around them. These bubbles were created by the powerful light from Population 3 stars stripping electrons from the surrounding gas. By measuring the size and shape of these bubbles, astronomers can learn more about the ancient stars that caused them. The study of Population 3 stars isn't just about understanding the past. It's also about discovering how life began. These stars were the first to create the heavy elements needed for life, like carbon and oxygen. Without those elements, planets couldn't form, and neither could living things. By learning how these early stars lived and died, scientists can better understand how our own planet, and all life on it, came to be. Population 3 stars also help answer big questions about the universe. They played a key role in forming galaxies, black holes, and other giant structures in space. By following the story of these stars, from their birth in dark gas clouds to their fiery deaths, we begin to piece together the grand puzzle of how the universe changed and evolved over time. Each new discovery adds another piece to this cosmic puzzle, helping us see the big picture of how everything in space, including us, came to be.